make it better. Let's do something else. Let's talk about the renumber thing. All right, so I've got this section here. I want to add some more code between this hello world and this little, loop that's going to print out some characters. If I select a piece of text, I can renumber just that text. And I can specify where do I want the numbers to start at, what the increment is. So yeah, I'm going to say start at 100. So that just takes that block. If I had things inside this block that were go-tos or go-subs, it would actually recalculate those and give me the new line numbers, which is pretty cool. If I didn't select this as a block, I could just renumber the entire program. I'm probably going to do that a little bit later, so hold on for that. All right, get some more space here. All right. Let's do a screen code. Yeah, let's do that. All right. So same as I showed you when I was in Vice, and it knew how I could do like certain codes. That's how I got the little reverse heart to clear the screen. Can't do that exactly here. But what I can do, if I open up a quote, there's a screen code builder. So in this, or you can hit F4. The screen code builder gives me a keyboard or this key map or this handy little key codes thing here. And so from there, I say I want to clear the screen, and I want to turn the text white. A little kind of like workspace here. I can mess around with it, but then when I say update, it's actually going to take that and pop it into that where my insertion point was back in the code. So I'll update that, and there it brought that in there. So that's going to, when I do this and bring it over to the emulator, it's going to give me the actual heart and then the little E, the reverse E for making it white. So that's kind of cool. All right. Okay, let's talk about comments. This is a pretty typical comment, right? Everyone knows this one. That one's no different. That will actually get in the code, and it will come across, and it'll still be there. There are two other types of comments that this editor supports. One, let me add something more in here. Let me add a, yeah, I think I'm going to do that one. Let's do that, and just do a little, wait for a character. All right, so then I have this little block here, these two-line block that I want to have a listing-only comment. A listing-only comment is an exclamation and a dash. And when I compress this and send it over to the emulator, it removes these listing-only comments. So these are just for me to see and kind of move and keep things arranged in here. There's also a really cool block comment. So if I go in here, this little loop for the printing out the characters, I want to add something here. So I'm going to go to Edit, and there's a comment block. It gives you this little thing where I say, loop through some characters, and what do I want to have as a boundary? Because it's going to draw a nice little box around this. And there. So that gives me a nice little block comment. And once again, it's a listing-only comment because it has the exclamation and the dash, so it's not going to end up in the eventual program code, so that's kind of cool. All right, so I've got this section here, and since I know what this is, I'm going to say, let's change this comment to be something more descriptive, like wait for a key. There's a thing where you can do regions. Regions allow you to collapse and expand code pieces. So the best way, you can do that by typing this region thing, but I like this way. So I'll highlight a section of the code, under the edit menu, under the selection, they call it a fold. So I'll take this fold, and it will then collapse that little bit of code. Gives me the little region. I can put something after the end of it here. That's where I wanted my comment to be really for, I guess. So when you're working with like large chunks of code, it gives you an easy way to kind of collapse things into, and you can kind of say these are like things, and I know what they are. I'll keep them out of the way. So the regions are pretty cool. Oh yeah, let's do this. All right, so loops. Let's make this a little more interesting by jumping over a few characters along with the loop. So instead of just having a line, let's do it so it's we'll be going across. All right, so I always wish I could do this back before, but so now I got these. There's this indent and outdent, so I can move that over so it actually looks a little bit more like a modern programming language, so I can kind of keep track of like, what the heck is going on between these loops? So that's really handy. All right, I think that's the pieces I wanted to show. Let me see if I've missed something. I'm trying to keep my notes here because I just made this last night. Oh, yeah. All right, good. Oh, I know what I need. I need for this, after I press the key, I want to clear the screen again. That's what I forgot. All right, see, I'm going to do it the old-fashioned way. I didn't actually have to go into the screen code thing. I could just type the same thing with that, that format. All right, so code looks a lot different. Code doesn't quite look like C64 Basic in some ways, but it's pretty cool. All right, let's go look at it in the emulator. All right, no surprise there. Cleared my screen, waiting for any key. There it is. So if I list this though, wow, that's all it came out. So all the other good stuff with my white space and my indenting and my regions and my other listing comments, all gone. Pretty cool. All right, let's do one more thing and then we'll get back into the other bits. I told you how I can have multiple files. So what I want to do here is create a separate basic file, add it to the project. I'm going to call this one subs. All right, so in this new file, I actually want to take, this is sort of a simple subroutine, you could say in some ways, so I want to take this piece out. I wish it had a nice extract to file, but it doesn't. All right, so that's kind of cool. But, so now it's a subroutine, I really need to have these numbers. So let's highlight, no, I don't need to highlight the text, this is my whole file here. So I'm going to go into the renumber. I'm going to say, let's start that at, I don't know, line 1000. So then handily renames that. Also realized that my goto is part of that, and it renumbered that as well. Pretty neat. So I'm going to make it a subroutine. I also need to have, line 1030 here to, return. Okay. So now I know I've got in this subs.basic file, I've got this little subroutine that's going to wait for a key, starts at line 1000. So take that out. Go sub 1000. But there's no 1000 in this file, right? Where's it going to come from? Oh, hang on. There we go. Make sure I end. But this is going to work. And why is it going to work? Because it's this is more of a project. So if I go to the project and build this and run this, I think I got everything, right? Let's see. Nope. I got an invalid line number. 1000 is right. Oh, thank you. See, I'm really thinking way too modern language, wasn't I? All right, got past it that time. So, looks the same, performs the same. There it is. It takes those two files. So you have to be careful. One, I guess, obviously you have to remember to put a line number when you put the go sub, but you also, it will combine all those basic files together so you can keep things in line. You have to kind of watch out for your line number, so that does become a problem. All right, wow, I think that was all the bit I wanted to show on that one. How am I doing on time? Wow, it's almost 9. All right. All right, let's try something else. All right, we've talked about the code editor. Now I want to talk about what I think is one of the coolest things I wish I would have had. There's a screen editor. And the screen editor allows you to do a lot of cool stuff and generate this code. So let's go and take a look at the screen editor. All right. I'm going to close this project down. Create a new project. Let's call this screen 1. Don't need a Git repo. Okay. In the tree here, there's a thing for screen designs. So I can either add a new screen design, or there's a way you can add an existing file. So I actually have one of these prepared already because I want to show you one of these built. So I can navigate over to another folder, choose one of these, and it copies it into this project. Now, the screen editor is a separate tool, so when I click on this, it brings it up in a separate kind of modal dialog. So this is a screen that I built the other day. I don't know, a little border, some grass. I don't know if that's supposed to be a sun, maybe. So this grid allows you can scroll through and you can click and select characters. Kind of got a nice little pesky map here, so I can pull them together that way, and it's really just sort of like a click and place thing. There's also, from a mode, I'm in this draw mode. You can also go to a lines mode and a boxes mode. So with the boxes mode, I can actually drag and drop. It looks at giving me a selection area, and then it knows to use the pesky characters to draw a box like that, which is pretty cool. There's also a line mode that does similar things like that. And I can also go into a text mode. So let's make it white text. And because I'm in text mode, I can select into an area here, and I'm just going to start typing. Let's see. Press any key to continue. Ooh, wait, that did that forced uppercase. Let's see, forced uppercase. There we go. All right, so I got this screen. Let me save this. And now I want to put it somewhere. Before I do that, let's go back into the basic file. I'm going to, no, there we go. Export to basic. Give you some option here besides what you want to have it to generate this code. You want to have it generate the empty rows, where do you want the line number to start. Let's do that. It gives you this little actual basic printout using the screen codes from what I just drew on the screen there. I'm going to say copy to clipboard and close. Let's add a new basic file here. And I'm going to paste that code. And so this is all the code for that screen. I want to do one thing to make this a little more interesting. So I want to put that semicolon at the end of that line there. And I want to, line 283, let's, wait for it to press a key so it doesn't roll off the screen and print that ready thing at the bottom there. Okay, string equals nothing. Then go to 283. All right, so that's what we just built this screen. We exported it to code. Let's see what it actually looks like in the emulator, huh? And that's the screen we just built. Pretty cool. All right, let's try something else. I've got another program that I wrote a long time ago. And I'm going to do the same thing that we were trying earlier. So let's start off with, let's just close this project and make a new project real quick. Call this one Quest 1, no Git repo. Okay, so like I said, I made this program a long time ago. And let's see. Called Quest. There it is right there. So this Quest program has kind of like a little screen I built inside of it. I guess I was trying to do something there. I never finished this, obviously. Well, maybe not obviously, but I never finished it. But it draws these little mazes, and then in the mazes, you'd use the joystick and kind of wander around in here. Then once it wouldn't let you run into the walls, and once you hit something else, it like thought there was supposed to be a different map, and it would take you somewhere else. Anyway, so that is actually implemented in code, right? because you can see like the little maps, like the map templates in the code here. So let's try something and see how this works. All right, I am going to, once again, go and I want to import a basic file. So I'm going to go and I'm going to browse to that disk image there. Let's see. All right, so this is that program that we just saw. Of course, it had to convert all those pesky characters over into all this stuff here. And, you know, I want to do a different map. So what I'm going to do here first is I got this whole section here highlighted that I want to replace this map that was already in the original listing. I can comment out that entire block. Pretty handy, so I don't have to lose that block. Let's create a little space here. Now, I also don't know how many lines my new screen is going to take, because right now this is pretty tight. It starts right off at line 70. So let's renumber this whole program. So I don't have a selection. It's going to do the whole thing. So if I go in here and say, I don't know, let's renumber it starting at 100, and let's go increments of 100 just to see, just why not? In there. So it just renumbers the entire program. And I've got a lot of space here between 200 and 300 to do something interesting. All right, I actually prepared a screen design for this earlier, so I'm going to go ahead and add an existing file. I'm going to choose that screen design here. Maze. So this is the little screen design that we saw in code earlier, right? Now, because I think I made this on graph paper or something. I don't know why I was being so conservative with the size of it. I don't know. I don't remember. But there's no reason to be that conservative because the program like just looks at like, you know, prevents you from running over a checkerboard character. So I can make this maze anything I want to. So if I can go in here and just erase chunks of this old maze, if I want. And let's go here and pick the checkerboard. And I can just extend this out, make this a little larger, and just keep it safe so I don't crash into things. And I don't know, not really trying to be too interesting here, but just kind of show how this works. Create some other areas now, and you saw that also it's when I hit the diamond pattern, that's when the program seemed to know it wanted to do something. Box myself in there. So let's put a diamond out here. There we go. Let's put a diamond right there. All right, so I just kind of changed that up, whatever. So if I export this to basic now, wait, did I do that right? Where do I want to start? Oh, yeah, I want to do something between lines 200 and 300. So when I do the exporting to basic, I want to say start at line 210, increment by 1. All right, so that gives me my screen. Copy that. And I'm going to pop it right in this area. And that's it. All right. Is this going to work? I hope so. All right, see how it goes. Build it to the emulator. Wow, there it is. I just extended that maze, and things still work. So I can wander around here, and if I wander and hit the little diamond, it knows that it's still a diamond and jumps me around to the thing. So that is a quick way that you can use the screen editor to do some pretty amazing things. All right, are you ready for more? Can you handle it? All right, sprites. Oh man, how many people had graph paper and you had to design your sprites on graph paper? Right? I used to do that. I think I was supposed to be in biology class and I was supposed to be doing something else, but I remember I used to draw on the graph paper they gave me in biology class to do sprites a lot. All right, anybody recognize that balloon? Right? That was the first program I ever did that had sprites. It's in the user manual, you know, right there where you had the little program. All right, well this is pretty cool because there's not only is the sprite editor, which has a lot of different kind of neat things, how you can manipulate individual sprites and you know, create more. There's also a lot of really cool support in the studio for this. So if I go and create a new project, I'm gonna call this one SP1. All right. When he was building this and developing this, he put a lot of sample files in here. So under the file menu, there's sample programs, there's basic programs and assembly programs. And most of these are all programs that were from the user manual and the programmer's reference guide. So if I go to this balloon program here, this is that up, and away program that everybody has seen many, many, many times. Although I actually want to make it, I do want to make 2 changes so that you can see it better, right? Let's see, let's do this real quick. Line 25, I want to change the color of that, or change the vertical size. Yeah. I want to change the horizontal size. Sprite 2 to 29. That's expanding them. And also I'll make it, because if you remember this was like cyan colored when this program first comes out, so I want to make that sprite white. All right. Just to prove that I'm not lying, let's look at it in the emulator. And that's the program we all know and love. All right. Sprite editor. You can start from scratch, obviously, but there's a really cool thing here because, right, these data statements are all what's defining that one sprite. So if I open, let's go to sprite data, say add a new, I'm going to call it balloon ball. When I open up the sprite editor, it gives me an option to import from a listing, from memory, from a bitmap, from a binary file. I'm going to say from a listing, because I have a listing I know includes one sprite. And when you're importing sprite data, you can choose, if you know where the sprite's at, you can say if there's multiple, how to handle it. But I'm going to say this really cool thing called find sprite data. It's going to take that listing that I've got open behind me here, and it's going to parse it and try to find a sprite. And it does. There's the balloon sprite that it parsed out of that data. Now you can do a lot of things here, right? You can flip it left and right. You can flip it up and down, shift it up, shift left, shift right. The sprite editor gives you a lot of cool things here. You can also, there's this kind of scroll bar area here. You can actually load a series of sprites. So if you have an animation you want to do, so if you have one, you can copy it to a second sprite. Then you could flip it or rotate it or move it around so you could do an animation. And there's a scratch pad here if I've got a bunch of sprites loaded that you could play around with that animation. I've only got the one sprite, so I can't do much, but it kind of gives you a way that you can mess around with putting sprites on top of sprites and setting their priorities. So it gives you a lot of cool things you can do if you're trying to do an animation there. But anyway, back to this one. All right, let's change it. So, instead of having the Commodore logo, which we all love the Commodore logo, let's try something else. I want to do, since we're here at VCF, let me see if I can somehow put a little V and a little, I don't know, is that a C? Yeah. And an F. All right, next door looks like a VCF, I guess, yeah, all right. So, same as the way that the screen editor allowed me to export to code, I can export this sprite now too. So first of all, I know this data section here, I don't want to put it over it, but I like the comment thing, so let's comment out all of that old sprite data. I know I can start somewhere, anywhere I want to after line 70. So let's export this to a listing. And I want it to start at line number, I don't know, it doesn't matter. Let's start at line number 1000, why not? And there is the newly exported data for that sprite that we just created. We modified the Commodore to put the VCF logo in there. And let's see what it looks like. Let's give it a shot. There it is. Wow, VCF. Look how easy that was. Take an existing sprite that you could pull in from any program that has sprites in it. And it took me 2 minutes, right, to modify that, and boom, new sprite. Okay. All right, close the emulator. Let's see. We're doing okay on time. I'll see if I can go through this next section. Let's see how quickly I can do that, because I wanted to talk just briefly about the assembly language features this thing has. It kind of uses its own version of assembly. I know Kick Assembly has been a real popular one in the Commodore crowd recently. It's a good three-pass assembler. It's got everything you would probably want as related to labels, variables. It's got a way you can create a neat little basic loader or the syscall. I'll try to show you that. But there's actually a lot of good information out there. It's not that dissimilar from an old Commodore, a lot of the other C64 MASMs out there. So it's not going to be too alien if you've done a lot of assembly language. All right, let's try this. I'm going to, of course, start off with a new project. Close this project down. All right. I'll call this ASM3. Nope. All right. So instead of doing basic file this time, I actually want to do an assembly file. And because I don't want to have to type all this in, I actually did pre-create this. So I'm going to add it as an existing file. There it is. All right, so this is a real simple little program that's going to clear the screen. This is going to set the background and the border to red. A couple things, if I don't know if you know assembly that well, but I'm mixing things here, which is pretty cool, right? I've got some regular values, I've got some hex values, I've got an integer value here, because if you don't know, I mean, I didn't know this, but if you know D020 is actually 53280, from hex to decimal, I don't know. But anyway, you recognize those as old poke statements, right? I'm going to put 65 into the X register, put that into A. This JSR actually prints what's in the accumulator, increments it, compares it, see if I've reached the 91, and I'm looping back to this, moving the X to A. So what this is basically going to do is just going to print out ASCII, A to Z. That's what it's going to do. All right, so and I'm starting at this the beginning of the basic, right? Which is I don't remember what the hex 0810 is. It's 2064. All right, so what's this going to look like? Let's do this real quick. Build program, run. Oh, hang on, I got a processor error here. I had this problem happen to me last night. I had to open it and then reclose the project again. Hopefully we can get through this because this was really messing me up last night. I didn't know why this was happening. All right, let's build it as a project. File first. All right, no preprocessor errors. All right. When this loads this up in the emulator, it doesn't do anything, right? You're like, why did it do anything? Well, because it just put it into memory. It didn't actually execute anything. But if I know that I poked the program starting at 2064, there's the program. All right. But that's crummy. You just saw how awesome that was when I was doing all those basic programs. I just pulls it into the emulator and automatically runs it, right? Well, of course, there's an easy way to solve this. So give me a couple lines of white space here. Under the tools here, I can either generate a basic loader, or I can actually generate a syscall. I'm going to generate a syscall here. It says, where do I want to start it at? Do I want to comment? I want to start it at the beginning of basic. Yeah. There it is. So it puts something right there, gives me this little loader. That's basically all it's going to do is basically say sys 2064, which is this label right here. So now, if I build this, let's see, build to file. Yep. And then I'm going to build it and run it. Launches the emulator and actually runs the program. So the syscall is a neat little handy way to get into that. Okay, wow. I think we are 11 minutes left, so I think I've just about made time. So I didn't talk about everything. Remember that long list of features that I brought up at the beginning? I didn't, but I did talk about the Sprite editor, the screen designer, the screen code builder, we saw that. I saw most of all the editing stuff, but there's things we didn't talk about. The character editor, there's a character editor that is just as fully functional as that Sprite editor and that screen designer. You can actually bring those into the screen editor and have your custom characters in the screen editor. Very cool. I was never much into music, but there's a really cool SID tool. I haven't really made much with it, but it's also built in there. The assembly language I showed you, there's a built-in debugger, so you don't have to use the Vice debugger. You can actually do a little memory map and actually see things right there in the IDE. There's a bunch of cool basic constants that are built in. Really worth it. All right. What should you do next? Have I inspired you? I don't know. Have I confused you? Perhaps. But the tools are all free. I'll post them in the Discord channel where the links are. You can get all these things I showed between the Durmaster, Vice, and the CVM Perk Studio. It's all there. Has a really good help file. In the help file, there's tutorials. And you saw the other thing where I could generate sample programs. There's a lot of ways you can get stuff out of there. There's also books. There's a guy, he's not the guy who made the program, but this guy, he goes under the handle Old School Coder. He actually has published, there's 2 books on Amazon that he's written about how to use these tools to develop for C64s. There's a whole lot of YouTube videos, so you can check his out. And then really just try it out. I think the first thing I ever did with this was I wanted to take it and I built it to a D64 file and I put it on my C64 Maxi and wanted to see it run on like, well, almost real hardware, so it was pretty cool. And that's all I got. I guess we got 10 minutes, so you can like take a breath. You just like soaked in all this amazing things, think about all the things you want to do, or ask some questions. So what do you got?
So the IDE, you said, remember how it changes the PET-C characters, and can you display the characters?
No, so the question is how in the IDE that we were showing all the character codes. Let's see, do I have one of those real quickly?
Like your maze, for instance.
Yeah.
I wrote a lot of programs like that too.
This one. So the question is there a way to get these back? And the answer is no. So there are 2 different formats for this. I don't know if you can see this very well, but in the options under the basic code generation, these are the 2 standards. TOC64 is the one that I like because that's the one that I first used. It's the older standard. There's also a bass text format. It uses parens and different codes. It's very similar. But I think that was one of the trade-offs he made, and that's why I always use that Durmaster tool and have that around, because if I want to see what that used to look like. Let's see, yeah. They actually put a lot of effort into being able to display those like this. So it took me a while to get used to that, because I was used to like being able to like just look at the code and like see it and see the images like this. But as I started getting used to using the screen designer for everything I did, it kind of bothered me less. So I'm not sure if that helps, but yeah, that was my first reaction to it. I'm like, I want to see this. I'm like, I'm looking at all this stuff. I don't see all this, all these like 166s and stuff like that. Good question though. All right, anybody else? Yeah.
What's the support like for disk files? I mean, I saw you using Durmaster bringing things in, but if the program reads and writes to files, like open, 8 comma, where does it send these? Can you see those files in the program?
Okay, so the question is really like, I was doing a lot of things where I was compiling things and I was putting them into PRG files and D64 files, and where do they go and can I see them before I run them in the emulator? And the answer is it is all in, let's see, I'm not sure if you can build, let's hope you can see this, okay. So here's all those project files I was creating here. It actually builds them to, this is to a PRG file. That was a subtle difference. I'm not sure if you saw that or not, but sometimes when I was going to the build menu, I was saying I want to build the program. Sometimes I was saying I want to build the project. If I build the program, it creates a .prg file. And that PRG file, you can look at it directly. There it is. It's a really, this is that PRG file that I had there. It's got one program called Quest 1. I could, that .prg is a format that that Vice knows how to actually mount that directly with a parameter. That's actually what it does. If you see in the output here, if I build this program and run it, it actually starts the emulator and it passes in the parameter for what the thing it just built was. And as well as, like I said, if I do it, as I say, don't build the program, but I say build the project. I do that for something. Was it ASM? Yeah, well, there's PRG files. There's ways that you can also, that will build a D64 file.
That has probably answered the question, that you can build it out to I guess you did say that, then you moved it over to the new hardware.
Yeah, which is just as easy. Like I say, you can take any of those PRG file and you can create a new disk image here. It says it's got them all, D64 all the way through anything else you can think you can possibly want. So I could create a new image here, and I could take any PRG file and move it around. Like I said, this tool is like crazy helpful if you're dealing with anything off an emulator and back onto real hardware. You've got to have this Derm Master tool.
That's great. I have not heard of that. The other two, particularly Vice, been around a few years.
Yeah. Cool. All right, I've got another couple of minutes. Anybody else? Yeah, go ahead.
So have you written any moderate and large programs?
I wrote this Hammurabi program, and that's when I first started realizing that I started that program during COVID, and I started writing it directly when I got my Maxi. And I'm like, that's when I started going like, God, this is impossible. I can only see this much of the screen. I'm like taking the handwritten notes again. So that's when I looked around. I first started to use VS Code, and I wanted to use VS Code for that. And I tried some plugins, and it was okay. But like I say, VS Code has even more problems with not knowing Petsky. Then I stumbled across the CBM Perg Studio, and that changed everything. And I was able to. That's one of the first things I did was like, how do I create multiple basic files so I can have all this program logic put in different spots? You know, you saw how fast this was as far as like I opened, closed, created projects. It's super fast. And anyway, it's like the code and all the artifacts are like really small, right? So I have had no problems using any large programs either.
That's really cool to see. Thank you.
Cool. All right. All right. Thanks, everybody. Thanks for coming. Enjoy the rest of the show. Really well, I think.
All right, great. Thanks for coming. You're a new guy, right?
I am. I was a attendee last year, and I was passionate about this, so I was glad to get to come.
Great.
You're Jeff, right?
I am Jeff.
All right. Nice to meet you, Jeff.
Thanks for coming. It's great to have new speakers on different things.
There's an off switch there somewhere.
Yeah.
Yeah, no, I think I love this topic, and I really thought it was going to be like me and like two other guys in here. I didn't know anybody else would be interested in even hearing.
Right. It's always a surprise until you get here. Yeah, he can, I don't know if I know his plans, he has other microphones, I don't know, I have to ask. All right.
So I
Is
can,
it safe to grab this, and,
Yeah.
or should I not touch it?
so I was
Okay.
anything, first of all, is it
Rhinour.
right now?
Oh. Rendering, but it's not
a
done by
very
me.
nice rendering.
It is a very nice rendering. Don't know what to say. Oh yeah, I came from Bay Area, San Francisco.
San Francisco, yeah.
Yeah,
And you're talking about SCSI host
Yeah.
controller for
for the
Amiga
Amiga.
4099.
Yeah, that we reverse engineered.
Officially, we got about 14 minutes.
close enough? No, to start, 1 minute. Or just wait till actually, okay, whatever. Hi, no, you're good. Morning. Am I on? There we go. Morning, everybody. Welcome to VCF East 2022. And coming up right now, traveling all the way from the San Francisco Bay Area to come see us here today in New Jersey, giving a talk about Amiga 4091 SCSI host controller, reverse engineering, Stefan Reinauer.
Hey, thank you, everybody. I'm really happy to be here, and thanks all for coming and listening to me today. This is not so much a class as it is. I want to bring you in a journey that I took over the last couple of months on rebuilding an old SCSI controller that used to be really rare, let's get started. So I want to tell you, I didn't do this alone. Every good project is comprised of a team, and in this case, the team was comprised of Chris Hooper and me. Chris is both of us are originally firmware engineers. We met in the Bay Area. Chris is also the founder of a company called DSSD. And I'm working for Google as an engineering manager. We have a number of open source projects that we both worked on. A lot of my career I spent on firmware projects like Coreboot, OpenBIOS. I did some work a long time ago on UAE, the Amiga emulator. Chris worked on a version of the Berkeley fast file system and built his own version of the RGB to HDMI, some of which you may know. So what is this project about? We're building basically a brand new 03 SCSI controller. And this project, during the whole lifetime of the Amiga, there were only really 2 03 SCSI controllers ever built. 03 is the bus that powers the Amiga 3000 and the Amiga 4000 and is significantly faster than the 02 bus that it precedes with, in theory, it being a direct competitor to PCI. In practice, the implementation is not quite as fast as the original PCI versions, but it was getting pretty close. So what we're doing is, this card is also supporting DMA. It supports the FastSCSI 2 protocol, which in theory supports 10 megabytes per second. I know, it's not very fast today, but back in the day, this was a killer card. The card was originally designed for the Amiga 4000, had pretty hefty hardware requirements in terms of the latest bus controllers. So it needs a Buster 11. Well, I'm saying minimum. There's rumors out there that we might see a new one any year now. There's also, the card is powered by an NCR 53C710 chip, which was a state-of-the-art a SCSI controller chip at the time, and it supports auto boot through a ROM. So you plug into your Amiga and you can boot right off the hard drive. So how does this start? How does anybody start doing a SCSI controller, right? Well, the answer is, of course, because we can, right? The way this started is the pandemic happened, and I started learning soldering because I had a lot of time in my garage. And in addition, I spent a lot of time chatting on Akel Paul Resendez's Discord server and found a guy, Chris Hooper. Turns out he lives 7 minutes away from me. which was ideal. So every time I ran out of parts in the early pandemic, I was like, hey, Chris, can you come over and bring me a 74 F32 or something, right? Chris would bring it over. I would do the same thing if he got stuck. So that was the beginning. We did both like smaller projects. And then I would say by accident, I I got an A4091 SCSI controller on eBay. These things were extremely rare. Like you see one every couple of months pop up, maybe every couple of years these days. And so the card, it was only like the seller lived in Germany, which is where I'm originally from, and so he wouldn't send it to the United States, so I sent it to my mom's house originally. And then it sat there for most of the pandemic until finally, like in August last year, I was able to go home and visit my mom and pick up the package. So here's a rough timeline. So this has been a project of like the last 6 months, roughly. And so why now, right? Like why build this in 2022? So if you look at it, the prices really, like for all of these Amiga boards that you can buy on eBay or Amibay, they've really skyrocketed, right? And why? Because they're incredibly rare. Nobody makes this stuff. They're hard to get by. People now all have decent jobs. We all pay a lot of money for this stuff. But it shouldn't be like that. It should be available for everybody, right? On the other hand, also, I got pretty inspired by other folks in the Amiga community, namely Paul Resendes and John Hertel, who worked on a number of reverse engineering Amiga products, like reverse engineering the Amiga 4000 mainboard and reverse engineering the Amiga 3000 and a number of others, bringing like a lot of old machines back to life that died because the electronics went bad or the batteries or capacitors ate through the mainboards. And I was like, well, I'm not the guy to build like a complete Amiga from scratch, but like maybe I can do something like a SCSI controller, right? And then of course there's like one important thing to this whole story. It's the Dave Haney files, all right? Like Dave has published the all of the logic files for the GALs, the little SPLDs that are powering this board as source code. And so you can download them today, recompile them, put them on a board, and it'll work. The other card that I mentioned out of the two that exist, that logic is all secret, and most likely if these cards die, it's lost forever. So with all that going on, like the idea was really like, hey, can we create something that's like open and accessible, right? And like all of these things, like if you're looking at the Amiga today, you're not looking for getting the latest power machine that like features your nice 3D graphics and your latest games, but you're probably looking to learn something, to feel nice about the past, and to figure out, because all this stuff is so easy compared to what computers are doing today, you can look at it and you can understand it, right? So that was one of the aspects why we started doing this, really, and putting something out there at future generations maybe, or if it's whoever is interested, really, you can look at it and say like, oh, this is how this worked. And also, these guys that built the Amiga originally, and particularly also the 4091 SCSI controller, they've done an amazing job. And a lot of the work that is happening today, like a lot of the work that I'm doing, I got into computers because of the Amiga, or stuck with computers because of the Amiga. A lot of what I have done in my career wouldn't be there without this stuff. So it is a little bit of a tribute also to the shoulders of the giants upon which we stand. One thing that came to be in the, like, as the project moved along, we started looking at this and we're like, hey, we gotta like build a SCSI controller, right? What is the first thing you think of? It's like, let's build a PCB. There's lots of PCB projects out there, especially during a pandemic, this has exploded, right? Now, the next thing though is like, oh wait, this thing has a custom bracket. And then there's like, maybe also other stuff that was when you used to buy the product 20, 30 years ago, you got a box and a manual and an install disk. And so what really tickled my fancy there too was to create something that is not just like, here's a PCB, go and solder it yourself, right? It's like, can we create something that's really like end-to-end? That you look at it and it's like, hey, this looks like what you would have gotten back in the day. So that's how this journey started. And it started last August by me traveling to Germany and meeting my mom, and she was like, son, I haven't seen you in 2 years. Let's eat a lot of German food. And as I mentioned, retro computers are cheap in Germany. Cheaper, much cheaper than here in the US, particularly in the Bay Area. So I occasionally ordered something to my mom's house, and then I occasionally ordered another thing, and well, 2 years later, I had forgotten about this a little bit, right? Like how much actually might have happened. I got home and my mom had like built this tower of stuff. Honey, don't look at this. Well, coming back, I met Chris, and I said, hey, Chris, we got to build a SCSI controller, right? And it's like, how do we go about this? Okay, we got to take some pictures of the thing so we can like map it out and figure out what's going on. And my first thought was, hey, we can put it on my printer and just scan it and we'll get high-resolution pictures. Well, that was a fail. I didn't put those pictures on there because they were just like completely dark and not sharp. And so we figured out a number of ways with cell phones and other stuff and stitched the pictures together. It turned out pretty well. And then we sat down in the garage and took a multimeter. And basically the way this works is you look at, you try to figure out roughly what the schematics should look like. But in the end, if you reverse engineer, there's only one way of getting through this. You measure every single connection between every single pin on the board. And that's what we did, and we started writing it down. It took us weeks and weeks and weeks, and sometimes, like, this is something that really was enormously helpful to do this with somebody else. Because sometimes you just start fading off and go like, oh, did I measure this one already, or did I forget about this one? Is it really connected to that pin? If somebody else listens and writes and then you do a shift, it goes a lot better, believe me. And of course, sometimes we were not quite sure what's going on, like under the chips and on other sides, on the other side of the board. And so I started taking the logic chips off and started looking at what's under there, and we started looking at the traces. And then we started making schematics, right? And so basically what happens is, in the past, there were 2 revisions of this board. Revision A was made by Commodore early on, and they built PCBs, they got it almost working, and then they had to ship it in a rush. And so there were a bunch of budge wires on the board, roughly like a dozen or so. It's quite the adventure if you get one of these early on cards. And then for revision B, because Commodore was not trying to be, I guess, in the business of building SCSI controllers, there was this company, DKB Software Incorporated, which then produced this board for Commodore. And what they did was they routed the bodge wires. They put the bodge wires onto the inner layer. So this is a 4-layer board. And so on a 4-layer board, what do you do? Like if you start reverse engineering, right? How do you figure out how the board is routed? Well, one way, and I believe that John Hertel did this for the Amiga project, is that he sanded down the PCB and until he saw the inner layers, and then he drew them up, and that was it. Now, it hurt my soul to do this, all right? I can't say it differently. I did not want to destroy the one original working board that I had because it was rare, and I didn't know if I would get another one, and who knows, maybe I need to measure something later on in the project, so destroying this one thing would have been a really bad idea. Well, gladly, we got a lot of this done just by shining a flashlight through. And because literally we found out that it was only the bodge wires that Commodore had added that they routed through here. So you can see this in the picture here. It is actually, if you're using a flashlight and you're shaking it around a little bit, you can see it much better than on the picture, but it's hard to put this in the picture. And then once we actually figured out all the wires, right? So this is what it looked like. Each one of these blue lines is one of the connections that we measured. And then we started placing the components as close to the original. And then we started routing also as close to the original. And this was one of our goals really for this version of the card, to create something that is as close to the original as anyhow possible. Of course, there's like these days you would, if you built this from scratch, right, you would optimize some things. You would maybe make the card shorter so it's cheaper or whatever. Like there's ways to optimize this, but the first version that we built, we wanted to make it authentic. And the one thing, however, that we didn't keep authentic entirely was clear labeling, because we wanted it to be easy to build. So if you look on the back side of the PCB, all the caps that are soldered on there say their values between the pads. So you cannot see this once it's assembled, but it's on the board, just to make it easy without having your documentation in front of you at all times. And this is what the final board then in the first version looked like. As a EDA software, we used Easy EDA. Easy EDA is, I always found it weird to do this stuff in a web browser. And mind you, I work for a cloud company, but this was kind of like I started out using KiCad, and I thought that was pretty nice. But one of those things, like with Easy EDA, it is fantastic for collaboration. Like Chris and I, like even because we would not get together very often during a pandemic, and when we did, it was kind of troublesome, and so we could do this at the same time while he was at his house, I was at home, and so we were working, and we always had the latest version of what the other person had put in, and we could communicate about this very easily. So this was a great way. Now, let me tell you, for manufacturing, it turns out it hasn't been the best thing ever, because getting easy ADA files to certain manufacturers is a little troublesome. As long as they take Gerbers, that's great. But some folks want more than Gerbers. They want the original files, especially when you go into manufacturing the cards. And this gets a little tricky. But that's still a journey we're embarking on. So let me talk a little bit about the level of detail, all right? So there's, one of the things that DKB added was this little seal over there. And so we did exchange the seal and put our own initials in there. We did update the timestamp. I think it's at 93. We updated it to 2021. But other than that, like we really tried to get very, very close to the original board, and including, we found this, like when we started looking at the board under a microscope, and we found this little tail hanging off one of the vias. We were like, is there something wrong with the board, right? Like, what's going on here? Like, maybe this cap might have leaked and eaten up this trace, but no, it's just like a little tail that's left. So I don't know if Dave, I think he's not here right now, but like if I meet him, I want to ask him. It's like, what's that appendix for? I mean, quite frankly, these guys, when they built these boards back in the day, right? Like they drew this stuff up by hand and then they erase parts and like redraw it. And at some point, it's like, this is good enough. That's what I'm thinking where stuff like this is coming from. But yeah, they didn't have all the fancy tools that we have today where you have, so we didn't use an auto router at all because we wanted the routing to be identical. But in theory, if you build something from scratch, obviously, like you have an auto router available and stuff like this would not happen, right? And you move something around and it gets rerouted and everything looks nice all times. Well, at this point, a short stop to say thank you really for the people that have been helping with this project. And first and foremost, obviously, Dave Haney, who was originally working on this board, and for really make this possible. But also, I want to say thank you to Simon Gosk, who is the guy rebuilding Amiga cases. He lives in the UK. I think he's originally from Poland. And I started chatting with him about this project, and I was like, oh, like, how would you go about building custom brackets? And he's like, I know how I would go about it. I would talk to my boss, and I would ask him if I can have his machines for a couple of days, and I would do this. And so I was like, well, I don't have a boss like that. Could you maybe actually ask him? And so he did, and this was a big help. Tim Iyer, who was also a big help for the project. He has one of the few remaining manuals of the Amiga 4091, and he sat down and scanned it, and he did a fantastic job. Like the manuals, the original manuals, they were really flimsy. I'll show you in a little bit. And of course, Jeff Brace for answering my late night panic calls last night. Thank you, Jeff. So brackets, right? The first thought was, hey, we can 3D print something. That'll be good enough. And so we made like a little model, and this, basically what's going on is you cannot use PCI brackets that are more readily available because on PCI the back of the card is on the other side. And so these are basically just inverted, mirrored versions. But then also most cards anyways don't have this large to where you screw your hard drive against, right? And so turns out you can 3D print something like this. It works. It's around here. It gets a little bit tricky. This is the original bracket that I took off the board. But it's better to make something. And this is a photo that Simon sent to me from the production line. So they were all laser cut and then bent. And I had long discussions with him because he was like, this double bend that you see there to keep the pins safe. It's like, can we optimize that away and just put a hole in? And I was like, well, yeah, that would work. And then it's like, but can we try to do it anyways? Because it would look much closer to the original if we had that double bend. And so these double bends need a lot more sophisticated machinery, basically, is the problem. And of course, at the same time, we also try to do this ourselves. Chris built this bracket over there, and you can tell, like, without the machinery, your bends look a little more round than they should be. And this is the 3D printed version. It looks nice, but if you look at it at the wrong angle, it will fall apart, and certainly won't hold your hard drive. One thing we did then was like some post-processing when we got them. So we put like some foil on the inside and protected the outside so that like if for whatever reason any parts are touched on the board, you don't short circuit the board and destroy it. Another challenge we ran into was the artwork. All right, so pretty much nobody has these boxes anymore. When you buy something on eBay, you get a board in like a silver sleeve, right? And that's it. Now, Big Book of Amiga Hardware has some pictures. And for the original that Commodore built, this is the best picture that I could find. It's like 700 pixels. You can not make out a whole lot of detail on any of this stuff, and certainly not get the dimensions of anything, right? And well, DKB, when they built the board, they did different packaging. I'm gonna ask you, which one do you folks think looks better? You like the DKB one? I thought, for my taste, the DKB one was like a little too colorful and peppy for the time. So we went with this one. Well, as I mentioned, a complete project end-to-end is not possible if you don't have a manual, right? So the original manual had 3 different languages, was like almost 100 pages. And in the scan, you can see it, well, this one's from a 1200, so it's not exactly the same, but you can make it out here, like the pages were almost translucent. You see all of the color from the next page blend through, and when you scan these pages, that is also what you see. So when we got the scans from Tim, we did a bunch of post-processing to get really the quality up. Chris did a fantastic job. Also, like the front cover and the back were completely redrawn to have an even higher quality. And so one of the things that we had to do to keep it affordable, because trying to print a manual in 3 languages and almost 100 pages gets expensive pretty quickly, and it's more of a gimmick. So we cut out everything but English at this point. And on the other hand, I have to say the new manuals actually look a lot nicer than the original Commodore manuals. So that's one positive aspect of the whole thing. And yeah, like it originally started out also with, we were like, hey, we should just like scan it and print it and then cut it and fold it. And now we're both firmware engineers. Firmware engineers and cutting hundreds of pages of paper does not work super well together. So it kind of worked, but it never looked great. So we had somebody do it, and with only 1 language, it's actually quite affordable. Well, the box. The box was a different kind of challenge because really nobody has this box left. We didn't have a good guidance on like how big does this thing have to be, right? There were obviously, we also couldn't get any scans, and so we only had to go off pictures. And what we did was we measured the card, and if the card was in the same picture with a box, we extrapolated between the card and the box. And then we're like, okay, at this angle, it's probably gonna be this high. And I think we got pretty close to the original. And then you draw it up in some web-based software, and when you order them, and then this is like me assembling all the boxes in my little office room at home. Yeah, I definitely have to say, like, building one of these is fun. If you're building like 30 or so, it starts looking like this pretty quickly. I think this is only like 15-ish right there. Another thing, so we had the boxes, right? And I was like, hey, all the original boxes, they have some sort of foam material in there. Like, what do we do? So I found on AliExpress, I found this fantastic noise dampening foam that you can order, and people were complaining about it online because it comes in a box, probably like this size. and it's very flat when you have to put it in the shower, and like with a shower head, you shower it off, and then it goes like, right, and then it becomes bigger. And then you have this giant thing that you can see in our shower over there, and of course you got to cut it, and like once it was done, our cat Katsu, she loved the foam pit. She was all over it. I spent another hour or two trying to get all the cat hair back off again. Yeah, and then finally, like our PCBs arrived, and the first one, we built 5 PCBs. We ordered 5 PCBs. So we were like, it's just a proto build. It's not going to work anyways. Let's start building this, and that was hindsight is 2020, obviously, but that was kind of a mistake because it turned out the boards worked all along. And buying only 5 is, of course, like not as economic as buying 20 or 30. So I assembled the first board, and it looked good, and we stuck it into the machine, and nothing happened, right? One of the things that happened was that I did a little mistake. We tried to power on the board first, and we attached a lab power supply, and we burned one of the ROM chips that we put in there. And so one of the pins, the VCC pin, fell off of the chip. We didn't notice it. These are rookie mistakes, really, but like this stuff happens if you've never done this before. So it's going at it with a lab power supply, not the best idea. I'm not exactly sure even how we did that. We figured because we saw like the card wouldn't show up, and that's because the all of the identifying information is not in the logic, in the ROM itself. And so if the ROM is dead, the card is just like never going to show up to the system. We fixed that, then the card did something. It showed up once, right? And that day we stopped and we were like, we did it. We got it working, yeah, right? Well, next day we were like, okay, let's attach a drive to it. And it's like, wait a second, this thing's not booting. And once you're actually like in the operating system itself, the card is also not there anymore. It just vanished from the bus. So what did we do? I plugged in Diagram, which has like a little more diagnostic functionality to look at Zorro cards. Diagram started endless looping because it was off. And so we were like, oh, so what seemed such a win yesterday was a big fail the next day. That sucks. So we got the little series there. We got our logic analyzer from Cellier out, which is like a nice little box. It has 16 channels, so you can check a lot of signals at the same time and compare them against each other. It's still a little tight for the Zorro 3 bus. You cannot look at all the signals at once, but at least it gave us some idea of what was going on. Now, what was going on was the Amiga just stopped talking, right? Like at some point, it was like, look good, look good, look good, and then silence on the bus. So we made a bunch of assumptions originally, and I want to talk about this because building a project like this, you're guessing, right? You're guessing, 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 and then you're verifying as you move on. And so in terms of the GALs, the logic chips on this board, the original 4091 used a -10 and -15 parts. My assumption was, naively, I buy Atmel parts that are all -10, and it's just going to work because you can always go faster. You just can't go slower, right? And then I don't have to worry about what I solder onto the board, in which order. And the original 4091 also had not only GALs, but also PAL-CE chips. The -15s were all PAL-CE. And of course, I thought, because I had built a 3660 before the CPU accelerator board, that the ATF 22V10 is like a fully compatible replacement. Well, more on that later. Also, we looked in terms of the ferrite beads. We looked at the Amiga 4000 schematics because those were open already, and they use a lot of 600 ohm beads. So with ferrite beads, the inductivity is measured at 100 megahertz, which when you just measure them like as a part, it's basically just like 0 ohms or whatever, right? So that's so we had no idea coming into this. We had no idea how to even measure this. So we had to do some research. It's like, how do you know what's on the board? And we assumed it's like, whatever, stuff we get on eBay or stuff we buy from Mauser is all the same, more or less, we hope, right? But as this smart guy, Albert Einstein, a long time said, assumptions are made, and most assumptions are wrong. And he proved to be, that assumption was correct. So we had to get a little more serious. We were looking, all this logic analyzing didn't get us anywhere, right? Like, just the signal looked good on the logic analyzer. My skills on the oscilloscope were not good enough at the time to actually see if the signals were like at the right levels or like slightly off, but still like in scope for the logic analyzer. So my hunch was like, hey, how sure are we? Because we took a big guess with those ferrite beads. What if those ferrite beads are off? And so at some point, Chris was like, hey, I got this a nano VNA. It's a very small network analyzer. I don't know how it works, but I got it from a previous job. Like, I read somewhere that you can measure these parts with them. So we started, it's like, how do we measure these parts? Okay, we got to take them off. So I made this list. I desoldered all of the parts, stuck them on a piece of paper, drove over to Chris's house when he had figured out how to do this, and we started measuring. And then as you can see, like right around 100 megahertz, all these curves make like some weird bump, right? And we were like, what is up with this? Like, we must be doing it wrong. Well, now it turns out the nano VNA is like a very cheap piece of equipment. They're like $80. And for the most part, it's accurate. Just like production, because of the way they're designed, they have this problem at 100 megahertz that stuff becomes inaccurate there. But we didn't know. We thought like, hey, maybe the parts are broken, maybe whatever. Like, so this is the nano VNA, and one of the things you can see down there, actually, like that little antenna thing, is if you want to measure these parts, right, you have to solder them to the probe. And so that's a lot of work if you're sitting there desoldering and soldering and desoldering and not being sure if you're actually doing the right thing. And you have to calibrate every single time you do a measurement before, because the antenna, the length of the antenna will have significant impact on what you measure. Well, it's a good thing. It's a good thing to have friends with better equipment. So, thanks God we had a friend with a $30,000 real network analyzer, and that helped us get the curves look a lot nicer. All right. It also confirmed that the original measurements were not that bad, so we could have just stuck with that. You don't really need the expensive equipment if you want to do something like this. But I wanted to put that out there. It's like sometimes when you're looking at these things and you're debugging and you're feeling stuck, getting a confirmation like that can just push you over the problem. So, what came out of this? Say, if you look at this curve, right? We put 600 ohm ferrite beads on there. Well, are in a range of like 60, 70 ohms here. And so that was one mistake. Basically, by the time you get to 25 megahertz, which is what the card is clocked with, these 600 ohm beads, they were just drowning out the signal and it was gone. Just enough to be a problem after a couple of iterations. So first thing I did was I soldered on 0 ohm resistors, and then later real ferrite beads. You just like say like, hey, the noise on the bus is not as bad as like completely killing the signal, and it worked. And so we, for the first time, like the card survived multiple reboots, was visible in the operating system, and saw disk drives. Yes. So we did some tests. Originally, I only took down the resistors, the beads for the Zorro signals, and then the card would work stable with SCSI 1, but not SCSI 2. We did the same thing. We were like, well, maybe Commodore or DKB used 60 ohms for all of them, right? So we tried that, and indeed, I measured some more, and indeed, of this was that the card would work at full speed. Now, full speed, in this case, the card does not do a 0.3 burst mode, so the speed is limited at around 5.1 megabytes per second at the moment. That's where the community comes in, hopefully. Somebody that understands programming logic and writing GAL code a little bit better than me. Please, if you do, come talk to me. All right, so the card worked in my 4000. I plugged it into a 3000 and it stopped working. And then we took the original card and Chris took it home and put it in his 3000. It worked like a charm, right? The original card works. What did we do wrong? So we went through the schematics again, measured again, went over it. Well, it wasn't any of that. At some point, I took all the gals off of the original card and put it in our cards, and the card started working in the 3000. So it was our chips that were the problem. Right? It's like, because we have the source code. Did we maybe compile the source code wrong, right? Or is it something with the chips? Are the chips bad? So I'm like, okay, no, we bought them from Mauser, so they're not probably cheap fakes or whatever. They should be working. A little glimpse at the data sheet will tell you that the Atmel parts have significantly shorter propagation times internally. And so one of the things that we learned is that the logic of this card does its timing implicitly through the propagation delays of the parts. And so if you use too fast parts, the card will just not work. That's still one. The solution to it was like to use a bunch of slower parts in certain positions. So 2 of the parts now have to be slow parts and all the others are fast parts. We got it working and it's reproducible, and we always test like all of the cards in both in the 3000 and the 4000. But it's not like, right. So that's definitely an open. Of course, I had to put this one in because Austria is pretty close to my homeland, Germany. We had, of course, like the design has under like the plate where the hard drive is mounted has a terminator that comes with it. It's an active terminator. There's not much magic to it. One of the things, like if you ever decide that you want to build one of these, the design is such that you have to Dremel out the PCB. Please Dremel carefully. Like you can destroy both of the boards if you do that. And make sure that you clean it. It makes a giant mess. Yeah, of course, end-to-end, right? I said that. Let's make some disks. And if you remember, like I said, the best picture that I found of all the collateral was that low resolution picture on Big Book of Amiga hardware. Well, there is no better picture of the disk than that, of the original. And so I was looking at this stuff, and I still haven't found any, so this is the best guess I could do. Actually, I know that on the original disk, as it is in the picture, this logo is not there, but it's on like the manual, and I decided to derive a little bit. It's not very accurate, but the disk right now with like Amiga OS 3.1, 3.2, whatever, you don't really need the disk anyways. Like we're developing, we put a little test utility for the card on there, like our so-called factory test, where you can test functionality of the card, like test the jumpers on the back and test throughput and test that the card is generally working. So we put that on there together with the original files. The original files are good if you want to use Amiga OS 3.0. But it's in the box. And then cables. Wow, cables. I did not think about that being a problem. And of course you can make your own cables, right? And it gets tedious pretty quickly if you're sitting there making 30 cables or whatever. So we try to figure out folks that would like make the right cables and the right size. And turns out speaking Chinese is a very big advantage if you express vendors. And so one of them actually did make these cables for us specifically. Yeah, and then like once we had the first boards working, we got a larger batch of 25, and so we started, right? And this time we got a stencil and components in reels now, not just like the little packages. And then Chris, this is Chris, that's me over there. That's my workstation. Chris brought his microscope. So that was another point of contention when I started putting basically 2 factory line stations in the garage. It's not necessarily the best to keep peace in the house. Certainly, one suggestion to all of you, be careful when you start talking about pick and place machines. Well, all that fun aside, while we were building this project, one of the fun things that happened too is we built a bunch of other stuff to make debugging or working with this easier, right? And so one thing is like the 28C256 EEPROMs are easier to get, they're cheaper, and they're reflashable without like having to have a ultraviolet light. So working on a driver, we decided that we're gonna like make a little adapter. Many people have built these adapters. I found out after I made one myself. But it's easy stuff. These are more interesting. They're like interposers for the gals, because as you could see on the pictures before, like attaching probes to the gals is a little bit painful if you have to do it on and off, and a lot of them. So these come like you can put either a PLCC socket on the bottom, then you can plug it on top of like a non-socketed chip, or you put a plug in the bottom, and then you put it in the socket, and then the original chip on top, and then you can connect your probes here. It's a lot easier. Other custom stuff. Simon, for us, he also designed these SCSI to SD carriers, so you can mount your SCSI to SD directly on the card. In this case, it's an original card where I tested it. And like if you want to go that route, like you can 3D print your slot brackets. At some point, when we open source the whole project, we'll put the STL files in there. It's okay, but they're fragile, so don't tear on them too much. another really cool thing, because we were like, hey, what if, right? Like the gals that are part of the card, the original card that I got, they were all protected. What if they changed stuff and it's not in the Haney files? How would we know? We can't read them. And they're PAL CEs, so the other reverse engineering options in the field didn't work with this one. So Chris decided to build a brute force PAL decoder, which analyzes. It actually doesn't only decode PALs, you can put any logic chips in there and it'll basically tell you what's in there. It's quite nifty. It needs a little bit more work for more complex stuff, but it was useful during the development process. And then some fun pictures here, actually. Like when I put the quartz, typically I would put like little pin headers through the holes and then put the quartz in, so I could ultrasonically clean the boards and take the oscillator out. On this board, I had completely forgotten, for some reason, to solder the 4 pins in. And because the fit was so tight on the first revision of the boards, the card just worked fine. And we found it later when we were like, wait a second, this still looks very golden and not as silvery as we anticipated when we were inspecting the boards. And then here, this is one of our attempts. There's around, I think, like 40-ish farad beads on this board. So if you start having to rework all of them, it's a little bit of a pain. Make sure that you check your parts numbers and get the right parts if you want to build something like this. Well, closing in on the end, the drivers, right? So there's a driver coming from Commodore. The latest released version, 40.13, works just fine on the board. We've seen in the wild copies of version 40.20, and then this guy in France, Cosmos Amiga, he published a patched version of 40.13 that fixes a couple of bugs. This guy's a genius. Like, he will binary patch all of the 30-year-old drivers, whatever. But for me, that's a little stressful to do. So looking is at drivers that are out there, right? There's some of the code will be written in assembler, and some is in C, and then there's this other thing, because the SCSI controller chip that's on the board is actually its own CPU, more or less, and it can run its own code. And that code needs to be compiled with the NCR script assembler. And it took, I don't know, probably a month to find an old copy of this. This was tricky. There's also various open source versions in the Linux kernel and in the BSD kernel. Both of them don't really work well. Well, the one in BSD is a lot better than the one in Linux. The original driver does not support NSD or TD64, so theoretically, no disks larger than 4 gig. Now with 3-to-1, you can switch that limitation off, and that works. But manual intervention is required there. Now, it's really unfortunate, right? 3-to-1 is out, and it supports the Amiga 4000T, which has exactly the same chip, except that chip is directly on the main board of the 4000T and not on the Zorro card. So whoever's working on that one could just recompile the latest version, and it would work great with all of these features that are missing from what's out there. But with the current situation of the Amiga community and the legal situation about the operating system source being unclear, I doubt that that is going to happen in the near future, at least. So what do you do? Well, I like this saying, if it's not open source, it's a waste of time, right? One of the reasons why we built this thing is because we want to make it available and we want people to be able to learn from this. So Chris, I started talking to Chris about this, and Chris is not one to listen and then not do anything. So he immediately started rewriting the driver based on existing NetBSD code. He is using a more modern driver design where he decouples like device partition table and handling in separate tasks in a way that basically like what happens in these old drivers, right, is that the partition table of the system needs to be parsed by every single storage driver. So there's a portion of code that's copied into each of these drivers. Now, our idea is we can split this out into a separate task and have the actual hardware driver talk to that task, more like a modern Linux or BSD system would do it. So if anybody's working on another storage controller, please talk to us and adopt this, because it will allow us to fix mistakes across the board and add support for other stuff like MS-DOS partitions and stuff, or UEFI partitions these days. Now, the driver supports large drives. The speed, we're not quite there yet. The original driver is 5.1 megabytes per second. This one is 4.2. We're catching up. We have to do some more work on this, but we're definitely getting there, right? Just to put, this is our factory test tool that Chris wrote, and you can see on the left side, there's like our driver now, and on the right side, there's the original Commodore driver. It's a little bit too small, but just to tell you, like a lot of this stuff is just like either implemented wrong in the original driver or it's not implemented at all. So we're trying to really modernize the whole thing. So, stop talking, right? Like, we want to see some hardware. So I have the hardware up here. You guys can come up and look at it or whatever. I'll also have a table in the exhibition. Please stop by, come talk to me. I did not bring my Amiga to actually plug it in and demonstrate it because that was just not doable overnight in the airplane from San Francisco. But the card is there, and I can definitely try to answer all of your questions. Yeah, and then the future, like what could we do, right? So one thing that is definitely going to happen next, we're going to open source the whole thing because that was the plan all along. We hope that people will be inspired by this, just as I was inspired by the work of Paul and John, and maybe people will start improving what's there or build their own or just glance at it and say like, hey, this is neat, glad it's out there, right? One of the things that would be really nice to have is support for Zoro 3 burst. That would, with a simple PAL upgrade, GAL upgrade, would improve the speed of the board by a factor of 2. It is unclear if any workarounds on a board would have to happen. So I saw in the original GAL code that Dave Haney published, there are traces of Zoro 3 burst mode in there. They have been replaced. I believe it was because of some issues on the 3000. I hope to find out more. If you know, please come and tell me. Of course, if one were to build future versions of the design, like get rid of those 8 different GALs, put them in one single larger CPLD, you'll save a lot of pins, you can make the board smaller. Or you leave the size the same and you add some RAM to it or something, right? So there's also folks working on open source RAM upgrades for Zoro 3. Together with something like the storage solution, this would be an ideal thing. You could directly DMA into the onboard RAM and get like much higher transfer speeds. Of course, with the open source driver that is also happening now, we could use more modern SCSI chips that could do So the 720 and 725 are still 6830 bus friendly. So they're easy to integrate. They're not pin compatible, but other than that, they're drop-in replacements, right? You gotta like cut the board in half, forget about mounting the SCSI hard drive to the board. I wouldn't recommend that particularly anyways, to be honest. But like in that case, like people have already asked me and say, hey, I could use this with a mediator, I could plug a PCI card in the end, and then the SCSI controller in the front, and that would work. It's definitely possible. We talked about it, it's unclear, probably we're not gonna do a whole lot of work on the hardware design after we open source it and just give it out to the community and see what happens. But there's a lot of ideas, and stuff like reducing the size of the board is not particularly hard or challenging, right? And then, well, whatever you would like to see, please grab the stuff, work on it, make it better. This is what this community is all about. And with those words, that's it. And if anybody has questions, please come find me later. Because I think I ran out of time already.
And you can pay them. Oh, I would pay my daughter like $15 per board, much cheaper than a real pick and place. Yeah, and they have very good eyes, and they can use the tweezers. Yeah, yeah. So, yeah, great talk, man. I enjoyed it. Yeah, thanks.
Well, thank you, thank you.
May I take some video of a close-up of the board and
Oh,
the
yes.
box and all that kind of stuff before you leave the parent? Oh, okay, here you go.
Outside so it lasts longer. Discs. Everybody wants floppy disks, of course. The noise dampening foam cutting for whole media. The Terminators. Silence mount for the SCSI to SD. That's also quite nice. Yeah. So we can try this again if you like. I'm gonna try and put this up like in a little nicer presentation. I was thinking about passing it around, but I kind of ran out of time.
What do you mean a nicer presentation?
Oh, like I have a table. Oh, so I'm gonna put it out and like then like show the bracket and whatnot. Thank you.
So you're testing right now, right?
Test, test, test. Yep. Any levels?
No, I think this one's taking off this computer right here. I think this is all wrong.
Test, test, test.
Is this good enough? No, that was not planned. Okay, does it sound? It sounds like something's working. Ooga booga. Ooga booga. Shall I just start anyways? Because it does sound. Okay. All right, despite the technical and the impromptu dance moves, I'm Rebecca Ann Heineman. I've been in the video game industry for the beginning of time. Many of you look like old enough to have been there at the time when we were using sticks for ones and rocks for zeros. But my career started off as a video game champion, which then led to people actually recognizing that I actually had skills, and I did a of 6502-based computers that were all the rage at the time, namely like the VIC-20, the Commodore 64, the Atari 400, 800 series, the Commodore PET. One of the reasons I got myself an Apple II was because the Commodore 64 didn't exist yet, and somebody was selling one on a it was called a penny saver. It was one of those little ads you open up, and it has, basically called Craigslist today. But someone was selling an Apple II for some reason for $600. And I'm like, what happened? Did you just fall off the truck or something? But it ended up that his company ordered a bunch, and he was just tasked with getting rid of them at whatever price that he sold them for, or he can get for it. So $600 later, I had an Apple II, which was essentially the sum total of my life savings at the time. But I managed to drag this thing home and started programming on it. The fun thing about the Apple II was that when it was created, it was designed from a circuit board that was supposed to be nothing more than a text terminal, the Apple I. Many of you have heard the Apple, but if you actually use an Apple I, you will find it really is nothing more than a glorified teletype. I mean, it had a text mode, but you couldn't even couldn't even write to the text mode. You actually had to write to a port, and a chip was used to generate text much like a teletype. Now it sounds, I can hear it better. But that basic idea and concept was then used to create a brand new computer, the Apple II, which had, of course, video graphics, text, and other modes such as that. Other computers were designed by people who were sane and didn't both look like a hippie and probably, smoked some serious drugs, because the hardware from the software perspective really was something that whoever designed this was on some seriously good drugs. Because on the Commodore 64, video is arranged pretty much linearly. You start your video graphics page at 0, 0, and you sequentially go through memory, and that is how, and just go sequentially, and that gets you to your text screen. Your video buffer, when you're doing graphics, is a little bit weird because you could see they were just using the text mode for fonts, because the graphics was 8 bytes solid vertically, then the next 8 bytes, the next 8 bytes. So if you were drawing a horizontal line, you just skipped every 8th byte to draw a line. So you get a base, draw a line, and every 8 lines you do the new base. The Atari 800 used a thing called the Antic, and can't remember the exact name of the system, but essentially it's a scan line display buffer, in which you just tell it, okay, I'm going to describe my screen saying, go to this memory address, draw some 160 pixels of graphics, go to the very next line. So when you create your screen buffer, it's again linear screen. And of course, both Commodore and Atari, when they did their bits for how you describe the graphics, 2 bits per pixel, great. Grab a byte. There's 4 groups of 2 bits. There's your color. Same. Now let's go to the Apple II. Yes, you start at the left of the screen, 0, 0. You draw 40 bytes. There's 40 bytes of graphics. And then if you go linearly, you go about, think of like 40 lines down, and then that's the next scan line when it comes to linear memory. I'm like, wait a minute. I don't just add 40 to get the next scan line. I have to go all the way down in memory to something like about 400 bytes hex ahead. And that's why whenever you see a video game on the Apple II that just fills the memory to blank the screen, it has this Venetian blind look. It's because the scan lines are not linear. They are interlaced, something like, if I think of like 8 groups. It's either 8 groups or 4, I think it was 8, but it's one of those things where, after 40 years, my memory is kind of a little But, okay, we can draw graphics on the Apple II by just simply drawing 40 lines of, let's say, FF to get some white, 0 to get some black, and using what we call a Y table, in which you just take the Y coordinate of your graphics you want. You go to this table of 16-bit values, which will tell you what the scan line actually is, use as your base address, and then you can draw that line. Okay, problem solved. Now let's go to that 2 bits per pixel. This is where a lot of Apple II programmers would realize, you know what, I should have stayed on the Atari. Instead of being 2 bits per pixel with 8 bits of graphics, no. It's 7 bits. What you do is that you have to do your graphics in 2 byte pairs. The first byte has 2 bits per pixel, fine. But then there's 1 bit left over, which is carried over to the very next byte. And then that is the remainder of the 2 bytes per pixel. And then you have 3 more 2 bits per pixel. So in other words, 2 bytes gets you 7 color pixels, not 8. Which is one reason why the resolution on the Apple II, instead of being 160 color pixels across, is 40. But what is that extra little bit there? What is it? Is it there because someone was insane? Magic 8 ball? Probably. Okay, got that. But waste not, want not. Steve Wozniak, the inventor of the Apple II, decided that why don't we just use that little bit to determine the color clock, and if that's clear, you leave the color clock alone. If you set it, you offset the color clock by half a clock. So in other words, instead of using 4 colors, which usually is black, orange, and blue, or it would be black, white, green, and like a purple, I think it was. So you could essentially choose 6 different colors, because black is always black and white is always white. So those 2 colors, you toss them in the garbage. But if you draw with, let's say, colors of blue, you now have to pattern them, because every single byte is either 1 or 2 palettes, except for that odd man out who's straddling the 2 palettes. And you have to deal with the fact that, okay, you have half a green pixel here, but now it's half a purple pixel over there. Especially when you have a character, let's say, I don't know, I'll just use something more contemporary, Mario, and you have him drawn in this orange color, because red didn't quite exist on the Apple, and having him run around, but as he's running around, he sometimes shifts in color because he's near something that's in the other palette, and you're drawing the 2 on top, which is one reason why in the Apple II there's a lot of little artifacting going on. So we have nonlinear graphics, we have 7 bits per pixel, and the fact is that if you run this on a black and white display, you're going to find out exactly how the colors were shifted. Because on black and white, there is no chroma whatsoever. What's going on is just taking the bits and just displaying them as is. But then you will, on images that have the high bit set, their bits are literally moved a half a bit. So therefore, when you draw graphics on the Apple II, and some places where it's supposed to be color, you'll see that they don't quite line up with the pixels. It's because it literally is a high resolution 280 pixels that's actually doing half shift, so it kind of pretends to be 560 pixels. So heaven help you if you want to draw, let's say, black and white text on a color monitor. This is the reason why you get all that color artifacting, because the hardware has no idea whether or not you're trying to draw text that's actually in color or in black and white. So when games are designed, like the original Apple II games like Space Invaders and Pong and Asteroids, which are all done for black and white monitors, you play them on a color monitor and all the images have this color artifacting. So these are all the things you have to deal with when drawing graphics on. So that's one reason why when you see games that I'm doing, or I've done back in the past, the fonts usually have very thick lines. It's only because I want to do 2 bits per pixel as much as I can to get past the color artifacting. And I have graphics that are usually set in specific spots, like Bard's Tale, so that therefore when they are drawn, I don't have to worry about the images being moved left or right. But for games like Mind Shadow and Tracer Sanction, which I actually have animations running in which they can move anywhere they're on, I do have to make certain, like let's say there's a shark fin and it moves around in Mind Shadow, and what I did is I made certain the background was all blue, so therefore when it draws it doesn't have to do the color artifacting. Well, this is we just got past graphics. You think the drugs stop there? Oh, hell no. Let's go to sound. On the Atari, they have this chip called the Antic and the TIA. I don't remember which chip it is specifically, but it had a beautiful sound synthesizer. You know, with you just set what waveform you want, you set what frequency you want, and after you set the registers, the sound's going, and then you can just go on and do other pieces of code. And then, secondly, the Atari 800 has interrupts. So you can actually write an interrupt driver that runs 60 times a second, so it can play the music and sound effects without the main game code even happening, and with minimal use of the CPU time. Commodore, they obviously followed Atari's lead, and they came out with the SID chip, which was, again, beautiful sound. You just go ahead and set what waveforms you want. And the Apple II, you have a single I/O register, C030. What do you do with it? You access it, and then it causes a speaker to move in. You access it again. It causes the speaker to move out. I have just explained the sum total of Apple II sound. Literally, that is Apple II sound. Now, of course, they redeemed themselves many years later with the Apple II GS, but I'm going to stick with the Apple II right now only because I want to make all of you go psychotic. So, with the Apple II, Steve Wozniak, for whatever reason, decided not to add a 555 timer or some sort of countdown chip and an interrupt. So therefore, not only do I have to tick the speaker and tick it again and do so for every single iteration of a beep I want to make, I do not even have an interrupt driver, so therefore I cannot do music per se, because the main code has to stop, loop to make a tone, but then as soon as it goes back to the main code, sound stops. Because nobody's there sitting there like a, what is it called, a railroad handcart, you know, trying to get the sound to keep going. This is where games like Borrowed Time, Task Times and Tone, Borrowed Time and so forth, the music in there was basically just a couple of tones, and then the game progresses, and occasionally when there is a sound effect, you will notice that the game stops momentarily. Because on the Apple II, you literally have to say, to make a sound effect, I say, this is the loop, this is how, you know, I tick the speaker, I sit in a little idle loop for X amount of time, then I tick the speaker again, and based on that amount of time I do between ticks will determine what tone I play. And then, of course, if you have, let's say, a sound effect like static or doo, like that, you actually have to have your code change the delay it is between the ticks. So anybody who does anything more than beep is going to have to do a lot of gymnastics in order to be able to play sound on the Apple II. Well, this is where I read a lot of white papers and stuff, because on Bard's Tale 3, I did not want the music in the game to be nothing more than beeps and bops that every time it happened, it would cause the monster animations to freeze for a little bit. So, learning what MFM and frequency modulations and so forth, I was able to get 2 sounds out of the Apple II, in which I created a carrier wave that was about 30 kilohertz, and then on that, I would have 2 different tones in which I would then be changing the, I would do the frequency, but every now and then I would pause for a little bit and then reverse the frequency. And I would do that based on 2 tones simultaneously, in which when you listened to Bard's Tale 3, you actually heard chords. And you're like, wait a minute, this music is not 1 sound, it's actually 2. And that's because when you take 2 frequencies and you add them together, you get this 3rd frequency, apply it to a carrier wave, and it's called FM radio. So, effectively, using an FM frequency, which is in this case 30 kilohertz, because that's the fastest I can go on a 1 megahertz Apple II, you're able to do 2 tones. One of these days I'm going to be getting around to uploading the source code to Bard's Tale 3 to GitHub or something like that, and you can then see how the sound was done. Now, just to let you know, I wasn't the first one to do it. There was actually something called Music Tracker that was done like 2 or 3 years beforehand, and they did the same technique. I just listened to it, go like, okay, challenge accepted. But this doesn't still solve the problem of interrupts, because you see, this is all based on hardware timing and accepting the fact that the Apple II you ran at exactly 1 megahertz. So therefore, if you ran with an accelerator or with a Apple II GS, or later on the 4 megahertz Apple IIc, the sounds would be 4 times higher in frequency. In those particular cases, that's where you have to, if you want to hear the sound the way it was meant to be heard, you have to turn the accelerator off before playing the game. Now, let's go on to the development environment. This is where the Apple II actually doesn't suck. And this is the main reason why I was attracted to the Apple II in the first place, other than the fact that one fell off a truck into my pocket for $600, was slots. Unlike the Atari and the Commodore, which were designed to be all-in-one computers, the Apple II was intended for you to lift the lid off and plug some cards in there. And of course, the circuitry to plug the cards in was simplicity itself. On the Apple II, the way the memory map works is from memory location 0 to BFFF was just RAM. C1000 to CFFF is the hardware memory locations. D1000 up is ROM. Can be switched for RAM, but that's another story. In the Apple II, location C1000 through C0FF is the hardware register. Actually, no, C0 through C07F is the hardware registers. This is what controls the Apple II and all of its behavior, etc. But then you have C080 through C08F, C090, C09F. These are 8 groups of 16 registers that don't exist. They actually exist on the peripheral cards, and there's an actual select line, 1 individual to each one of the peripheral cards. So therefore, if you put a card in slot 1, and it just looks for that 1 line, then anytime memory location C090 through C09F is accessed, all the card has to do is say, oh, this line got pulled, check the lower 4 bits of the address line, and put up whatever register that I feel like putting up there to implement my card. Then we do it again for memory location C100 through C7FF, in which C1 is slot 1, C2 slot 2, C3 slot 3, etc. There's another line, gets pulled down, and it just says, hey, you got a 256-byte ROM? Enable it, put the lower 8 bits on the bus to figure out which byte you want. There's your ROM. And then, finally, at C0800 through CFFF is shared ROM memory, in which there, all cards can put a 2K ROM in there, but if you access memory location CFFF, you're supposed to relinquish control. So hit your card, C090, it tells the card, oh, I have control. Now, if I go to C800, there's 2K ROM for whatever the card is, if the card supports it. Why are you even bothering with this? Because when I got my Apple II, I liked Atari 2600 games. But unfortunately for me, I couldn't afford Atari 2600 games because I spent all my money to this guy who basically gave me a computer from the back of a truck. So, I, like any other enterprising individual, would go onto the bulletin boards, or, in my case, the actual Apple II manual that came with my Apple II, which had the schematic for what was called the Apple II integer card. This card was just a ROM card that plugged into one of the slots of the Apple II. Well, all it takes is saying, if I just add a read-write line to the ROMs, I could put in RAM chips in there. If I put in a 74LS245, I could make a buffer, and then if I have a flip-flop, I can make two buffers. One goes to the Apple II, and the other one goes to this funny little cable, which goes over to a little combat cartridge that I remove the ROM from and put in this cable. And then at that point, using another cable, I could plug it into a cartridge into it and read it, all based on the schematic of the Apple II integer card. This allowed me to copy Atari 2600 cartridges. So once I downloaded these cartridges and put them into RAM, I would then be able to put them on this modified integer card. It actually is a card I wire wrapped from parts at Radio Shack, may they rest in peace. The place where, like Fry's Electronics, may they rest in peace, where they would have wire wrap tools and sockets and chips. Man, those are the days. But was able to build my own little Apple II card, all wire wrapped. It's now sitting in the Video Game History Museum in Frisco, Texas, if you ever want to see it. But with this, I was able to download all the cartridges, put them up on the Atari cartridges, this fake combat cartridge, and I was able to basically copy every single cartridge there was. But I wasn't going to stop there. You see, the Apple II, those of you who know will know what call -151 is. That is the command that when you turn your Apple II and your Apple II Basic, it will take you into what's called the monitor. It is a command prompt that is connected to a little tiny BIOS who has a disassembler. This is where it gets some coding here. The disassembler allows you to just simply look at memory in the Apple II, either through a memory dump, or disassembles the opcodes into actual 6502 code. Funny thing about Atari cartridges, they're legible because they were also written in 6502. So, by looking at the 6502 code, looking at using the Apple II disassembler, I was able to learn how to program the Atari 2600. But then, I thought, you know what, why don't I actually start making games in the Apple II? So when you're making games on the Apple II, now to explain to you the wonders, that is the video graphics system, the wonders of the audio system, and the fact that every other platform out there was far, far superior, yet I was seeing games out there like Serpentine and Space Invaders and so forth on the Apple II, and they were all going like, I could do that. So there was this game that I saw back in 1979, I think it was called Mission Asteroid from Sierra. Now, Mission Asteroid is just basically one of the first graphic text adventures. The text adventures are not new. I mean, Zork predates it, and then Scott Adams' Adventures predates that. But I saw that this game was using just draw commands and in order to draw the art, so you can have dozens of pictures on a floppy disk, which, 140 KSI, come on, winner. So you can take a 2K, sorry, was it 2K? Let's see, it's from 4K to, so it's about, yeah, it's about too much, but it was 8K. You have a video picture, which is about 8K memory, but you need to be able to compress it. Well, all the compression algorithms, the best ones even out there, will only get half the space. But if you just simply store the draw commands, you can only have maybe anywhere from 100 bytes to 500 bytes to just to describe a picture. So, how to do this? How to duplicate that? Well, I just went ahead and created my own little graphics programming language, which would just say, a byte would say draw command 0, followed by the x coordinate of where to start the line, the x and y coordinate where to end the line, and then I would have another command saying pen color, so that would just say, okay, draw in black or draw in white. Then there would be another command for drawing a circle, which would then give me the origin and radius. But to do this required some interesting techniques in programming the Apple II. The Apple II only runs at 1 megahertz. The 6502 takes a minimum of 2 clocks per instruction. So even no-op, increment X, so forth, they all take 2 clocks. So effectively, your maximum throughput is 500,000 instructions per second. So how do you improve upon these speeds? On the Apple II, many of the instructions would be such as like load A, that a 16-bit address, comma Y. And that's hard-coded, and the address, of course, is hard-coded in the instruction. Then there would be instructions like load A with a 0-page location, which would have the pointer, and then you index it by Y. The problem with that instruction is it takes 6 clocks. 2 clocks for the instruction itself, another clock for the actual byte that for the 0-page address, 2 more clocks to go to 0-page to get the address, and then another clock to read or write the memory. And of course, if that happens to cross a page boundary, it's an extra clock that's just thrown in for fun. So this one instruction could take 6 clocks in order to read or write a byte of memory somewhere in space if you want to go ahead and have this one little piece of really brilliant code that would read memory from a graphic, write it to the screen, and repeat and fill. Well, there's a problem with this. And the main issue is the fact that this really slows down your ability to draw. Now, back then, computers had nothing like multitasking, multi-threading, so then therefore, there is no reason why anyone would have to worry about what's called self-modifying code. So, many of my routines, what they would do is that when I generate the address of where I was going to draw my art, instead of actually storing it in a direct page or 0-page location, and then using one generic piece of code to do the draw, instead I would actually modify the instructions ahead so that they would then say, okay, instead of being load A at 4,000 hex, comma Y, it now becomes load A with 5,000 hex, comma Y. And same goes for the destination. I would change that one too, because that instruction, load A 4000X, takes 3 clocks to read the instruction, the instruction itself, the 2 bytes for the address, and then the fourth axis is the read or write itself. So instead of going from a maximum of 6 clocks, I knocked it down to 4 clocks. But there are ways of doing this even better. There's techniques I use in the 2GS, which I actually fold the graphics page to the stack. And I just use push effective address or push A and write memory in there. But those are only available on the 65816. On the 6502, self-modifying code was one of the things. But then there was another technique which I used on some pieces of code or pieces of the game in which I had a lot of space. And this is what was called compiled sprites. As you can imagine, when you're wanting to draw a sprite on the screen, you have in memory the actual bits of the sprite, and then just reads from the sprite and writes it to the screen. Well, what if you could say the sprite is aligned with bytes on the screen, so you never have to shift, and you also know that the sprite is never ever going to clip any of the screen boundaries. Now, if you could guarantee that, like I was able to do in some animations in Task Times in Tone Town and in Tracer Sanction, what you do now is you actually generate a piece of code. In this case, I use a small script in BASIC to create it, and then I use the assembler to assemble it. But what the code does is load A with the first byte of the shape, 2 clocks, instead of load A, go through a pointer, index by Y, go here. No, it's load A with that. Then, let's just say the shape is like a rectangle with some little X's, or corners cut off. Well, what happens if maybe about 20 bytes of the shape is the same value? It's all FF. So now the code would say, load A with FF, store, all indexed by Y, with each store being offset as to where it would be on the screen based on the Y coordinate. And then I would load A with the next version of the shape, or in some cases, let's say the next byte is 7F, I would actually generate an instruction, arithmetic shift left, which turns the FF into 7F with one instruction, 1 byte, still 2 clocks. And then do store again. This technique I use for both fonts, and I used it also for some specialized graphics in which I knew that the Venetian light effect wouldn't come into play, but it would allow me to draw these shapes at unheard of speeds, and allowed me to focus on draw the art as fast as possible, then play a little bit of sound, draw some more art as fast as possible, play a little sound, so that now when you're playing Bard's Tale 3, you would be wondering, how in the world am I drawing this art and still playing sound at the same time? The technique of using compiled shapes was how I did the fonts on Bard's Tale 3. So therefore, and what's funny is in some cases, the code was actually smaller than the font itself because of the fact that I had the ability to read one value and just write, and not have to read another value at all. So it cut the speed of the draw in about half. Other techniques that I used, let's see here, the good ones. Oh yes, the disk drive. Let's go there. On the Apple II, the beauty of the disk drive is that it is directly tied to the hardware and the bus. The drive itself is completely software controlled, in which stepping the head, reading from the shift register, and so forth, those are all software controlled, which allowed people to create some very, very creative copy protection schemes on the Apple II. C64 and the Atari 800 were actually way ahead of their time, because today we all use USB drives and no one thinks anything of it. But back then, their disk drives actually had CPUs, RAM, ROM, everything in it, and you communicated with them serially. So therefore, it's one of the reasons why Commodore 64 and Atari 800 disks tend to be a lot slower than Apple II. And secondly, the options for copy protection are extremely limited, which is one reason why a game like Mule, one of the most top-rated Atari 800 games ever, for floppy, only sold a few thousand copies because of the just rampant piracy. But on the Apple II, remember I told you 140K on the side of a floppy? We can do better. The way it happens is that on the Apple II floppy drive, the way it's supposed to be is when you write out an entire track on the disk, you're supposed to first turn on the write head, first let the head settle, get to the appropriate place, turn on the write head, and then you write D5AA96 and some information to determine to say, this is sector 0, an epilogue, then you wait a little bit, and then you write a D5EEAD, and then you write the actual data, and then you're done. Because of the fact that these are done by precise timings, that is, you have to read if you want to modify just one sector, you have to wait for the sector previously to move by. As soon as you can read the sector, read the epilogue, knowing the head's going by, you have to wait a few microseconds, and then after that, turn on the write head, write out the sector data, and because of drive variance speeds, you have to have some wiggle room between sectors. Well, what if we could use that wiggle room? Some of you have heard of a technique called 18-track sector, or 18-sector tracks. This is a technique in which what you do is that you just clear out the track, first turn on the write head, clear the entire track, and then you write a single group of source bytes saying, hey, this is D5AA96, or whatever numbers you want, and then you follow it with 18 sectors worth of data consecutively, no breaks. So then once the entire track comes in, because there's enough space in there for 18 tracks, 256 byte sectors, if you do not have any space between adjacent sectors in order to handle the ability to arbitrarily read and write sectors on the fly. And of course, you know, when you're shipping a game, the game is hardwired, hard-coded, so you're never supposed to be modifying the sectors. So what the heck? So what will happen then is that you go ahead and create the epilogue, and then you just write 18, and therefore you will also know that when you make the head revolve around just once, you read the entire track, which, you know, when you're running at 300 RPMs, you know, you can read an entire track's worth of data in 1/300th of a second, which on the Apple II, due to the way interleaving works, you really technically have to have 4 revolutions to read an entire track. Because the way it works is that it's sector 0, then sector 4, then sector 8, then sector 12, then it goes to sector 1, so forth, and that's how the sectors are actually mapped on the disk, because that way you would read in sector 0, then you take some CPU time to munch on it and digest it, and then by the time you're done and you want to read the next sector, the floppy already puts the sector 1 should be coming up, but it's still going to take 4 revolutions to get the entire data. Well, when I presented this idea to Activision for Mind Shadow to do the single sector track, their first reaction was, that's a great copy protection. Too bad none of our vendors can actually duplicate that. So I contacted the vendors and wrote the software for them to modify their drives and stuff like that so they can actually write and duplicate these types of sectors and so forth. Now, for Mind Shadow and Tracer Sanction, we actually never did use that particular scheme, but I had a side business where I was going to duplication houses and selling them different copy protections. So I'd say about maybe a quarter to maybe a third of copy protection disks probably have my fingerprints on it, whether or not I actually had any direct involvement, because it was a turnkey system. Basically, is you give them your unprotected disk, you apply my software to it, they then use their disk duplicators, and that's the reason why a lot of copy protection schemes look the same, because it literally is mass-produced. But undeterred, how in the world can I still read an entire track in 1 revolution, but have to deal with the fact that the tracks are formatted the right way? That's where I came up with a technique where I wrote my own read-write track sector. Now, on the Apple II, RWTS, read-write track sector, is a piece of code whose job it is to go move the head to the certain track, read in the sector, give you the data, but of course, the post-processing was what took the time, which is what limited you to reading a track in 4 revolutions. Well, I look at the algorithm, and I saw that the algorithm was taking what they called, again, I may be off on some of these specifics, but it was GCR encoding, in which I believe it was 4 bits to 3, or is it 5 bits to 4? It takes this 8 bits of GCR data. The first bit is garbage because it's just a clock bit, but then the other 7 bits, you then apply it to a table, which will then tell you exactly what the real bytes are, and you store it into a buffer. What the original Apple II read-write track sector did was it read in about 300 and some odd bytes into a buffer, then it ran this algorithm on the buffer to turn it into 256 real bytes, and then gave it to you. Well, by using 3 different lookup tables interleaved with the code that read in the actual hardware registers of the disk drive, and using self-modifying code, because instead of the Apple II's code, which would be saying load A with a memory address and then you know, it would take 6 clocks to read, mine was load A with C068C, comma X, and C0, and of course I would be modifying that 8C to be exactly what slot slot it was in. So in some cases, it was just load A was C08C, C0, you know, it was all those registers were direct. So I didn't even have the index by X register, which is necessary because I needed that X register, because as soon as I would read it, I would be load X with the value that I read from the floppy drive. Index it into this table. Pull up the value. Get the next value from the disk drive. Now, of course, 32 cycles apart, because there's some very, very strict timing. It's 32 cycles between each byte being read from the floppy disk. I would then read in the next byte, get the next thing. Once I think it was patterns of 4. After I read in 4, was it 3 or 4? I don't remember exactly specific, but I would read in the 3 or 4 bytes, use the lookup tables, and it would actually generate me 2 real values, and I would store it directly in the resulting table. So as a result, by the time I had finished just reading the 300 and some odd bytes from the floppy disk, I already had the decoded data. There was no pass where I had to go in and read in the data, then go in and use an algorithm to convert it into the real bytes. It was done all at once. So therefore, what I would do is I'd move the head to a track, then whatever sector came by, let's say sector 4. Okay, sector 4 comes in. I would then set the destination pointer to where the 4th entry of where I was going to put to. I would then read in that sector, decode it immediately. Then whatever the next sector was, oh, it's sector 8. I'll put it in location 2800. Read in the sector, go to the next one, to C100. And of course, because it was arbitrary, as soon as I had 16 sectors read, I just counted. As soon as a sector came in, I counted. Okay, as soon as all 16 sectors were counted, I would then verify, did I actually read one of every sector, which the answer was yes. Because if the answer was no, I had a read error and had to do it again. But with this, when you played Mind Shadow, when you booted it up, it booted the entire game in 3 seconds. Because it literally was, the delay was how long it took for the head to move from track to track. Because I would just boot the game, 256 bytes from the boot block, which would have a piece of my little code, reads in my read-write track sector, which is another 8 blocks. After that was done, then the code would just say, okay, move to this track, read the entire track. Just move the track, and after every revolution, so since I was doing it once every 300ths of a second, and it took about a quarter to a half revolution to move the head from one track to the other, I was able to read in about 40K of data in approximately 3 or 4 seconds. It was like when the game boots, you could see the graphics, and this was the technique I used because it was a way to optimize how to read in the data, convert it from GCR to actual bytes, and do it at the speed of the drive as the data was coming in. Later on, I used this very similar technique when I did a game called Borrowed Time for the Commodore 64, because in that case, I uploaded code into the Commodore 64's disk drive, which, by the way, is also 6502, fancy that. And I actually had the same types of buffers in there, which I would read the track in one revolution, and then I would have a high-speed serial communication, not the Commodore's communication. I had my own, which then loaded the data into the Commodore 64 memory as quickly as possible. With this, it was allowed me to create, my game Borrowed Time, Task Times, and Tone Time, which the loader was going very, very fast. And people loved it. In fact, people were thinking like, wait a minute, is this a cartridge game or is it a floppy game? No, it's definitely floppy. But these are all the techniques that were used there in order to speed up the disk drive. Fun fact, when I told you I was doing hardware tinkering, I didn't stop there. In order to test the 1541 modified card code, I made a card on the Apple II with a 6522 VIA, which basically is a duplicate of what was in the Commodore 64, and I plugged my 1541 too. And I was using my Apple II to actually write the code, upload it to 5041, debug it, test it, and so forth. So by the time it was actually running on the Commodore 64 it ran the first time because all the code was developed, hundreds of iterations were all done on an Apple II. That card also is sitting in the the Video Game History Museum. But of course, I didn't stop there. Those of you who are curious, if you have a copy of Task Times in Tone Town for the Commodore 64, go into it with a sector editor. If you do so, you will find that there is a catalog on track 13, which is the directory where the Apple II stores its directories. Because, actually, no, take it back, it's the other way around. The Apple II ProDOS stores its directories on track 0. The Commodore puts its directories on track 13. So on track 13, I had a fake Commodore 64 directory and everything. So if you put it into a drive and you type in directory, it'll say tasks and system.prodos and stuff like that. But if you actually went to track 0, there's a ProDOS directory because I actually wrote an Apple II driver that used that serial card to be able to read and write sectors as a ProDOS disk. So therefore, on my Apple II, when I developed a version of Task Times in Tone Town, it was drives just mounted on my computer, and I just simply copied the files with just file copy, except it was using the 1541's communication protocol to read and write the sectors. But it was an actual ProDOS disk, ProDOS file system, ProDOS everything, and I wrote a little mini ProDOS, in which what it does is that when Commodore 64, we put the disk in for it says ProDOS or task.system. It's actually ProDOS. You put it in there, and it goes through the ProDOS boot system, and it boots that floppy as if it was an Apple II. And it ran the game. And the game thought it was running on an Apple II, except, of course, with a completely different video driver. But the final question here is really, why the hell did I do this? Why in the hell did I go through all this trouble to use the Apple II as my host machine? I wasn't the only person out there making peripherals for the Apple II. Titan Technologies created the 3.6 megahertz Apple II accelerator, which on it had 64 of memory. This board was packed with chips on it. But I put this thing in my Apple II, and I was running at 3.6 megahertz, which meant compiling code on Merlin was a breeze. Then, of course, came the Axlon RAM disk. This is something, of course, I still have one left, but of course its battery's long dead. But what it is, it's a RAM disk. On it, it had 320K of glorious memory, a battery-backed up RAM, and a controller that read the memory into my system as fast as possible with a special driver that made it appear to me as a floppy disk. Because that's how I was working with DOS 3.3 before I moved to ProDOS. Because most of my original development was under DOS 3.3 on the Apple II. With this development environment, an Axlon RAM disk, a 3.6 megahertz CPU, it took me only seconds to do a build of any of my games. So I would write the code all in assembly, get everything, hit build. It would then use the RAM disk for reading and writing files, which means what the hell is a track delay? What the hell is a propagation? Whatever, it just was instant. And then once the code was built, then I would use either the serial drive or I'd just be running on the Apple II, and I would test the code. With this rapid iteration was one of the reasons why I was able to write so many games in such a short amount of time. Because if you look at my career, I've got my name on about 250 titles. And when you divide this out to my career, it's wait a minute, that's one every 6 weeks. And, well, I was churning out a game or port every 3 weeks. And it was because this Apple II with an Axlon RAM disk in one slot, a Titan 3.6 megahertz accelerator in another slot, and either a Commodore 64 disk drive controller that I built or an Atari 2600 ROM emulator, which I also used for ROM emulation on the Commodore 64 in another slot. It gave me the equivalent of what you all call the PC Master Race deck that people these days are bragging about, saying, ooh, I got a Threadripper, I've got all these wonderful bells and whistles. Well, technically, that's what I had, except this was the year 1980. I only have 10 minutes left, so if there's anybody who has any questions, I can go ahead and do it before I go ahead and do another Burger Time rant. All right, what can I waste another 9 minutes left? Oh, wait. Oh, yes, you.
The best
Red Robin Bonsai Burger. Yeah, Red Robin. No, you can still, no, that one's a burger. Now, I will share you with another secret. Go to Red Robin, order it to go, take it home, find a nice desk drawer, put it inside, keep it in the plastic paper bag because it absorbs any moisture, leave it in there. 72 hours, precisely. After 72 hours, peak of flavor. Very fermented. And then, of course, to add it better, just before you decide, you know, around the 73rd hour, run down to McDonald's, get an order of fries. Come back, fries, burger. Bon appetit. It also allows me to be as immune to pretty much every virus and disease known to man because I think every single virus and disease is already partied down in my body. So take for what you will. Huh? Yeah, I mean, that desk has seen things. If it could talk, it'd probably just scream nonstop. And yes, you. Friends of mine who took shrooms. That's an interesting story. Task Times in Tone Town was created by Mike and Muffy Berlin. Now, you may, at least the story, I created the game engine and everything, and I worked with them extensively saying, no, you can do that, yes, you can do that, no, you can do this. So I was just as much a creator, which is technically is my game. But essentially, my best tagline to it is, it's the closest thing to a drug trip without actually taking drugs. But the whole point of the game was just basically, I wanted a game with a story that was so off the wall, so crazy, so stupid, that people will just be flocking to it solely because it's not another, oh, the princess is in the castle, go through the quest. I mean, yeah, King's Quest has made a lot of copies of it, but you know, it gets old after a while. And of course, with Task Times in Tone Town, people would look at the box and go like, Task Times in Tone Town, what the heck is that? And of course, it got people to pull the box off the shelf and look at it. And of course, the thing that really helped Task Times in Tone Town was when I was developing it, Apple was 1985. Apple was creating this brand new machine codenamed Cortland, which, so as you would know, is the Apple IIgs. And since they already knew I was an insane Apple II programmer who was making games like crazy, Apple was able to give me one of the prototypes, to which I ran chordling with a friend of mine, Russell Lieblich, may he rest in peace, to create that opening soundtrack, which is when you play the 2GS version, it goes do-do-do-do-do. Now, we had that same song on the Commodore 64 and the Apple II, but you know, when somebody said, here's an actual synthesizer chip, do you think I was not going to go ahead and molest it? And as a result, it became one of the top-selling games on the Apple IIgs ever, because when the Apple IIgs finally did hit the store shelves, it was running Task Times in Tone Town, and it was running the music soundtrack, and people were going like, a computer can make music like this? It put the Amiga to shame. And remember, in 1986, people were all talking about trackers and stuff on the Amiga and saying how the Amiga is far, far better than the Apple II will ever be. And now this thing called the 2GS shows up and kicks the Amiga's ass. And subsequently, when I did Bard's Tale 1 and 2 for the Apple IIgs, you can hear the polyphonic soundtracks and so forth. I mean, it literally was taken from what I learned from the programming in Sonic MT32. No, ESQ1 was the ESQ1. It's the Roland was the MT32. But I actually learned how the ESQ1 worked with the people over in Sonic, to telling me all the dark secrets, which I, of course, applied to programming the Apple IIgs version of Task Times in Tone Town. But yeah, interrupts are great. Please, why didn't he put interrupts in 1970? I could have done so much. Anybody else? Because I'm about ready to be kicked off this stage. Any last minute questions? Oh, yes, we have a question over here. Volunteer?
So for the, let's see, for the GCR decoding,
Yes.
the high-speed stuff, did you end up, was that sort of one loop per byte, or did you have to unroll it since it's, I think it's 6.2 is the
It might have been 6.2. Again, it's one of those things where the specifics are something that I haven't even thought about for 20 years, so the little details there. But what it is that there was like 3 or 4 different states of the byte, because it's basically there was 3 bytes or 4 bytes. I don't remember specifically, but each one is a different grouping of GCR to actual bytes, and it was literally 6 bytes it decoded into, or 6 bits it decoded into. So I think it was 4 to 3. But what happens is that I would have 4 tables. So I would read in the nibble that came in, looked it up in the table, and the table would give me the actual 6 bits that are decoded, pre-shifted to where it's supposed to go. And I would read in the values, and of course with some extra clocks, because I don't need 32 clocks just to read in and do a lookup table, but I would then do some pre-shifting. I would then get the other bytes shifted out. So like if it's already pre-shifted, I would just read the byte and store it in a temp or just keep it in a register. The other one I would read in the next nibble or in with a different table, but it was all designed so that it would take no more than, read in at 32 clocks, it would take 128 clocks, but in at 128 clocks precisely, I would read in the 4 bytes, output the 3 true bytes, and then we do this all over again. And it's what allowed me to read a track in 1 revolution. I do have the code to that game, and it is my intention, I'm going to be just letting everybody here in the Federation know, that I am planning over the next couple of months going through my Apple II collection and posting it up on GitHub for everyone to see. And since I have 2 minutes, I just have time for one more question before I'm given the hook. Who wants to be my volunteer? Well, I already gave you my burger recipe, so there you go. All right. Well, thank you very much for having me over, and I hope to see you again next year. And, and of course, follow me on Twitter, Burger Becky. Follow me on Discord, Burger Becky. I have a YouTube channel called Burger Time, where I do basically these rants whenever I feel like it. And again, Burger Becky, just follow it on every one of the social medias. So thank you. Lost Technology, I recognize that shirt. Oh God, yes.
I don't know, management underestimates. I have a lot, I don't know if you want to, up to, I don't know.
It's your fault.
Where do you go with one?
Where do you want? Fun fact, I actually got my previous desk working again.
Oh, did you?
Yep. So when I finally decided to retire, this is one of the things I want to revisit.
Oh, yeah?
Except, of course, without the PTSD. Yes.
When you got your name badge, Corey asked you to sign.
6 of them. He's got 6 of them.
Signed 6, okay.
Yes. Yeah, I think we want to buy my name badge.
I don't know why he only did 6. If you have time sometime, you can sign the rest of them. We have probably 20.
Sure.
I didn't bring them with me, or I would've
Oh,
just
I'll go there because I always want to watch 1 or 2 more
I
talks.
lost one of my Sharpies.
No problem. Oh, I'm more than happy to help out and just sign them all for you.
Very much.
Yep.
Is this my, oh, yes, never mind, thank you.
Check, 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 check.
Bill Hurd, please report to the stage. Bill Hurd, please report to the stage.
It's a software problem. Yeah. Well, that's who fixes all our problems for software. That's right.
2 minutes.
Can I get a bottle of water? Yeah, excellent.
Great idea.
Actually, it's 3? Yep. Oh, the lights.
Yeah, it's a little strong. Yeah, you're gonna be quizzed. Yeah. Turn my phone off. Is probably a good idea. Yeah. Yeah. No, that's the important thing.
All right. Are we good? Hello, I am very honored and pleased to introduce the lead designer of the Commodore 128 and designer of the TED series, and a very good friend to VCF, Bill Hurd. And I believe for the first time in person, a gentleman that Bill has mentioned many times in his talks, a chip designer at Commodore and entrepreneur, Al Charpentier. Now I just screwed it up. Charpentier. And the topic, the Commodore VIC-1 and VIC-2 chips. And thank you very much, guys.
And with us is Professor Stephen Edwards from Columbia, right?
Yeah, long time lover of 6502 and all things 8-bit.
Right. And we'll forgive the fact that you see beauty in apples.
What are apples? I have no idea what
it's a 6502 based system.
I've heard of that.
That's the beauty of it. Yes.
Yeah, that's the beauty of it. Absolutely. Yeah. So my goal here was to set the stage a little bit. I have oodles of technical questions for you, but let's see. Come on, there it is. Okay. So spin your minds back a little bit. 1977. This was the Trinity that came out. We've got the PET, the Apple II, and the TRS-80, later called Model 1 or whatever. So the TRS-80, pure black and white, character mode display. It had one trick, which you had a bunch of characters that had, let's see, I think it was essentially 6 pixels each, and so that you could get like dancing demons and things like that. It was a bit primitive. The Apple II, this evil thing. If you heard Burger Becky's talk, the color was actually quite deliberate. But a very interesting, it's essentially what happens if you send frequencies at the NTSC color burst frequency. So the trick here is that that actually had color, and it was a nifty thing and so forth, but brutally difficult to program. And then the PET had this wonderful PETSCI font built into it that you could do all kinds of crazy things. But again, it was sort of a character-based thing.
We called the Apple an artifact generator because of the way the color was generated. As you said, based on the interference with the frequency of the color burst.
Yeah. No, it's when a frequency beats with an amore.
Yeah, that's amore.
It's funny. When the VIC-20 came out, and we were actually before the VIC-20 is when the VIC chip, and we were trying to sell it as a video game. Jobs and Wozniak came around and were quizzing me. How did we do color on the VIC-20?
Oh yes.
Because
this is what I want to talk about. Right. So tell us how the VIC-1 chip came about. Like you say, it did not start as the heart of the of the VIC.
Well, you didn't start as a VIC chip designer either. You
No.
started as a ROM designer.
I was a memory chip designer.
Memory
I did
chip.
ROMs and RAMs and calculator chips.
Right.
Okay.
Because Commodore was big on calculators.
They were the biggest, one of the biggest sellers of calculator chips. I started there in '75, and they were a calculator chip company. And their biggest customer was Commodore.
Right.
Commodore calculators were really big in Europe. So they were buying all the chips from them. And so at the same time, I always was interested in video, okay? Even from...
Video was cool.
Video is so cool.
Video
Yeah.
is cool.
Yeah, I mean, I remember waking up and I was 7 or 8 years old, looking at the test pattern at 5 o'clock in the morning going,
Yes,
how did that get there?
Yes.
So it was always fascinating to me, and it's, even though I designed ROMs and RAMs, since that was where somebody was paying me to do that, video games was one of the areas I'd love to figure out how to work with, in video particularly. So I did some ROMs for Atari. I remember the old Asteroid games. I had done a 64K ROM at one point, but the old Atari 2600 only had a 32K memory space. So they couldn't fit Asteroids into the ROM. So I said, wait a minute, I can make a bank switch that if they click a certain address, will flip over to another 32K. So
And you have to be careful with that because that's a read access.
that's a read access.
Right, so that's like a landmine with a pin already.
Yes,
type
it
thing, yeah.
really, and you had to be very careful that you didn't have any spikes or anything that was going on in there.
Right.
But at any rate, we put this in, and Atari went, yes, we can make this work. So they put the Asteroids game into it and made bazillion asteroid chips.
Did you actually put the bank switch logic into the ROM chip
Yes,
itself? So that's
correct.
just a single chip?
Yeah,
Okay.
so it was no different than any other cartridge they had.
Sure,
They just had to basically, as they
Electrically,
needed to
yeah,
change
yeah.
back and forth. And so they would wait for the vertical syncing time to be able to flip what they were going to do from one frame to the next. So that was the concept that there. So it was my first time I actually got to play in a video game world. And it's funny, I made a little cartridge for my kids that since we made all the video games and the ROMs, I had cartridges that the ROMs plugged into so my kids could play all the video games from Atari for free.
Oh, that's wonderful.
We had a really good neighborhood house. Our house was very, very popular.
The comment.
Yeah. Uh-huh.
Yeah, so from there, I still was interested in video. Now what happened is MOS, well, we did the 6502.
Right.
And that changed the world as well.
Right.
Okay, and and Apple got involved with it and so forth. But then what happened was that it never caught on fast enough. The support wasn't there, and MOS, they got into financial trouble. So then Commodore basically went, okay, we can vertically integrate. And that's when Commodore came in and basically
What
took it
year
over.
was that?
End of 76, early 77,
Okay.
roughly right around that time, maybe, yeah, 77, because Chuck Peddle had come in at around 76, and that's when 6502 came in, 75, 76, right? About a year after I was there.
Okay.
Chuck Peddle and Will Mathis and that whole team came in, and Bill Mensch, they all came in from Motorola.
So a question I had then was Chuck helped founded MOS, but that's not quite true.
No.
MOS was there. There was Alan Bradley, and it became
Alan Bradley, yeah,
MOS.
MOS started in 1969.
Okay.
Okay, yeah, and it was Alan Bradley funded it, and John Pavinin and, I can't remember the other two gentlemen, Don McLaughlin, one other guy, I can't remember his name. They were the three founders, if you will, that Alan Bradley funded.
Okay.
And so what ended up happening in that 77 era, 76-ish, Alan Bradley just stopped funding it. There was no future in semiconductors, right?
It's all industrial controls.
Right,
yeah.
exactly. What do we need?
Right.
It was just mind-boggling, but that's the world that back then, okay? So anyway, Commodore comes in, we continue to make calculator chips, and I still wanted to do video. Okay, now if anybody can remember the video typewriter.
Oh, yes, Don Lancaster, sure.
Yes.
Yeah, uh-huh.
Yes.
Okay, so that was fascinating to me. I said, okay, what can we do? How can I make this thing into something that's malleable? Okay, and the aha moment was, okay, I'm going to turn the ROM that the character set is in into RAM.
Ah, okay.
That was like, okay, and I can make this work, because if I put some ROM and RAM in there, then you can change the character set as you need.
Sure.
And then the object is, how do you get something to move across the screen? Well, I could make like 8 or 9 of them, will just step through them, who appear to move across the screen, sort of like the old flip card thing.
Right, right.
That was the concept of what we did. And so,
So what other kind of graphics things? So at the time, the character graphics were reasonably well known. The PET had this fixed font.
Right.
And so you had looked at all these circuits and figured it out and so forth. Well, let's see. How closely had you looked at the TV typewriter, actually? It used a very different technique of generating.
I just looked at the fact that it was ROM, I knew what it was doing, and I
Okay.
didn't actually go into the
Okay,
details
okay.
of it, because I...
Makes good sense, yeah.
I felt that architecturally, it really wanted to be more of like a processor kind of structure: fetch, store, manipulate,
yeah.
and display.
Well, it was bizarre. It used a FIFO which you can use, but
Right.
you can't really write to it very often.
Exactly.
But anyway.
You're right, yeah. So it was a way of, and also the indirection structure of the 6502 lended it really well to be able to go and pick things out and change what character you were
Oh,
going
absolutely.
for.
Yeah. Without random access, you'd be in a lot of trouble.
Right, and FIFOs were a form of memory back then.
That was the thing.
Yeah,
Yeah.
there wasn't the big static RAM that we could access, wherever.
Well,
we
they
wanted
were
an
cheaper.
address.
I was thinking about it. It's all the wires are short. Or most of the wires are short. Yeah. So I understand that the goal originally with what eventually turned into the 65. What is it? 60.
About 6560, I think it was, or something.
Yeah, or 61 or something.
Yeah, something like that, yeah.
So, I've got numbers here.
Yeah.
Eventually. Sorry.
It's amazing that we've forgotten the numbers, because we used to live and die by those numbers, and now it's like
Vic 1 and Vic 2 is all I remember.
I've only ever heard you refer to it as the VIC 1.
Yeah.
Vic 1, Vic 2.
Yeah, that's
Something
one
like
and Vic
that,
2, yeah.
because these numbers were made up later.
Right.
So if I understand that the idea was originally, hey, we're going to build this great chip, sell it to all these companies. They're going to go and make video game
Yes.
consoles off of it, and that didn't quite happen apparently.
No. Well, yeah, the object was, we're going to make a video game, and we're going to try to sell it to Atari or Coleco or
Right.
Mattel, somebody that make a video game out of it. And we beat our heads against the wall for about a year and a half after the chip was done to try to get somebody to buy into it, and nobody would.
Oh.
And here's what ended up happening, okay? Now, this is where another person of lore, a good friend of mine, Bob Yanis, I was interviewing and wanted to fill out the staff, okay, and get more chip designers. So he was at Villanova and finishing his senior year there, and I interviewed him, and he came into the office, and I showed him the VIC-20 prototype that we had, which did a video kind of a display and so forth. And he said, "Oh, wow. Would you mind if I do my senior project on this?" I kid you not, okay? So I said, "Sure, take it. We have a bunch of them. Take one home." So he did. He took one home, and he did a senior project on it. And then after his senior year in May, we hired him, and he came in, and he showed us this wonderful thing that he did. So literally, like a few weeks later, Jack Tramiel was coming in, and we showed him this prototype, which was basically a VIC-20 where Bob had put a little operating system in there. You could type on it and so forth. Very rudimentary.
Yeah,
but
we never heard about the operating system part.
Right, yeah, he had built a little just so you could type on it
That's
and
cool.
make it, and Jack went, "I want that."
Right.
Okay, and Chuck Peddle was called in, he flew in, and they had this big meeting, and Chuck didn't want to do it, and Jack said, "You will do it." and ultimately it moved, so then the actual architecture moved out of MOS, and they did the architecture of the final VIC-20 in Palo Alto.
Ah,
And
Right. Bill Seiler.
Bill Seiler, yes. Names and I am. Yes. And Chuck was very upset because of the fact that I had done that phase 1, phase 2 DMA structure.
Oh, yeah.
Which is the lifeblood behind the Commodore products, and we kind of knew that, but you did it.
Yeah.
You said, well, let's do it times millions. Let's make these things share the bus.
Right.
Everybody else was waiting for refreshes. They would wait to the dark period of the screen make changes and then get out of the way. And the beauty of what Chuck, I called you Chuck. Okay. Beauty of what Albert did was they could sit there and simultaneously get to the same ramp. It's just your turn, my turn, your turn, my turn.
Yeah,
very
it was
quickly.
truly one of the early, like, true DMA.
Yes.
So totally, so it was uninhibited. So the only thing you had to have was memory that ran twice as fast as your
Right.
processor or your video requirements.
Yeah, and in fact, this is the hilarious thing. If you plot processor frequency over time versus memory frequency over time, there was you hit the exact window where you could actually have memory faster than the processor, and that's not been true for 30 years. Whatever it's been. I mean, it's very nice.
Yeah.
Absolutely.
Yeah.
So
that was- they were the thing.
this other Steve apparently did that on the Apple II as well, by the way. But it's sort of a 6502.
Did he? See, I'm not aware of the architecture of the competition. As strange as that may sound, we didn't examine it and say, okay.
Yeah,
we're
yeah.
gonna
You
do
just you just mocked
just
it.
kinda-
Yeah, no, I understand. Yeah, it's good.
They use our chips.
Yeah. No, I understand completely.
Well, that's-
no, it's a natural thing when you look at how the 6502 hits the bus. You
Right.
do have this sort
Oh,
of
yeah,
half the time
yeah,
to
it makes
do it.
perfect sense.
Yeah.
That was the
No, it makes
magic.
sense.
That was the next piece of like, okay, how do I get enough bandwidth? Because the old Atari 2600, as Bill
Yeah,
said, it
yeah,
was stuck waiting for synchronization with the blanking times.
Right.
And, it had to try to force feed as much as it could during those periods, and that was all you got.
It was a
Yeah.
brutal thing. I've looked a little bit about that. It's barely a line.
Oh,
for a
man,
chip.
it was really a
It's
nutty.
9 microseconds or something.
Yeah,
Yeah,
there's
it was,
something like
oh,
that,
yeah, it was really amazing that they were able to do what they were able to do, but it was
But,
really painful.
so now you breadboarded the VIC chip.
Oh, yes.
So, yeah. if
I
we
got,
could
yeah,
back up
that's a
and
good
talk about
story.
that.
Yeah, this is
Yeah.
funny because, okay, so I'm a ROM designer, memory designer, and, oh, by the way, I'm gonna do a video chip. Yeah,
Which,
right.
which the company hasn't done before.
Nobody's done one of these. Okay,
Well,
so,
not just a video chip, but a color video chip with DMA.
Right.
Yeah. Okay.
What could
yeah.
go wrong?
Yeah. Piece of cake.
so, they basically went, well, are you sure you can do, let me prove it to you. I'll do a breadboard in TTL to show that I can make this actually work. So I designed and this is back when you were actually doing taping. There was no system that you would do the layout for you. Literally, you
The
take it
PC board or the chip?
the PC board.
Okay.
Yeah,
we're
so you
talking
do taping.
PC board chip.
Yeah,
Okay.
you tape the chip.
Okay, but your breadboard, you did it. You
So I
actually
did a
PC
breadboard.
board,
Literally, the breadboard was
but not wire wrap. That's what I would have
Yes,
expected.
it's wire wrapped.
Oh, wire wrapped. Okay,
Yeah,
that makes sense.
we actually, I put all of the pieces on there, and we had that made into a bunch, and then they wire wrapped it on the bottom.
Oh, okay.
Oh, okay, that
Kind
makes
of
sense.
hybrid.
Yeah.
Hybrid
Okay.
approach, because
Okay.
it was too hard to figure out all that.
And
Yeah,
power and
no,
ground
it's,
and all that.
and you
It
can
was-
probably get the power wiring
Right,
right.
exactly.
Yeah.
All right, so they wire wrapped that, and then, so I basically, it wasn't the full VIC-20, but I remember that I had the color stuff, or I had the RAM working, the DMA for the RAM
Yeah.
working and so forth, but I didn't have color yet. Okay, and so they were really worried that, okay, and I literally, he goes, well, you don't have color working yet. How
Right,
are you, we
right.
can't let you do this unless you get the color working.
Oh, yeah. Well, in my experience is that there's nothing easier than getting color working perfectly on NTSC.
Yeah,
Right?
what a-
It just
what-
works
happens,
beautifully.
right?
Yeah.
So I spent a weekend cobbling together the color circuitry. And then that Monday, everybody, the team, I remember the team came in and went, wow, you got it. And I said, yeah. And they said, all right, go do the chip. So that's what I had to do to prove that I really did know what I was doing when it came to that time. That was, I guess, in '76, I guess it was. Yeah.
Now, I assume you learned a lot while doing the breadboarding too.
Oh,
or-
yes. Well, yeah, exactly. But it was architecturally very clean in the fact you had just a bunch of registers that you filled out, and you had 40 registers, and 20 registers in this case. So, and you just fill them out as you go.
Right.
And then, yeah, so it was pretty much a simple, I don't think I had a full, I'm trying to remember, but so long ago, but I was able to get the characters on the screen, which is all I wanted to
Right, right.
prove that I could do.
Well, to me, though, that's kind of the beauty of the VIC chip itself. I've got some screenshots
Oh,
here.
yeah.
Of course, given the era, of course, you have to. Hal actually licensed Pac-Man, apparently, to be able to do that. I thought it was just another
I didn't
illegal
know that.
knockoff. Yeah, anyway. Oh, and you mentioned the smooth moving. It's kind of painful. All I have are these still images, but in fact, the animation is the whole point.
Yeah.
Right,
So the trick here is you still have these big fat characters, but you would shift through them really quickly.
Again, I always
Yeah.
thought the card flipping thing, and
Yeah,
that's
yeah.
what you were doing essentially.
Yeah. So you
At
can
1 megahertz.
yeah. Exactly, yeah. Here's another thing I found. People are still writing new games for this.
They are.
You're kidding.
2005.
8-bit guy is.
Yeah.
just did.
Oh, that's a riot.
This is insane, yeah.
So now, during this time, where was the toy and the Ultramax? Was that after the VIC?
That was after.
20?
Yeah.
Okay.
Yeah. What was that last one you put?
Yeah.
So
show the
what I
die.
have here, this is a die photo, and so this is the fashion these days to take these
yeah.
chips and.
Which one is that?
So I believe this is the VIC 1.
Oh, okay, yeah.
You
I
laid
have
this
seen-
out, right?
It's
Yeah.
missing
been a
the
while.
Sprite collision logic.
No, that's why I was
Right,
looking for,
right,
that's why I thought it was a
right.
bit, yeah.
That's what I look for too, yes.
Yeah, no, I've got that for later. We'll
Okay.
get there.
Right, yeah,
Yeah.
yeah.
I
Okay,
actually, so you
I have
have
that, I have that in my car right now, the Vic 2, one of these.
Oh, fantastic.
Yeah,
Okay, a little
yeah,
larger.
okay.
Oh, wow.
Yeah, and this was the block diagram of it.
Yes.
So my understanding is that for character graphics like this, it's mostly about counters and horizontal and vertical counters and address generators and things like that.
Yep.
And just looking at that, that's kind of vaguely what's going on here.
Yeah.
You've got a bunch of registers controlling the size and all the rest of that.
Correct, yeah. Yeah, because, I mean, if you looking at a TV screen as a digital structure, you just have so many pixels across and down, and you have to create the vertical blanking and the horizontal blanking periods. So it's just a really big counter and a lot of decode to set the different flops essentially to create the signals.
And with this, the DMA axis is really quite regular, right? It's fetch the character, fetch the pixels, shift it out, go on to the next one. Okay.
Correct, yeah.
Right, that's going to change when we get to the
Yes.
C64,
Yeah,
right,
it got
okay.
more complicated because you had to do a lot more stuff.
Okay, yeah.
Hence, the serial bus got slower.
Yes.
Oh, interesting, yeah.
Yeah.
So there's this magical little thing. So what's nice about the 6560, there's actually documentation because it looked like you intended to sell this at one point.
Yes, we
so
did.
it's vaguely public and so
Right.
forth. But there's this magical box down here, color decode. And so I'm curious what did go into the color
Okay.
and making all that work.
All right, well, this is a riot too, because I knew about
No,
NTSC.
that's in the Atari, but anyway.
At any rate, what we had was, how do you control phase shift, which is what you had to
Right.
do to
Right,
create
yeah.
color. So, and this is well before you had Google and Wikipedia. I literally went to the library, the public library,
I've heard of those, yeah.
to learn about what phase shifts I needed to create the various colors, okay? And then, fortunately, the trigonometric, you take A sign plus B sign.
Sure,
And you
yeah.
create a phase shift, tan to the A over B. So once you knew that, all you had to do was create a little resistor ladder network. So I took square waves, which were 90 degrees, and then you basically ran them through a resistor ladder network, which
Okay.
created the summation for the amounts of each of those two.
They were square waves?
Well, and they weren't, I ran it through a filter.
Okay, so you made it into a sine-ish wave.
Right, yeah, I
Okay.
made it sine-ish.
Sine-ish, that's right. Yes.
Yeah.
Right, and so that went into an op amp, okay? And then that basically, and then I just amplified it out to make sure that it was peaked correctly.
Okay.
And that then allowed me to make the color. So by adjusting the resistors in the two phases there, I could create any phase shift that I wanted.
You were doing essentially 2 pulses per 3.58 megahertz
No, it was 3.5
Yeah.
each one. Yes, two of them, I'm sorry, yes.
Oh,
yes. So
okay.
two of those.
One delayed by 90 degrees.
Ah, okay.
Yeah.
Ah, okay.
Yeah.
Yeah, that makes good sense.
So
Yeah.
just add them up.
Just
And
add 'em up,
the
right.
thing at the time was NMOS made lousy absolute values of resistors, but the ratios could be set.
All you needed was the ratios.
Right.
Right, so as long as, and that was, as long as the ratios were right, I knew that I could
Yeah,
get
I
the
was going to
colors
say
intended.
a video speed DAC and op amp, that sounded a little bit beyond what a typical ROM designer would be doing at the time.
Well, the good news was that, but doing memory was actually a good thing, because I had to work speed.
Ah, right,
I had to get
okay.
things to go fast.
Oh,
To
yeah.
drive
I'm-
huge
I'm-
arrays and
Right.
the
Right, right.
capacitance of those big arrays.
Right, and
and stuff.
exactly, and like the sense amplifiers.
Oh, right.
So all
Well,
analog.
They look digital on the
Right,
outside, but there's nothing digital
there's nothing
inside.
digital, it's
Yeah,
all
okay.
analog stuff internally, so
Makes sense,
having
yeah.
that speed really allowed me to get to the color structure.
Okay. Do you have any recollection of, bits and pieces on the die while I have it up here, or is that too many chips ago for you?
It's a lot of time, I tell you, the color was the hardest, it really was one of the hardest
I'm
parts.
sure, yeah,
Because
uh-huh.
doing the TTL version, as you said, really did force me to think the whole digital process through. And I remember, back then, again, we didn't have the stations to work on, so I had this chart, literally it was about 12 feet long, of the entire timing diagram of the chip. from beginning of the top of the screen, all the syncs.
An entire field worth of timing diagrams.
Correct. By hand. Where the decodes would have to occur, so you'd set the flip-flop here, reset it there.
And you
So
could-
I've
you
got to
could
make
only-
this joke. I'm glad you were in North America, not Europe, right? Because you got a
Oh, the
slightly
PAL.
smaller,
Yeah.
right? You got a slightly smaller design, right?
Yes.
on this. Wow.
Well, we had to do the PAL version as well.
Yeah, I was
One
going
of
to say,
these.
it
Yeah.
caught up to you in the end.
Yeah, it did. But yeah, but there was no other way to do it. You didn't
Sure.
have simulators, and
That's why I was going to ask, you could only simulate one horizontal line, I think you said.
Yeah.
And the simulation was SPICE, no digital simulation.
No, it was all deck of cards, or at that time, I teletype.
Right, yeah.
Big
I remember the
improvement.
card-
Yeah, oh, yeah.
Uh-huh, yeah.
Right.
Yeah, it was crazy. It would run all night. I mean, to do one line, it would run, and it was really just a small amount. You could do maybe a few hundred transistors.
Yeah.
So during this time then, what was chip design like? You would sit there and do a cell or something like that, and they would digitize, or walk us through?
Yeah, okay, so the first thing, you do a schematic, and you would have blocks. You try to keep this thing as regular as possible. And then you would have, your NAND gates and so forth. So you'd have a block, and somebody would lay that out by hand, each of the transistor sizes. And then you would try to keep things regular so you could just step them and reuse them all the time. So you would you would try to minimize the number of cells that you used. And then you kept everything from a speed perspective, it was how many transistors was one driver going to have. And if anybody remembers the HP calculators, the 65s with the little dipsticks in them, this is really going back.
Oh, wow, okay. Yeah.
I programmed one of those so that I would be able to say, okay, this one's going to drive this size of transistors, which is this much. Then I would put that in, and it would then spit out the transistor size necessary
Oh, wow.
in order to
Wow.
create a rise time of a certain
nice,
number
okay.
of nanoseconds. So that way I sped up. I
Right.
simulated it on a.
Yeah.
Oh, that's nice.
So I
Yeah,
sped
yeah.
up the process so I could figure out what transistor sizes I needed.
This is great. Your own EDA tool.
Right, it was bad. But, so, once you did that, then this whole thing got compiled into what you're showing here, and that was where we did have some computer aid.
This was the big Calma.
Calma plot.
Yeah.
yes.
Okay.
So they were digitizing those still on the big drawing boards and using the digitizer, or were they using the tablets at that time?
No, on the big board.
Big board, yeah.
Yeah.
Because I heard the people complaining about shoulder pain at the end of the day from sitting there doing this all day long. But now were they still cutting? They weren't cutting Rubylith at this time.
I'm not trying to remember, when does
It's like
Rubylith
a
go away? I know we did it for the 6502 Rubylith.
Yeah.
But I don't think we did, I think Rubylith was gone by
Right.
this time, by
Okay.
the big process.
So Rubylith, for everybody, is actual red film that they would actually cut and photographically make small enough to make a chip out of. But it started by hand cutting film. It's, so we,
I think with the Calma systems, they actually used essentially a pen plotter, but with a knife.
Correct.
yeah.
So it
Oh,
would do
okay,
that. So
okay.
they would, I'm sure there were manual touch-ups and so forth,
Yeah,
but
yeah.
this was kind of the reason to use the big.
You're right, I
Yeah.
forgot about the.
Yeah, so it was
Calma.
a, it was a thing that was like basically an 8x8 pool table size thing with a cutter on
Right,
an XY pen plotter.
Yeah.
And when you were all done, the thing would cut it all out, and then we would have what we'd call a peeling party. So you go in with tweezers, and you'd peel up the areas that were going to be exposed.
So it
on
was,
these
it was
things.
half automated.
Right,
So
right,
the
right.
cutting, but the removal.
It still needed to be photographically reduced.
Yeah, so then you put
that's
this in a
amazing.
huge camera that had a camera the size of a room. It had a
Wow.
plenum on a chamber on it,
yeah,
like 8 feet by 8 feet, and they'd hang this ruby lith on it, and they'd shoot it down to this size, I mean, whatever, 2x2 or something. And that's what they used to make the posters, which we would then use to check that all the peeling was done correctly and all the transistors were right and so forth, okay? And then they take that and then shoot that down to the final size for the chip itself.
How long did it take you to check the VIC chip then? Because in my era, they would sit there for months with their little scales, rulers, and sit there and measure.
No, I didn't measure them, okay, because of the fact that I was very consistent about, I remember that everything was a digital size. So I
Right,
knew that
right.
it was, I could tell eyeball-wise how
Right.
big things
So
were.
it's interconnects. You-
Right, I was purely 100% interconnect
Okay,
intense.
okay.
It took a month. I
Okay,
mean, literally,
right.
I had a plot that was 12 feet by 12 feet, crawling on it for days.
Yeah,
But it was nuts. But it was, I mean, but I was driven.
Yeah, yeah.
yeah,
Well, you saw the color at the end of the tunnel.
yeah.
That's fantastic.
Yeah.
So, yeah, it went on to take the world by storm.
Yeah.
Oh, one of the things I came across, and one of the things I found very unusual about the VIC-20 is it used static RAM chips, 2114s, if I remember.
Correct.
And I don't know, from what I was reading, it was claiming, they had a surplus of these. And so Jack said, we got to dump these into them. Any idea whether that's story is true?
I don't know if that's true or not. I designed the RAM chip that's in there.
Yeah, okay. Good, okay.
Well, that's the key, is first and foremost, as a system designer, if we could use a Commodore part, we
Yeah.
absolutely did.
Oh, sure,
Yeah.
sure.
Because we could control the timing on it, and this was back in days of allocation where you could hold up.
Yeah, so
So,
Oh,
we
makes
we
sense.
I
ended up
didn't realize
using,
you
yeah.
did the RAM chips.
Yeah, I did the RAM
Oh, that's awesome.
Yeah,
Yeah,
yeah.
yeah. Well, this thing had a whopping 5 kilobytes in it of RAM.
Right.
I mean,
I know.
Nice binary number there, Al.
yeah, well, I mean, it's great.
Fly by 4, Victor?
You know,
Yay.
5, yeah. uh-huh.
They're funny.
Very, very nice. But yeah, there's sort of almost nothing there except a lot of your RAM chips, right?
Yeah.
A lot of heat
So you
generation
get-
going on there too. I noticed those heat sinks.
Oh, yeah,
Yeah.
that's a nice one. Well, yes, before we got switching power supplies.
Yeah.
Anyway, so this thing took the world by storm, or at least a little bit, but of course you couldn't rest on your laurels.
It was our TI killer, is how I heard. Did you guys ever hear it called that?
Yes.
Okay.
Yeah, there was, I mean, Jack had a saying, business is war.
Right, yes,
I
yes,
mentioned
yes.
that, right? Yes. And he really took that to heart,
Yes, he
okay?
did.
I mean, literally, we're gonna target TI.
So wait, the VIC-20 was targeting TI or the next one?
Well, the next one was gonna target TI.
Okay.
Oh, I
the
thought that, we
yeah.
called the next one the Apple killer.
Oh, okay.
So the
Not,
Vic
I
20
mean,
was the
it was a
TI
lot of different names for
Killers.
things.
I would
yeah.
imagine
But
he was trying
it
to
was the
kill everybody.
TRS-80,
He was, yeah.
it was the Trash 80 and the as we referred to it, and then
Everybody
the
did,
TI,
yeah.
Yeah.
right? And but Apple really was
weren't on
never
the radar.
wasn't on anybody's radar
No.
because they were in a different market space. They were more in the business market space, not in the consumer market space.
Yeah,
So
yeah.
they never really looked at Apple as a
Right.
as a
Though they
deadly
were smart,
competitor.
went after the schools.
Yes.
Which we never did.
Correct.
Yes.
Yes. Right.
Yep, yeah, crazy thing, whole nother
Another
topic.
chapter.
So, yeah,
That's for
absolutely.
tomorrow.
Right. So, but, let's see, the 99.4 came out,
Yes.
somewhere in between that, and it had this marvelous Sprite thing, the
Yes.
9918
Right.
Sprite processor in it. Seen that and said, I wanted one of those, or?
Yes,
how did-
well, it was the fact that while the VIC-20 allowed you to do some level of video gaming, it wasn't good enough. I mean, I wanted more.
We all did.
Right, exactly. So, I mean, an 8-bit processor just never had the power to do anything, moving random memory around in the space,
You
so.
could watch it scroll. It's the days you could watch a screen scroll.
Yeah, and so there was really no simple way to allow you to move more characters and randomly move them smoothly. So the Sprite thing from the TI was like, I want that. So,
How'd you decide how many sprites?
okay, that was a function of, we could only make a chip that was so big that we knew we'd have a yield.
Sure.
Okay, and I forget what 200.
You were almost pad limited size, almost.
Almost,
is
yeah,
where
it
you
was a
were.
little
Yeah.
bigger than that, but not much. I mean, we knew that based on the defect density in the fab, a chip that this size is about as big as you would want to go in order to be able to have reasonable yield.
Yeah.
Do you
Okay.
remember the yields on the VIC-1? Like 20%?
No,
or
it was
were they
higher than that.
Way higher?
It was in the
Yeah.
30
Well,
to 40%.
When,
yeah.
though, right? You know, the first.
Well, that's why I'm asking the VIC-1.
Oh, yeah.
Well,
Yeah.
but, you know, the process over time, they got it better. and
Oh,
better.
it's
Oh,
like
yeah.
baking. Yeah, it's
Yeah.
like
Yes.
not only chemistry, but baking. There's art in how they
Oh,
make
yeah.
it is the way I always looked at it.
Absolutely, yeah.
Yeah, a recipe, yeah.
Yeah.
And they got in a lot of trouble when they messed the recipe up. I just, they would go looking for the guy that ruined the batch.
Right, throw it back.
Well, let's see, did they fire him or just shoot him?
Beat 'em up.
Yeah, okay, yeah.
Because I remember one guy writing a thing, I'm sorry, I ruined the batch, I won't do it again.
Oh, wow,
Yeah,
okay,
on his-
yeah, I would have assumed it'd be a lot harsher than that.
It was definitely a little bit of,
Well,
black
so
art.
this number of 8 sprites on a line, which is a very fixed hardware restriction. This is kind of at the heart of the chip in many respects, right?
Yeah.
So you've actually got a patent
yes,
on this, and this was the least technical diagram that it had. It also had you know, things with MOSFETs on them and so
Right,
forth. But this whole thing, if I understand, is making the decision of, okay, I'm at a pixel, which of the 8 sprites is visible or is the background?
Correct.
Right?
Yep.
And so why is that the heart of the chip?
oh, because you have so many decisions to make at that split second in time. Okay, so I've got a background, do I want to display that? Now, the background was prefetched, so I knew that was a stream that was coming down. So now you've got the data from each of the sprites, it's also prefetched. So now all you're doing is waiting for the timers to click over. And now once that happens, you have a decision to make as the cell, to say, okay, which one am I going to display and a priority for those? Okay, that was where you had a sprite priority list. Sure. And then you were able to select background or foreground. So all of that had to go through the big logic tree that was really crazy.
Right.
And so that allowed you to make things flow nicely. You could put things, make them visible, make them appear. So there was a lot, that was, because realistically, it was that was the heart of the change from the VIC-20 to the VIC-2.
Absolutely,
Because, because the rest of it was just doubling everything else in the VIC-1 for the
okay. Yeah.
background. The sprites was the heart of the system at the time. And it was a complicated piece of logic, I'll tell you.
Yeah, no, I
Yeah.
see why you would get a patent on that, definitely. So you say it has to go fast. How fast did it have to go at the time?
Oh, my goodness, we were going, it's so slow today.
Yeah.
I mean, so it was literally about, we were running at about 2 megahertz, as I recall, internally on the clocks.
Well, let's see.
So
Well,
that's 500 nanoseconds.
It would have been the
2048.
it would have been the pixel speed.
Yeah, the pixel
though,
speed,
right?
correct.
Yeah, so I
pixel
thought that was
speed
more
rate.
like 8. I thought that was
No,
much higher.
4. It was
4.
250 nanoseconds.
Oh, okay,
Yeah, because
okay.
it was 8, you started with 8, and I divided that by 2.
Yeah,
okay.
8.18 divided by 2.
Gotcha.
Yeah.
Exactly, right, yeah. So that was the pixel rate. So it was, yes, it would be the 250 nanosecond decision
Wow,
rate.
okay.
So
Yeah, that's pretty heady for that time.
for that time. So what you ended up having to do is pipeline the decision process, so you could only go through so many stages of logic, and then I would basically
and
stop
wait
it
for the pipeline.
and put
yeah.
a flip-flop in, okay, collect that information, then we'll go to the next series of logic. So the whole thing would shift in space a little bit.
Oh, so even the priority logic had to be pipelined to make that
Yes.
work? Wow,
Yeah,
okay.
yeah, so
no
then,
wonder.
then you had to go, okay, now if I want this to appear here, that means it has to be actually back
Yeah,
in
you
time.
have to figure it out.
Right,
yeah.
exactly.
You couldn't look at 8 things at once. You could only look at 2 or 3.
Right.
And then 2 or 3 more, and then 2 or
right.
3 more type
It
thing.
got, yeah, so it was just a speed function, you just couldn't go fast enough to get it all done in one shot.
Makes good sense.
So Albert did all his work in what, NAND gates, NOR gates, exclusive NOR gates, inverters, and pass devices.
That's
all
it.
you had in your bag of tricks.
That was it, and you
Yeah.
really couldn't go more than a 4-input
Right?
NAND
The
gate.
voltage drops would get up.
Yeah,
This was all NMOS or?
NMOS.
Yeah, okay.
That was why it was a power hog.
Oh, I'm sure.
Oh,
yeah.
I mean, we were running at 8 megahertz back then, which was, whoa.
Yeah. No, that was
What do we
serious
do
stuff.
with all this heat?
Yeah, right, oh, boy, that got so hot, it was
Yeah,
ridiculous.
Yeah, oh, yeah, they shifted this, or they ripped off the.
The
But,
lid.
but heat sinks and fans and so forth were still a decade off, and you couldn't put this in consumer devices
No.
at the time anyway.
Yeah.
Yeah, well, the heat thing was really, this was one of those it was like a MacGyver moment, okay? You got the chip sitting in that box there, okay? And since that was creating a lot of FCC noise, we did put that in a metal
Right.
box, okay, to pass FCC. Problem is, again, now putting it in the box, it got even hotter.
Right.
So we had the wonderful idea of welding the little tab to the lid in order to get some heat sink function down onto that, so we could get the heat off and keep the thing alive. Without that tab, it would overheat.
Years later, we were still doing tabs on everything. Still the way to do it.
It was like, oh God, how do we
You
get the
didn't want to
heat?
just heat up the inside of the computer either, so the tab tube metal, and
So
then
the-
metal to something outside.
So I've heard of this heat sink concept that I've seen it used in certain other computers.
Right.
But what was the deal? Aluminum was too expensive at the time, or it wasn't? on your-
Aluminum wouldn't have acted as an EMI shield, so we needed something to block the
Ah, you
EM.
needed both,
Yeah,
okay.
yeah. And speaking for the 128, which is just huge, that thing cost me, 20 cents to have stamps, some simple, small little amount. So, yeah, fix my heat problem and do FCC shielding, yeah,
Yeah,
let's both.
perfect.
Okay, yeah.
Put them all
Okay,
there,
yeah,
right?
check it in,
Absolutely,
okay.
that was what the answer was.
People don't like it 40 years from now, heck with it.
Makes good sense, yeah. Let's see, so I'll ask the same question about the die, and I apologize. So one of the things that's always been interesting to me is how successful Commodore was in Europe, especially Germany and so
Right,
forth.
yeah.
Which I never quite, but now I understand they had the sales channels from before.
Right.
So I apologize, this might actually be a PAL VIC-2 chip instead of the NTSC, which is what we had to be talking about, but I assume they're pretty similar.
Almost identical, just the
Few numbers
Just
few
the
numbers.
color
Yeah,
encoder, right?
Yeah, the color encoder is a little different, and
And
the,
some counters.
yeah, the counter points are
Right.
different. Other than that, it's pretty same.
Do you, can you guide us through any of the larger sections of this, or is it already too far? Is it too-
That's a little bit past, my memory banks are not that,
I can understand it.
But
I
the-
wish they were, but they're a little bit
The
flaky
main
there.
thing you see, though, is now there's a huge sea of gates, kind of in the middle, and that's the Sprite
Yeah,
logic
that's
times.
in the center there.
Okay, this is
Right.
the
Whereas
Sprite stuff.
the VIC one looked like a bunch of disparate functions. This thing has this huge thing at the bottom there, and you see the distribution going into it, trying to, and if you stop and count, you'll probably count eight
Eight of
of
them,
stuff,
yes,
yeah.
right, yeah,
Yeah,
yeah.
well, but it's pretty easy
You
to
know,
find eight of
in
anything.
the chroma stuff up in the top right corner, I don't know why I think that. I could be wrong.
You're right.
But for some reason, because I used to bop in while the guys were working on it, I just, for some reason, I want to say the color was up there. Maybe
Yes.
because of the pin numbers.
Yeah, that is that's exactly
Okay,
right, yeah,
cool.
right, yep. Yeah,
Did you do a similar trick with the resistive ladder and the two
Identical.
faces? Okay.
no reason to change it, was working fine.
Okay,
Yeah.
yeah.
Did you breadboard this one first?
No, they trusted me this time.
Oh, okay.
Wow.
Wow, so you got this to work essentially on the first rev. You shared with me you had to make one tweak. You
Yeah.
got this to work on the first rev.
Yeah,
That's
there was
amazing.
one error in the Sprite logic, and
Wow.
this is a crazy story too, because I got it in like November of '81, all right? And got the chip, putting it under, and back then, the line lengths were big enough, wide enough that you could actually, what we called microprobe them, all right?
Right,
With a micro
right.
manipulator. We had this tungsten needle that you would dip in acid to make it really pointy. So you pull it out real slow and it had a really tiny point on it. And you'd put this on these calipers, verniers, and then you would literally go in a microscope and look at a line. They removed the glass passivation so you could go out and actually probe the thing with an oscilloscope.
Right.
And I found the logic error and knew what the fix was. So we had to go to the CES first week of January in 1982, right after, it was like January 8th or something. So we got a fix. We cut the ruby lith, we didn't have ruby lith back then. So they cut it, they went through the masks, it hit the fab like right before Christmas, okay? And they had people come in over the Christmas holiday to move it from fab, from station to station. I got the chips like on January 2nd. Plugged them in, they worked. And we off to CES we went.
And it's significantly different than the VIC-1 for new stuff. I mean, like you said, the DMA and now these other character modes, multicolor character modes, and
all those things were.
And they all worked.
Yeah, it all worked.
How many modes are there? I don't remember.
I don't remember.
Andy, do you remember how many modes are in the VIC chip? No, some number from 40 years ago. Yeah, it's huge.
Yeah.
At least four.
At least four.
Something like that. Oh, this was another thing where I was surprised at the number. So the horizontal width of the sprites was not a number that I expected. What is it, 21, 24? I'm sure somebody can correct me. But it wasn't a nice power of 2, right? When I see numbers, I expect them to be powers of 2, and I assume something is desperately wrong. So what's up with that? What happened? What's this 21 stuff? Man?
Yeah, Albert.
What were you thinking, man?
I don't remember. I'm trying to remember exactly what the rationale for that was.
I don't feel so bad now.
God, 40 years ago is a long time. It's more than that. But I mean, I'm trying to remember.
But you would have known, like, so you would have.
There was obviously a logical. I mean, I'm sure it had to do with the logic pipeline. Because obviously, everything was 8-bit. So where did those 3 bits go? I just don't have a recollection. I'm sure it had to do with the pipeline, though. I needed some.
Well, it's a lot nicer than having just 8 bits across or something like that. And this is what the TI chip had.
Oh yeah, they definitely wanted them bigger because
I didn't realize the TI was only 8.
Yeah, they were only 8.
Oh, it was only 8 and only
they were too
4.
tiny.
So we had more and bigger.
Yeah. The object was that I wanted to be able to almost fill a full line if I could. That was the goal.
Oh, okay.
Okay, to fill a whole line worth of information.
Well, I assume it was just sort of, our sprite generator goes up to 11 kind of thing.
Well, I was going to say, how big were the Apple sprites during this time?
Depends on how strong the RF source next to the TV was, right?
Yeah.
Oh, that's.
I'm going to have to go back and look and try to remember that.
How'd the 64 start? By the way, that was urban legend where you guys said, no, Jack says build it, right? Yeah. So did the same thing happen on the 64? We got kind of, you took a VIC-2 chip. What happened next?
Okay, so when the VIC-2 chips, I started to design on that before the VIC-20 was the success that it was. Okay, because again, frustrated we couldn't sell the VIC-1 to anybody to do a video game. Clearly, it wasn't good enough, so let me do another one. All right, so nobody said no. Okay. It was no. And in the midst of designing that, the VIC-20 took off. Okay, so we pivoted from there's maybe a better video game with the VIC-2 chip. We're going to focus on making it the next generation computer VIC-2. I mean VIC-20. So that really focused it on that. And originally there was, I think the original VIC-2, we only had like, I think it was less characters on the line. I think only 32.
Right, that's my.
Right. But I said, okay, we're going to make this a computer. It's got to be 40 because I knew that you couldn't get any more on a screen. That was
so your dot clock changed frequency.
Right, and I went to the 8 megahertz because I couldn't get fast enough at the 3.5. At 3.5.
Yeah, this was. I was tempted to put up So I think Scott Adams' Adventures was one of the early things that was on the VIC 20 and so forth. And you could imagine reading a text adventure on 22 column.
Yes. That was always frustrating.
I was sort of impressed, yeah. So I could
22
could
was like,
see why you would want to do that.
Yeah, I wanted to get more, but you couldn't get it on a TV set.
Yeah,
You
yeah,
know,
oh, absolutely.
it
Yeah.
was just
So
never
you
get there.
got the 64, so you got the chip and the 60, you designed the 64 around the VIC-2 chip? then?
Correct, yeah. Bob Yanes, myself, we're really the architects of that
Right.
board.
Which is an amazing thing, because speaking as a systems designer, you're a systems designer, you're a chip guy that knew systems design.
yeah,
And you knew how your chip needed to be used in the system, down to the smallest detail, because you did the whole system.
Right.
And that to me is just.
Well, I think that I like to refer to that as really understanding the application that your chip
Right.
design is going to go into. And today, that's what, if you look at what the semiconductors industry is, with the exception of GPUs, you really have all the peripheral chips that people do. They're looking at the end application and designing the chip to do that. And the NISC was an early recognition of that,
Right.
and recognizing that you're going to have to, in order to get the cost and the process down, you really have to know where your whole system's going to be. So the good news was, sort of after I started the VIC-2 chip, we knew that the VIC-20 was a success, so therefore we did everything necessary to make it not just a video game player, but a computer that would have some power. And everyone, and the story is pretty well known that we actually had designed the thing with 16K of RAM to begin with, the dynamic RAM.
So we nearly had the Commodore 16.
Yeah, it was nearly the Commodore
So
16.
who wanted 64K, I asked?
Yes. And that was Jack Tramiel.
Right.
Okay, and that was a marketing position. I remember being in the meeting and discussing where we were at, and we were giving him an update, and it was going to be 16K and so on. And he goes, well, I think that we need to push it hard, and I think 64Ks are really going to be available. The price point's going to be, by the time we get there,
Right.
the price point will be reasonable, and we just got to go for it, and oh, it'll be a big splash. So that's when we changed it to a 64K system.
okay.
Yeah, so it was.
And so
go ahead.
that certainly meant DRAMs at the time.
I was
Well,
gonna
even
say,
the,
and
even
they're
the
so easy to
16Ks were
use.
DRAM.
Yeah.
Yeah, so fortunately, architecturally, it wasn't that big of a change. We just had to obviously add another address, a couple
Yeah.
address bits. But it wasn't a big, all the timing between the 16K and the 64K were very similar.
Had you, so the 6502 doesn't have DRAM refresh built into it, unlike the Z80, which one of those competitors were using.
Right.
You had added the DRAM control and refresh to the.
Well, the refresh happened automatically because of the fact that the
There's
video
sweep
was
of
in the
the fields.
background.
Okay.
So you refresh was a freebie.
Okay.
Yeah,
Oh,
yeah.
how convenient.
Yes.
Yeah, I think we had to still do something, like when we blanked the screen, we had to still
Yes.
refresh DRAMs and stuff.
Yeah, there was something going on in there. I forget what it was, but I mean, it was
Okay.
pretty free, but the counters were there.
Graphics is friendly to DRAM refresh. anyway,
Exactly.
yeah.
But the DRAMs had a whole nother timing though, too, because they don't quite, yeah, he just moaned, everybody. The DRAMs don't quite line up
Al.
with the 6502 cycle.
Sorry to, I remember why it's 21 wide sprites.
Why?
Because you did a 64-byte sprite image. 63 bytes and then one that you had to waste time on. Then that's 21 by 24.
Yeah, okay, as I said, I knew it had something to do with the pipeline.
Yeah.
It is binary.
Yes.
Yes.
Thank you.
Thank you, Andy.
I knew it was the pipeline, but I couldn't remember the details. Thank you.
Awesome.
So getting back to DRAM, so you had to deal with the fact of pre-charge and all this, which needed a
The RAS and the CAS.
And,
yes.
and we had to have our data hold time, which was different and everything like that. But then you had to learn about things, for example, the series resistors that are in there.
Yes.
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 These things are these are hogs compared to static ramps as
Yeah.
far as pulling current and these RAS timings.
Yep.
And were they putting capacitors on the RAS and CAS when you were there in
No.
production? They were doing it when I got there.
Oh,
They
okay.
were trying to, and what they were doing was trying to make it just past the fixture. They didn't care what they were doing to the computer itself. And we got in there and helped them. you
Yeah,
know.
yeah. I left. When Commodore 64 was done. And we introduced it in January, the first week of January of 1982, and then I did leave September 1st of my, so.
Okay.
Yeah, so I didn't get to see some of the pain you went through.
Yeah.
when I left you. I'm sorry to relieve you some of that pain.
Right,
but-
right. Well, you fixed the biggest one before you left, right? Do you have your slide of the phase lock loop?
Yes,
Oh,
yeah,
geez.
absolutely. So this is, yeah, this is a great one.
So in the VIC chip, you didn't need a phase lock loop. The frequency was non-intrusive, or was it just quieter because there weren't DRAMs?
It wasn't DRAM. It was quieter, and also too, the bit rate was half.
Right.
So it really never impacted the
Well,
phase as much. You never
so-
got the interference of the phase with the black and white.
Okay.
So it looks like on the VIC, what they did is they took the 14-something megahertz, which is the color burst times
Right.
times four, right?
right.
And then divided it down, and this naturally gave you the 22 columns with,
Correct.
with all the rest of it. So
Yep.
that worked fine.
Yep.
But the problem is that if you did that, this looked like.
Yes.
And so what do? How do you make it so that it's reasonable?
Right.
And 40 columns and all the rest of it, which
Starts to look like a computer.
yeah, this is beautiful. I mean, it works on a computer, works on a T-shirt. I mean, it's all positive. But there's this problem. How do you
Okay.
fix the speed of the pixels?
This is a good
How do you,
story.
but I was gonna say, how do you get to fix it too? I mean, you're in a
Okay.
position of doing something for millions of units,
Right.
and you've got noise.
Okay, so this is Jack Tramiel wanted to kill me.
Not Mr. Tramiel.
He wanted
He's
to kill
such
me.
a nice guy,
Oh,
though.
yeah.
He was just so polite. And,
So the original Rev 1, okay, this is the one we took to that we took to the CES in January, only had 36 columns.
oof.
I did not know
Yeah, I
that.
know, that's a real secret.
Ooh, that's nice.
Because I used the dot clock of
Oh, to
7.
divide it down.
Right, so it
Okay.
was the same thing, I only doubled it up, okay, but I
Ah,
couldn't
okay.
get
So,
enough.
so it
Okay.
wasn't moving, it was,
Right.
yeah.
Okay, so
So-
it worked beautifully, but only 36 instead of
Couldn't
40.
get, because
Jiminy
it wasn't
Christmas.
fast enough.
Yeah,
Okay,
yeah.
and also too, then you had bleed between the black and white and the color phase. So that if you would put ones and
Right,
zeros.
because it's not right.
So
right.
you would try to put up red, and if you put ones and zeros, it wouldn't be red anymore.
Okay.
Okay, so it annoyed the hell out of me.
Incidentally, what you did is you just designed the video output of the Apple II. Accidentally.
Correct. That's what I did, and I hated it.
No wonder.
So
No wonder you were in pain.
We owe our legacy to the
So
Apple.
Yeah,
anyway,
yeah.
so now I get back from the CES show, and I wanted to get to an 80-character display without these problems. So that's when we came up with the 8
Right.
megahertz. Okay.
Okay. Yeah.
So I changed the clocks in the chip, changed the decoders, because the rev I did on that real quick turn it needed to be redone. We had so we had to clean it up for production, and I put this stuff in now we had really 40 characters and no crossover between them. And it came out, we plugged it in, and it had a shimmer.
So did you have two independent? Okay.
I had
Yep.
2 independent crystals, and they were drifting, and the screen had this ghosting, shimmering effect.
Nice.
Oh, it was really ugly.
Yeah,
It was
yeah,
and I was
yeah.
going, oh, shit. It was, and I still use that term, the ocean moments when you haven't designed, and that was one of them. So, anyway,
You couldn't have predicted it without
Well,
having
those
I
are-
tried.
just didn't know.
Yeah, they're pretty rare. Most of the time, it's like, oh, that's awful. Why is that? Whereas an oh shit moment is exactly, you realize just how deep it is. You're
Right.
into it.
And
Right,
I'm really
okay.
deep into it.
Yeah, yeah,
Because
that's-
this thing was supposed to go into production in May.
Right. And you've changed the count.
And I changed the counter scheme, and I'm in trouble.
Right.
So, anyway, there's a guy who worked at the company called Bob Simons, okay? And he had worked for I think Motorola, and he went, oh, we can fix this with a phase lock loop. And at the time, I didn't know what a phase lock loop was. Okay?
Right.
That was an evil analog thing.
Yeah.
Even the memory designers didn't have to deal with these.
Exactly.
Yeah.
So he basically Gen 1 up, and, in a little hard and wire wrapped it and plugged it in, and it worked. Okay, so I have to give him a lot of kudos for
And
that.
it's an LS VCF, I mean, it's an LS phase lock loop
Yeah.
part of it there, yeah.
Yeah, it was pretty interesting stuff that he was able. We had to tune it right, but once the dot clock and the color phase clock were synchronized, then you had no problems and it worked beautifully. Okay,
So
but that was a Band-Aid.
It's actually, so the function of the phase lock loop here actually is very simple. It divides by 7 and then multiplies by 4.
Right.
And the issue is, how do you build a piece of circuitry that multiplies the speed of a clock?
Right.
And the answer is, you build a voltage-controlled oscillator, you look at the results, and then you tune the frequency that comes out based on, oh, that came a little too early, came a little bit too late.
Right. It's constantly
Feedback.
hunting.
Right, it's a feedback thing. It's very, very complicated. And incidentally, you can also use these things to tune FM stations. It's an FM detector.
Right.
But this is a steaming pile of logic that you would not want. You do not want in your cheap consumer device.
And you're going to production.
And you're going into production in no place.
Oh, God.
Yeah.
And you're going to have to pass FCC.
FCC.
Yes.
All right, and you got
right.
these clocks.
And so, by the way, you've got this analog oscillator operating at a few megahertz or whatever. You do have a nice disciplined crystal up here
Right.
in the lower right, but all the rest of this stuff, and Zeners and charge pumps and phase detects and
Oh, stop it.
yeah,
Yeah, that was fun. It was
Absolutely.
and I can still remember it. So I had to make the fix and put this thing together, and then eventually the word of this problem filters up to Jack Tramiel.
Oh my God.
Oh, you didn't run to him right away to show him?
No, I fixed it before we did that.
Okay, yeah.
Got him a solution.
Yeah,
Yeah,
I went,
yeah,
well, we have a problem, but here's the fix. Okay, so we had to add the circuitry to it, and he got, so anyway, I can still remember like standing up and ready to jump at me across the table.
Yeah,
Like,
yeah.
you could have cost us this company.
He's right.
I said, yeah,
Wow.
but we didn't.
Yeah.
Yeah, I was all 29 years old.
Yeah.
Jesus.
Yeah, I was 24, 25.
Yeah, I mean, it
Well,
was
let's
a whole
see.
different
You were
world.
29 before you went into the office. What were you
40.
after? Yeah. Wow.
Oh, yeah, that was definitely one of those, how are we going to get out of this mess? And fortunately, this was a good Band-Aid that worked great. I mean,
Yeah,
it solved the problem. But
Well, the
problems with it? Or?
Was there any production problems with the VIC chip guys? So they did a Tiger team. You correct me, and I'm looking at Andy. on
Yeah, I
this.
know. I say Andy is over
Yeah.
there. These guys had to clean up my mess.
So, well, one trick I'll talk about real quick was we had light blue flicker on dark blue, right? And they made it, which is the home screen has light blue characters on dark blue, and in a character cell, if part of the DRAM cycle got botched, it'd select the foreground color instead of the background color. So light blue snow everywhere, looked like crap. What they did is they went in and changed the characters in the cells that are supposed to be dark blue. They made the foreground and the background color both the same color of dark blue. So it's still flickering, but it's flickering dark blue on dark blue. So even on the oldest ones, if you look, if there's a cell with a character in it, you'll see like some dots getting into that cell too, but the rest of the screen is pretty blue.
So it was RAM timing problem?
Yeah, we had some RAM timing problems. Really? And it wasn't you.
how can you expect? He didn't design the DRAMs, right? Just the SRAMs.
Well, so another story, because I ended up in the bucket for what we called, where you babysat production for the C64. And Micron DRAMs, we had a big problem with, and it was sensitive in certain positions, the end of the row.
How about that?
And the problem was both of us. They weren't making the DRAMs right, and we weren't quite using them right, and it showed up in 2 locations on the board. And so we got better at it, and they Diorio got in and changed some of the timings and stuff. So yeah, we worked through a couple, mostly getting the heat out. We went to a really copper lead frame, got more of the heat out, and a lot of the problems, I don't want to say fix themselves, but move back into
Right, yeah, because
acceptable.
they got so hot, the part would slow down, and
Yeah.
that, we used to see that when before a heat sink, it would spark, the screen would start to sparkle.
Sparkle, right.
Yeah, a sparkle effect on the screen, it was just terrible. But,
Although
yeah.
I actively teach students to build the stuff, we use FPGAs and so forth, but one of the things I always loved about working on graphics hardware is that the bugs were visible.
Visible, I love it, yeah.
Yeah, you could just
Good
look
point.
at it, and it's, wait, that's not supposed to shimmer.
Right.
That's not supposed
Yeah,
to flicker.
Not supposed to do that.
So
yeah.
it's been true time immemorial.
Right, the difference being you didn't bet the whole company on it.
Right,
Yeah.
yeah.
Did we want to take some questions, or how are we doing on time?
We're doing okay on time. We've got another half hour.
Oh, do we? Oh,
yeah,
okay.
yeah. I've been pushing here, and it's actually worked pretty well.
Okay.
A very technical question I had is, so you have 8 sprites, period. Now, the TI-99 4A's chip, the 9918, I think actually had 32, but you could only do 4 per line. And it was doing much more elaborate DMA to sort of fill the shift registers and so forth. And so I'm curious why the architectural shift, or whether that was deliberate, or whether that was...
It was deliberate. I mean, it was a matter of, what I felt was if I could make a bigger sprite, okay? And that's where the idea of the interrupt on the raster,
Yeah.
that really was a thought process where I said, okay, if I make these things big enough, you can put a big enough article and you could combine 2 or 3 of them and get really something elaborate that you can move around. And then once you finish using it, then you can get an interrupt, change the pointer, and now you could have another one displayed. So having 8, again, was a function of how big I could make the chip, but then the raster interrupt function allowed you to reuse them on the second half of the screen once it was actually used.
Makes sense.
So I felt that, again, it was an architectural workaround, since I couldn't get more than 8 to fit on the chip anyway.
You could reuse your cloud sprite as a car sprite.
Right, yeah,
basically.
exactly, and that was just a single pointer, and change your coordinates, okay?
Now, were you sucking in the entire, it sounds like you were sucking in the entire
Yeah.
64-byte sprite, when? At the beginning of each line?
No, it was,
Once per
yeah, you had to,
frame?
I'm trying to remember.
Every 8 lines.
Every
you
8
would-
lines, right,
Yeah,
exactly.
you would slam
Every 8
out a
lines.
DMA.
Right,
Oh,
because you had
okay.
8, 64.
Ah, okay.
Right,
Okay.
Which is why then we went from the 1540 disk drive to the 1541 disk drive. The serial bus timing had to allow for the VIC chip to take over for that entire line at 60 microseconds, whatever it is. We go, me.
I'm taking over.
Which, by the way, the cruel mistress. She runs the chip. Once you set her up, it truly is the heart of the system. It's calling all the shots
it
in there,
runs it,
and the
yeah.
processor's just there to like, no, go left.
Yeah,
But it's the VIC chip doing the work.
Yeah, that was I mean, again, we defined
Right,
the
yeah,
hard,
the function.
that's what we were doing, and everything else was ancillary to that.
Were you no longer using the even-odd
we
cycle
were-
trick?
Yeah, but it still wasn't enough bandwidth.
Oh, I see, okay.
right.
So when it got really intense,
Right.
you said, okay, CPU.
Mine.
Yeah, okay, interesting.
Yeah.
Okay.
Yeah, he
Well,
won.
that's-
He always won.
Oh, right, okay, yeah. Well, that was actually one of the bigger things I was thinking about. So you did not put a 6502 in the Commodore 64, it's a 6410.
6510, yeah, right.
Or 6510, excuse me. And so, let's see. So one of the big changes was you could say, okay, 6502, you don't get to play with the address. Tri-state your address bus, so you could do it. So you could actually do the DMA
Right.
and all the rest of it. And it sounds like you could also tell it, wait, don't do another cycle.
Yes.
And so forth. Okay, so it
Yeah.
really did.
He really would stop cleanly, too. He
Yeah.
wouldn't stop and botch the last cycle. He'd go, okay, yours, yep.
Wow.
Yeah.
Okay.
Yeah.
So
that was the key, just because you just. it
Yeah.
was just
I was
so
doing
much
the serial
information.
bus, but sure, I'll stop and.
Okay, that
Yeah,
makes
so it
sense.
just hung it up, essentially, because there was really no other elegant way to do it.
No,
You know,
but
just
that
like
was
to-
elegant.
Well, yeah, it was the only thing I
well,
could come up with at the
Yeah,
time
it was-
that would make that work.
That was
yeah.
DMA in the modern sense of it, I would say.
Oh, yeah, it was, because it's like, okay, hold off,
Yeah.
and then start up again.
And you thought of it, implemented, and it worked, and you sold millions. I mean,
Right.
that to me
What's
is that
wrong
whole
with
chain of
Yeah.
events of
Well,
going.
that
yeah,
minor
it's
little thing,
Detail.
yeah.
Millions,
Yeah.
yeah.
Right, yeah.
Let's see.
Trying to think of something.
My mind is just blanked.
Yeah, I know, I lost my train of
Yeah,
thought.
yeah,
as well.
okay.
It's probably a lack of refresh.
Yeah.
Good, very good.
Well, I'm trying to be complimentary here, but, you know, it's,
Memory, where were we at? I
So,
forgot.
and you got the VIC-2, so the VIC-1 you got working in one rev, or the first rev worked, and the VIC-2 took,
Took two. Well, two, and then my deciding to make it 40 character thing.
okay,
Yeah, that
right,
was
I
great,
forgot
right,
about
yeah,
that, right.
Yeah.
nice little fix.
I think it was a worthwhile,
I think we all thank you
yeah,
for that.
I really,
definitely,
you know, yeah, it was definitely taking a shot, taking some chances, but, what are you gonna do, right?
So, one of the things that's cool in the Commodore 64 is you've got that quad bipolar pass device for the color RAM.
yeah.
So this was not a typical hardware engineer. I mean, we knew about this part. We loved this part, actually. But Albert built in, for the color RAM, instead of the logic that says, oh, I'm going this way, I'm going that way, is it your turn, is it my turn? He made it a pass device and said, if you can get there, it's yours.
Yeah.
That's basically what it's saying. Yeah. So in the 128, I looked at it and said, well, let's see what the logic would be like to make that a true, no, go this way, go that way, stop. And I looked at it and we could do it. And I said, no, it's better the way it was. And
It was so cheap.
it was one
It was
chip and it
so-
worked.
yeah.
And I didn't have to worry about compatibility
Right.
with the 64. So I was,
Yeah. So pass transistor is something that you get to use in a chip.
right,
Okay, it's the part,
just goes through, yeah.
the heart of what is the MOS technology. Or
So
CMOS.
what was in the color RAM? Is this the palette?
Yeah,
Yeah, the 4-bit color.
Right, 4-bit color, right, because
okay.
again, I didn't have enough bandwidth of things, and I said, okay, where am I
Sure.
going to get the color from? And we
Yeah,
stuck
so
it
he
on
made
the
it a
RAM out.
12-bit address bus,
Right.
basically.
Okay,
Yeah.
Right,
And that was connected up, I assume, to a little SRAM?
right.
Tiny
Okay.
little
Tiny little
2114.
one-
Oh, right, yeah, okay, yeah, okay.
Right, exactly.
Well,
Might
it just
take
sounds
my
like,
point.
it just sounds like nepotism.
Right, yeah, exactly. So we basically stuck that out there, but then we had to have a way for a processor to get it, and so the cheapest solution is a pass transistor. And-
Yeah.
And that
Is that a
way.
4066 or?
Was it the
The 4066,
Yeah, okay.
quad by,
Yeah,
Yeah.
the
Yeah,
quad,
the quad,
yeah.
quad bidirectional.
Yeah,
And
that's
so
great,
it's
yeah.
a really cheap
Yeah,
bidirectional
no,
buffer.
it's wonderful.
It cost me a penny.
Yeah,
yeah,
it was
yeah.
so
Quite
cheap.
literally.
Right.
Yeah,
Yeah.
well, they've been making them since the 60s.
Right.
Right, yeah,
Maybe the 70s,
probably, yeah.
And we're buying them in millions, so
Yeah.
it
Yeah.
costs.
So now I remember what I was going to ask. So you said for the VIC-1 chip, and I wish we had a photo of this. You said, 12-foot wide or whatever, where you
I
had
wish I did, too.
the entire timing
Right.
for that whole thing.
Yes.
For the VIC-2 chip, was that how you thought of the design and the DMA timing and all the rest of that?
Yeah, I did. And I actually, I made another big giant one. But
Wow, okay.
Because I couldn't figure it out any other way. I mean, now I did have extra small areas where we just had a sprite stuff and you watch,
Sure. Mm-hmm.
okay, now what happens if this particular sprite has priority and now you want to go over the background?
Right, yeah.
So I timed that all out, but it's small
Does
piece.
did you also not think in terms of choices? Well, I've got this memory slot, and I have this memory slot, but I could be reading this, or maybe I could be reading that, or something like that, or was it fixed?
It was a flow. I really looked at it as a process flow, sort of. I mean, almost like an instruction set kind of a thing, but a fixed instruction
Sure,
set.
sure.
But you had, okay.
Yeah, I'm picturing the 6502, the way it flows.
That's was what I used as sort of a
Right.
mental model as to how the
I
flow.
can see the left to right flow in it.
Yeah, I mean,
Yeah.
it was very much a 6502 architecturally, so essentially, you have a line, and then now you have, think of a line as an instruction set of things you're going to do at each line.
Okay.
So as the data's streaming out, you have this information that's going to say what happens at each particular pixel point. So that's what the flow structure looked like. Because in that way, it didn't, if I had the time, I could put more sprites in. Because
Sure,
it was a
sure.
flow structure rather than fixed in timing, and that I had these fixed structures. So that made it very malleable so that I could manage the whole thing. So
Okay.
that's why I architected.
Yeah, that makes good sense.
Do you remember the Ultramax?
No, I don't, no.
So the 64 is compatible with the Ultramax.
Okay.
So you build in Ultramax
I
compatibility.
didn't know that.
I know that because I had to build in Ultramax compatibility, so
okay.
you and me share something. Make an Ultramax mode, which
Okay.
was like a 2K RAM only as this
Oh.
oddball thing.
Oh, I didn't know that.
Yeah, yeah.
That's interesting.
Because we broke it one time. That's how I know it's.
That's how you know that.
Dave, you remember breaking Ultramax mode?
Oh, yeah. It was pretty much all the PGA, right?
It was in the PLA, yeah, it was one term, yeah.
Yeah, which wasn't really PLA at all.
Yeah, we made it into 48 pins, the PLA.
Oh, I know you did. Yeah, that was a good
yeah.
idea. I mean, that was another thing.
You didn't have 48
there were
pins
48
carriers.
pins
No.
did not exist then. It was
No.
40, that was it. There was nothing bigger than 40 pins, so that
So-
was another problem.
Right, and we talk about like the colors, you know, I get, why only 16? It's like, we didn't even have the pins on the VIC chip for more.
No,
Let
that was-
alone the room and
Right, yeah.
everything like that.
And also it was you have a 4-bit RAM, how many colors? That's
Right.
basically all you get, you know?
So,
Yeah.
and I've been asked that about the 128, why didn't you do it? And my answer that I actually would have busted the VIC chip, and by that I meant we couldn't have just added some stuff in the color area. We would have had to expand the size of the die, start moving things on the VIC chip
Right.
to include a 4-bit data path. And then if we had an external 8-bit RAM, we would have had to make 4 bits of it go away in 64 mode, or it would have been incompatible because people wouldn't load and 0F.
Right.
They would just load it and expect an F to be in the top.
Right.
Right. So we would have had to break the RAM to do 64 mode.
That backwards compatibility is a pain in the butt.
Yeah, yeah. So people said, why didn't you do it? I said, I thought about it for all of 3 seconds and said no. You know, and I figured it would bust the die. Right.
Yeah, I mean, yeah, because it was packed.
It was packed.
Yeah,
Yeah,
it was-
Diora used to show me. I mean, because you can tell the additions. They're kind of around the edge. You know? If it's on this side of the pad, it's an addition. Yeah.
Right, yep.
So here's the color circuitry, or the color circuitry on the outside. So
Right,
you've got,
as it comes out.
I never get tired of looking at this. And this is before the modulator was heavily customized for us.
That's right, yeah,
Yeah.
yeah.
yeah, so so you've got just the brightness coming out,
Right.
along with the sync signals, and then the two-phase color stuff. So the two-phase color stuff was this, again, the resistive ladder, and what, you have like 2 bits, 3 bits of,
It was 3 bits, I believe, yeah, 8.
okay,
yeah.
8, okay.
Yeah.
Sounds good. And
Yeah.
was the brightness just 1 bit, or did you have multiple?
No, I think there was grays in the color mix. There was a
Oh,
4-bit,
okay.
so there's
Oh, okay.
grays in the color.
Okay.
Okay, so there's.
2 grays,
There
maybe?
was 2
Two
grays.
grays,
yeah,
black and white.
Right,
Okay,
yes, right.
okay, so
yeah,
2 bits coming
Yeah.
out. Neat.
Yeah.
So, yeah, in the TED, we tried to shoot for 128 colors, but 8 shades of black is still black. So
Yeah, yeah.
It's still,
Well, it's
palette
like the
stuff.
blue against the blue flickering, but you can't tell because it's blue.
Blue.
Yeah.
Right.
Yeah.
Yeah. Yeah, that was just, I mean, tailoring, just trying to tweaking that circuitry to get it all to look good on the screen.
Oh,
And-
sure,
And
yeah.
to be compatible with the modulator that we purchased at
Right.
the time. And so had to feed it exactly what it wanted to see.
Wow.
Because that was the Blackguard RF stuff.
Yeah.
Yeah.
Yeah, well, originally, didn't the VIC-20, not the modulator, you had to have an external switch. Oh, maybe we did on the 64 too.
For,
Did you have there was a point in time where the modulator had to be external to pass FCC, and then they changed the rules, and I'm talking way out of
that's,
the timing. my
that's
time.
certainly not in the 64. Maybe the 20,
20,
because
I
again,
was
that was done
thinking
in
the
Palo
20.
Yeah,
Alto, so I wasn't
Right.
involved in
Yeah, I think
the details of that.
The 20 never had an internal modulator
External
in it?
modulator,
Yeah,
yeah.
yeah.
It
would
may be.
only do.
Yeah, right, yeah.
Okay,
Yeah.
yeah.
It does? Okay, thank you.
Yeah, but yeah, no, that was my understanding as well. At some point, somebody paid money to the FCC and suddenly you could put
That's my
modulators.
understanding
Yeah,
also,
yeah,
yeah.
it's pretty clear.
And then Mitsumi paid money to say, yeah, we'd like to be qualified to be part of this mess, yeah.
Yeah.
Right, yeah,
Absolutely.
yeah, so that's the good
Let's
stuff.
see. So we've got another, I guess, 13 minutes or something like that. Maybe this is time for audience questions.
Yeah.
As much fun as it is to
Yeah,
chat among the three of us.
there's usually a half an hour's worth of questions.
Yeah, yeah.
So-
Hang on. Hang on.
To look at the illustrations of the die, the VIC and the VIC-2,
Yeah.
it's obvious the density is much greater on the latter, as it would be expected. What kind of geometries were you able to produce at that time? I heard earlier that the yields were on the order of 20 to 30% in initial run, and I know this is a consumer product, but it looks like everything is crammed down to the last micrometer to get that VIC-2 created.
Yeah.
See, this is the kind of question you get at VCF.
Right.
How did he even know to ask that?
What kind of rules were you like one or something like that? I can't remember.
No, it was point. This is funny. This is before metric. Okay.
Right. That's why I'm confused.
It was 0.3 mils or 0.35, and then we would do a 10% shrink.
Shrink,
on that.
right.
Okay, so I think it was the smallest geometry we could make was 0.35 mils, which I can't do.
Somebody look that up in
Yeah,
micron.
I can't do the micron in my head.
It's got to be.
I've forgotten how to do that.
It's got to be
Used
like in the
Because
4 or 5.
254
something like
is
that.
the micron.
Yeah,
right?
yeah. So whatever it is.
Yeah.
So it was 0.35 was the smallest one we could
So
do.
this was so big, it was still in imperial units, I think is what it is. To sum this up.
Well, maybe going in the other direction, when you started the chip design out, you didn't work from geometry because that comes down to manufacturing. What kind of transistor budget do you have to work with now?
Okay, that's where you tried to create block structures so that you could manage that. Okay, I knew how much of a RAM would be, and what space that would take up. I knew how much a counter would be. So you would do an architectural overview of this and say, okay, I can only make this chip on the side or something like that, 210 mils on the side, right? So you start laying these things out, and you do it for enough years, you get a sense of, okay, a counter's this big, and I need this many counters. So you could start to lay out, just like you would lay out a house.
Right.
You go, okay, this is how much I need for the living room, and this is
Or a printed circuit board.
right. I mean, so you get a sense of it from that perspective, and that's where we did it that way. And I knew approximately, or before starting, I would be in that rough range of where I would be. So it was really experience that told me how big I could make it. But again, it's cells, so I knew how big a cell was.
And the longer it went on, the more you knew.
Right.
Yeah.
Yeah, I mean,
Were most of the transistors minimum size, or were they all over the map?
the internal stuff is mostly in minimum size.
Okay.
So it wasn't until you got to like clock generators or the
Right,
analog
right, okay,
sections.
that makes sense.
Yeah,
Yeah,
so that's why you didn't have as much, I mean, you would ask earlier about checking the transistor sizes. I never wanted to do that. They had to make sure that the logic was the logic, and you tried to get away from that, and you knew you had the speed to get through it, and
One
only
of the
when you had to.
changes Diorio slid into the VIC chip for us then is we found a game that had flipped a mode. I don't want to say flipped it to PAL mode, even though it was an NTSC. Something you or I would not think somebody would do on the fly. And the transistor was a small transistor, and it took almost the entire line to switch. And so you saw the RAS get skinnier and skinnier and then finally go away. And of course, it ruined every DRAM content of the thing.
Right.
And Diorio looked at it and said, nobody ever thought it'd be switched dynamically.
Who would do that?
And he made it into a 207 or something.
Right, yeah,
like
some
that,
big transistor to drive. I mean, that's the kind of things you don't think about, because there's always
somebody
somebody
does
in
it.
software poking it. What this would do?
Right, right.
And you don't think about
And
it.
then we got stuck on, and if you don't do it too correctly, because for some reason
Right,
our VIC
right.
chip acted different, then you're not compatible. So we had to go in and make it so you could flop these on the fly.
That's yeah. You don't think of all
In
those
many
little things.
respects, I feel like I'm responsible for this. As a member of the teaching world and so forth, what our students do is, we give them an assignment, they code it, they run it, it doesn't work, they randomly change it, they run it again, and so forth. And as soon as it works, they turn it in and they move on to the next thing. And so I'm sure it's a similar sort of thing. It's like, oh, was this a good idea to do? No. Did it work? Why, yes. Okay, ship it.
Oh, I remember the 3 seconds it took me to make a decision on things and then move on.
Yeah,
We
yeah.
simply didn't spend, and we weren't IBM where you needed to call a committee meeting and,
Right.
and do that kind of thing.
Yeah, that was the fun of
It was the fun of
back
it.
then.
Yeah.
I mean, everybody was a startup. I mean, really, even though Commodore was a little bit bigger because it had the calculator business, but because it was a startup, you had freedom. I mean,
You got to make decisions.
yeah, and it
Yeah,
was never
absolutely.
a committee. Yes.
So one thing I always wondered about is, like, I understand the limits of the 4 bits leading to the 16 colors, but how were the 16 colors decided upon? Right.
I told you you'd get that question.
Right, because if you look at like the history of games, the colors are used in very different ways, right? There's a kind of black background period. There's this kind of embossed period where you use the light blue and the dark blue.
It was somewhat serendipity, okay? And there were certain ratios that would fit and that would work. Okay, honestly, this was sort of like driven by the hardware.
And some look like crap.
Yeah, but I didn't, I mean, I had 8 to choose from, and like, okay, this is how these resistors, and there's enough separation from one to the next, and from a perspective of the manufacturing, they would be about always the same. So it was a situation, I knew I needed the primary, so I had to fix those. And then after that, it came down to what was left.
So is it phase angles that would play nice together?
Yeah, exactly. Exactly.
And enough room for the ones left.
Yeah, and so it was serendipity, those, you know, once you get through the primaries, it's like, okay, what can I squeeze in here? Yeah.
Part of the trick also is you have to remember this was aiming at NTSC, and you know, there's a similar story for PAL. It's equally twisted and so forth. But RGB is a modern invention, right? At the time, you know, it's what is it? YIQ is the space or whatever, and it's nothing like anything you'd ever want to design as a human being. There was a whole bunch of, you know, how can we make this and do it and all. So trying to get a pure color, you know, just red is ferociously difficult. Yes. And if you look at all of the machines of that time that would display on normal, none of them have red, really. None of them have blue, really. It's all weird combinations of all the rest of that.
This is the days when TVs had tint controls too, so you would make the colors be whatever you want.
Right.
Yeah.
Well, that's why it's called never the same color. Right. I mean, there's a very good reason for that.
Right.
I like it. That's good. Yeah. So, I mean, when I first read about it, as I said, I wanted to put color in. I was in the library and read about all this, and I went, "You are kidding." I mean, because as a digital guy, you go, well, "Why isn't there an R and a B and a G, and I could just change the way we have it now?" It's a much more sensible solution to the problem. But you know, going from black and white to color, and this is how they squeezed color into and be backwards compatible with the old color sets. Now, I think the person who came up with it was demented, but that's what they came up with.
Well, it was actually a backwards compatibility problem.
Yes, correct.
Right. It was how do you broadcast color and make it work on a black and white set?
So it wouldn't impact it. It's the same shimmering problem I had.
Yes.
Similar.
And they built in different relationships to try and counteract those.
Exactly. So it was really okay, once I get red, yellow, green, and a few of those, blue, then it was like, okay, what's cyan came up.
And orange is problematic because it's so close to the color burst too.
Yes.
Yeah.
Right. So it was. You know, I know I needed a few, and whatever fell out after that was sort of where it landed. Unfortunately.
Just compare the colors available on the C64 to that on the Apple II, and you'll suddenly realize what paradise in the Commodore world is by comparison.
I just wanted to add real quick that in the broadcast world, there were certain colors that were illegal that would tweak out television sets, and red was actually one of them. It has to be a certain frequency, otherwise TV sets get kind of messed up. They used to
tell them not to wear red suits, and even Santa Claus outfits on TV were bad.
This is like the brown note, but a visual thing or something? Yeah, okay, yeah.
How about that? I didn't know that.
In fact, I have this history. So let's see, before the opening credits run in Blade Runner, there's this red thing that comes on. And it's taken about 30 years before I could actually see that on any of the TVs that I saw it. And it's exactly the red. So you've confirmed what I've suspected all along. Red is out to get you.
Right. That's right. That's right.
Any other questions? Yeah, usually you guys got a lot of questions. Just shout them out.
We've covered a lot.
Yeah.
Try to, yeah.
Let's see, I'm trying to think if I have any questions.
We've talked a lot.
We've talked, Albert and I have talked some 6-7 hours now, and it's always new stuff we're talking about, so we've pretty much exhausted that. We played did you know this guy? We played that game.
It was a good team. I mean, there was another guy, Jim Redfield, he was also, mentioned him, he was a guy who really helped me with all the logic of the flow between the background and the sprites. He was really instrumental in helping me get that right.
So, and you guys were working without ERCs or DRCs, electrical rule checks or design, and this is real important. They would draw a schematic, and there was nothing that said, yeah, we made the chip like you made the schematic.
Right.
It was all hand-checked during that time. And when Jim Rebfield came back to Commodore, somebody pulled me aside as he walked down the hall and said his Sprite collision logic worked the first time. You know, and it was just that was just wow.
Yeah, there was a lot of it was just you had to keep things simple, but yet keep them flowing.
It had to work. Yeah.
Had to work. I mean, you really didn't have any choice, but you couldn't get. I mean, FPGAs are so wonderful now. I mean, you can just try things and. Oh, if that doesn't work, let me try something else. And you never had that luxury. Another story about when I left Commodore, okay, they gave me a very large pair of dice as I was leaving. Why would they give me a big dice? Because what I would say is after about a month of checking it, okay, I go, listen, let's just roll the dice and get this thing the hell out of here.
It's tempting too. I've watched chip designers wear out a brilliant person after 3 months, and they're like
you're just beat up, and you go rolling the dice and see what happens, because I'm tired of checking this damn
right.
thing.
Yeah, and so we got into a thing where we started revving the chips. We went to, well, in all fairness, chips got smaller and more complicated. But we were starting to do 3 and 4 revs to get chips to
Well, yeah, I mean,
work.
as your complexity goes up, you have no choice for that, because you're trying to do more, and then that's. I mean, I always look at it as we were designing computers to help us design computers.
Yeah.
Yes, I mean,
Yeah.
Yeah,
No,
I mean,
that's what you had to do, definitely.
absolutely, and but it was fun, because I mean, back then, you think about it, and even today, I mean, you can do a custom chip today, or you know, a Sea of Gates kind of thing for $100,000 or less, really. Okay, custom.
Maybe,
okay,
yeah. It would have to be
There's
Seagates, but yeah.
and there's
Sea
free
Gates.
programs going on too. Google will shoot your chips for you.
Yeah. So, but back then, I mean, the cost of producing that even was in the
$250,000 for a half lot or a lot.
Right.
Yeah.
It was crazy, and that's why it was like, okay, you had to do everything to get it right, but it was a shot in the dark. I mean, you just had to go, okay, I'm going for it, you know. And it was some sleepless nights between when you said ship it to when it came out.
We would take the chip guys out to the bar and just like, here, sit down. You know, you have to wait.
it was nerve-wracking.
Like being pregnant.
It really was. But there was a pride in the fact that, you know, you spent all that time, and it was always that pride of saying, okay, I'm going to get to work in 1 or 2 revs. I mean,
right.
That was always the benchmark of a chip designer at the time, is getting it work in that period of time.
Remarkable.
Yeah, but
it was truly remarkable.
It was fun stuff, you know. Thank God I don't do that anymore. Yeah, I mean, I just did, the last chip I did, I did a chip about 3 years ago. I'm still working. I'm in consulting and things, okay? And it's a whole different world. Everything is standard cells, or, I mean, this had some analog stuff in it too. But again, it's like, with all the EDA and checking ERC and the simulation capability, I mean, the only thing that didn't work the first time was some of the analog stuff needed to be tweaked.
Right.
So you have another rev to tweak the analog stuff, but because you have so many tools at your disposal, you can get it almost perfectly right the first time around. And if you don't, then you're really not using the tools well. You know?
Well, the stakes have also gone up, right? You know,
agreed.
$250,000 or whatever, like, you know, what is that? You spend that on one mask now or something?
Yeah.
One of the tricks we were doing, the chip guys, was we called it a 1, 2, 3, where there were 6 layers total in these chips, and they would divide the lot into 2 and only do 1, 2, 3 on the whole thing and save it. And so if they had fixes that they could do in the top 3 layers, they would do that, pull out the 1, 2, 3s, add 4, 5, 6 to it, and run it again.
Yeah, absolutely.
I had a 4, 5 6 save my life. It threw itself in front of the bus, you know, and literally saved us for CF. So.
Yeah, that would be definitely.
Well, that's why we have gate arrays.
Yeah, exactly. Exactly. Yeah.
And we had gate arrays the next year. It was pretty funny how, you know, when people ask me questions, well, why didn't you do this? And it didn't exist for another year, another 2, but it existed pretty soon after that. You know? But things were moving fast.
It's a fun part of doing it.
That's
It really was. Yeah.
Well, speaking of moving fast, I think we are officially over
Okay.
time at this point, but this is wonderful. Can we thank our panelists here? Thank you.
She had something on it there.
Did you bring that dirt with you?
I think I did, yes.
Uh,
Actually, I think my shoe was deteriorated here.
So the Intel back in, do you remember when Mount St. Helens blew up?
Yes.
Yeah. So they started doing stuff like walking across gummy tape and stuff to clean up because the dust of St. Helens got into the process.
Yeah.
And so that's what that made me think of. That's how warped I am. I saw the dirt and I thought
Yeah,
about
they know
St.
it's from my
Helens.
shoe, actually.
Oh,
I'm surprised you didn't talk about this. This is before the Big 20.
Oh, jeez.
I completely forget about this
that's-
till doesn't it have an IEEE on it or something like that?
That was released in Japan in the 80s.
Okay.
Before the Big 20 came out in America. And that's a Big 1001.
Wow.
oh, yeah. Yeah, they went for the Japanese market first. That's
Yeah,
wonderful.
see, this got passed off to the guys in Palo Alto, so I wasn't, and then that moved to Japan.
But that was based on their design.
Yeah.
You designed that.
Yeah, oh yeah, they just took that along, exactly, yeah, right. And it was, but they had more manufacturing facilities in Japan, but.
Oh, that's what gave us the rule of the world was we manufactured in Japan back in the days of transistor radios, being Japanese.
I would do it, but I can't. Just more contact, dude.
Yeah.
Fun stuff, though. It was a long time ago. Neighbors here, I think.
Feel free to adjust these as you wish.
Amiga chips. Okay, so you get an idea of the kinds of questions I'm going to ask.
Yeah.
You have good diagrams? I have some. Here's what I have. So Phil's not actually. So here's what I've got. Going, we've got these very early ones, things. Sorry?
Oh, those lights, yeah.
We look at each other.
Yeah.
Where's the sunglasses?
Sorry? Yeah.
I actually have mine. I
Yeah,
have
yeah.
some in the car.
Yeah.
I didn't plan for this.
You've heard the expression being in the limelight. Well, this is what's going on here. So this is some very early ones. I think you posted these.
Yeah.
Probably, yeah.
Yeah.
And,
Oh, the boards.
Yeah.
The prototype boards.
so about the 1,000 screenshots
Yeah.
and so forth. I mostly talked about 2000, which you were involved in.
Yeah.
So forth. I have one of these that
Yep.
doesn't work, but anyway, so this was where I had the service manual. So this has these diagrams in it and some of the inside sections and all this programming manual.
Oh, you get a lot of. Yeah.
I think I've got it.
Yeah.
Let's see, I very little about the sound, mostly about the graphics. But I was going to ask you about the building modify stuff.
Yes.
The
Yeah, well, of course, it's, you base your new thing on, on what you learned from the previous one.
Yeah.
So
the copper is straight off of the.
So Jay was able to correct all of the flaws from the Atari and make something better. Yes. And in fact, that this didn't come out to the world, but we had the AAA system, which were kind of similarly. This one just opened.
Is that one open?
Oh, is that a? Oh, yeah. Okay. Sorry. Yeah. So. You said you could, yeah.
I said I could. This is just.
Yeah. I haven't seen that one.
No, this is from the first NCC show in Philadelphia.
Oh, wow. Okay.
Long before I worked for Commodore.
Yeah. Oh, really? Wow.
I bought it. I had a Tim 1.
Yeah. Yeah. When I was in high school, two friends of mine got passed, and I was actually programming with them. That one I've seen before. Yeah, that was the logo from. They had the same logo on the mouse. I had Amiga mouse for a little while.
Dave, were you involved in the prototype of the first set? Those big pile of
No,
boards and
no, I know about them, but no, I started on Amiga. I started on the system, on the A500 system a little bit, and then I moved to the 2000. So I was, I did systems for, a little bit on the 500, 2000, 3000, a little bit on the 4000, but I did the thing that led up to the 4000. We had a thing called the 3000 plus, is where the Pandora chips, which everyone calls AA or AGA, depending on who you are. That one, that I basically proven the whole thing, got it working, and then new management came in and changed the computers all around, and then on to AAA, which was which had actually started in 1988, which advanced Amiga architecture, which is the one which could give you 32-bit or 64-bit graphics and all kinds of stuff that never got out. It was a 4-chip set that could also live as a 6-chip set in a 64-bit edition. I built a prototype of that basically just to prove out the chipset. And that was about the time Commodore was running out of money, and we never got Rev 2, if anything. Those were all made outside of MOS because we didn't have we could make 144-pin chips. Oh, sure. This was 4 or 6 144-pin chips. So I was basically there until June of '94, which was a few months after the bankruptcy.
Okay, and so my plan is more or less, you want to just start off and talk and present what you
Yeah, sure, but you want to do some sort of introductions first? Or,
Yeah.
That's the...
Yeah, exactly.
Okay. We'll see if I can go through what I timed out in 22 minutes beforehand. We'll see if I can do that in 5 minutes.
All right, there you go. Just power through it. That's
I'm
great.
afraid I might do that.
Oh, it's great.
accidentally.
It sucks. Okay, I may slow you down if that's that much of a danger.
True.
Fix the slide rebuilt copy PDF back then.
Okay, okay. It's, hey, you know, hey, it's, good thing that's allowed at a retro shop. Okay.
Yeah, no.
Go over 15 minutes.
Yep, okay. Yeah, we'll see how many rabid. So you're. It can happen, definitely. So you can introduce us then? Yeah. Perfect. Great. Right, right. Yeah, you just say, you know, Stephen Edwards teaches at Columbia University. I'm just this guy. So I was doing a little bit of reading about the Boeing demo since it's so iconic and so forth. So I was going to talk about that a little bit. Do you know about the details of how that was actually implemented? Or?
Moving viewport.
Yeah, it was.
And the sound was Bob Pariseau banging on a garage door, recorded. Let's see.
Yep.
It was 256 bytes for the instrument.
Okay.
And 16 bytes for the envelope for that thing.
Okay. Makes sense.
That actually happens to be on one of my cards.
Nice. Okay. Perfect. Yeah. No, that's perfect. The other thing
One
was that the
1 minute, guys.
spinning
1
was
minute.
actually done from just palette color cycling.
rotation, yeah.
Okay.
Color cycling.
Yeah. So in fact, it's
Ethan.
somehow all a fiction, but it's still
Ethan.
cool.
We ready, right? Okay.
And Robo City was done entirely in sprites.
Robo
City
City.
was done in sprites.
Oh my God. Okay. Yeah. Okay. Oh, I wish I had a screen dump of it. Yeah. I've got a handful of things. Yeah, the big question. I don't even know this. Sort of how much was done with multiple play fields versus splitting or something like that. I guess the answer is all over the place. But
You just have to know who did, you know, how it's done.
Okay.
You know, the screen sliding up and down, that was multiple playthroughs, and that's pretty much what we.
Well, some games probably used it.
Okay, everyone, for our next talk,
Never know.
we have our interviewer,
You're still- oh.
Steve Edwards from Columbia University, interviewing Dave Haney and Andy Finkel, Commodore engineers, former Commodore engineers, talking about Amiga. Thank you, guys.
yeah. So this is wonderful. I get to sit next to Commodore Amiga hardware and Commodore Amiga software, and we'll ask it. So, but to begin with, Andy, you've got a bunch of stuff prepared on the history of how Amiga came into Commodore.
Yeah, sort of.
Right? Okay.
Sort of.
Great.
So Bill Hurd asked me to do this a couple months ago, and I figured, yeah, I do these all the time, so I'll just riff on something for half an hour or whatever. And a couple weeks ago, I realized, hey, I haven't done one of these things in like 10 years, 20 years, so I'm kind of nervous. So I actually went ahead and prepared something. So I'm not riffing. I looked up like 2 weeks ago on the VCF website for what this whole thing was about, and I said, Amiga custom chips. I had no idea that was what they wanted me to talk about. So, and at this point, it's been like, you can Google anything you want to know about the Amiga custom chips that I could possibly tell you. And in fact, to prepare for this, I would have had to Google it myself. So I just different because, well, I wanted to do something unique, something that you can't get from the web right now. So now for something completely different. I came up with two ideas. One is the history of Commodore through T-shirts. I have a really extensive T-shirt collection from, like, here's one of the original Commodore T-shirts. This was before, well, anyone knew anything. It says Commodore supports its floppies.
Is it me or is that shirt small?
It's small. And it's not in men's style either.
I didn't know if it was the
Yeah, Commodore, light years ahead. Ooh, let's see. But I decided that, you know, that's, have you seen the Amiga, you know? Commodore was not really great at coming up with original T-shirts, I'm afraid.
Commodore in the U.S. had worse swag. You go to Canada, you go to Germany, you get some great swag. They had all kinds of stuff.
And this is a classic. God, isn't this exciting? It offends almost everybody. So I rejected that idea after going through, you know, just a few of the top ones.
Do you have a Jackbusters t-shirt?
I have a Jackbusters t-shirt. Let's see if I brought it. Yes, I did. A classic. Wow. Very few of these actually exist. And Jack actually knew we called the game that. You know, he didn't mind. So my other option was to tell the story about the Amiga acquisition from the Commodore point of view. The Amiga acquisition was like a deep, dark secret, done very fast, well, even by Commodore standards. And Commodore time was not like any other time. I mean, we did so much so quickly. It's like amazing how fast something like this happened. I think it was like from May to August is when the entire period of buying the Amiga and integrating it into merging Commodore and Amiga.
So what year was this?
1984.
Okay. Yep.
Yep.
That's a scary thing.
It's
so you were at Commodore first.
I was at Commodore. I was in Commodore forever. I was, you know, started with the VIC-20, then went through the Commodore 64, went through the Plus4, went through the LCD machine, went through the C128. There's probably a couple others I'm forgetting.
Dizzying collection of them. Okay.
It was a lot. So it's been like 40 years, and you know, trying to figure out and remember the exact schedule of when things happened, that's something I'm not usually good at. But in this case, I have high-tech weapons, engineering notebooks. Back then, every engineer had to keep engineering notebooks. You wrote everything you did on them. The pages cannot be removed without getting a mess. And I actually have all the engineering notebooks from that period. So I can actually tell what happened when. I worked for Sig Hartman back then, and I was I was manager of the application software group, but I was also his technical go-to guy. So I actually got to hear about all the high-tech things because Sig wanted to find out and get opinions about what other managers and division heads were telling him, whether it was real or not. So I would hear about a lot of things. I would actually go to engineering meetings, even though I was in the software division. So I got to hear a lot of the backstory behind stuff like this. So let's see. Got that one. Okay, so this was just before any of the Amiga stuff happened. On May 21st, 1984. Marshall Smith was the big boss at the time, if anyone remembers him. And this was from an engineering staff meeting. We were doing a product review. Top 4 projects at engineering at the time were the C128. It was due first quarter 1985. The PC, it was due the fourth quarter 1984. The Z8000 machine, that was due the second quarter 1985. And the LCD machine, which was due sometime in the future. And at that point, we started looking at or talking about next generation machines. So we scheduled a futures meeting. I don't have a complete list of attendees, but we were looking at what we can do next after those 4 projects were completed. And at that meeting, we decided our main target, our focus, was to beat the Apple IIc. That was at that point, we decided that was the biggest threat to Commodore. And I guess at that point, at that meeting, I got a really annoying question, which, what can we develop to start, what do we need to start writing the software for a new machine before the first prototype is built, or even designed? Because right now, back then, they decided that software was the problem. That was why we were always so slow at bringing out new machines. You know, if we could only get the software done first, then it would simplify everything.
It's like the negative time latch that would solve all kinds of circuit problems.
Yep.
Okay, yep.
We could fix the problems in hardware via software before the hardware even exists.
There you go. You wouldn't even need the hardware.
The strange thing is, this is how it's done these days.
On June 8th, we had a senior engineering staff meeting, and Martin Shabilsky, who is Adam Choniak's go-to guy at that point for technical stuff, who I actually later worked with, he's a good guy, he gave a competitive analysis of all the other computers around and all the rumored computers. And that was the first mention anyone in engineering had heard of the Omega computer, with an O. And so we heard about it. We thought it had some interesting features. So I was given the task of researching it. On June 12th, 1984, there was a general managers meeting in Europe. Word came back, or panicked word came back, that the GMs demanded a new machine for Christmas '85. They weren't happy with the projects engineering was working on. They wanted a 16 or 32-bit CPU, an 8-bit bus, and 64K of RAM, and a graphics processor with bitblit and raster ops. And because they were all disturbed by the Sinclair QL, which was going to take the market by storm. We couldn't compete. None of our current machines would compete against that. And so they were very concerned. But we were already doing, okay, in the staff meeting, decided we were already doing 4 machines. We just didn't have the resource to do a 5th. So we needed something short-term that we didn't really mind if it became an orphan product, you know, not part of the Commodore family, not compatible with anything, never to be seen after this one Christmas. So we decided that the only way to do that was to buy the technology from the existing group and help them get it to finish the product. If they picked the right CPU, we could at least stick with the CPU for future stuff, but we didn't really care. On the 19th, you see how fast this is running? We got the full specs of the Omega computer. It had a 68,000, 7.5 megahertz, 128K of RAM, expandable to 512K, 64K of ROM, custom animation bitblit, display sync coprocessor, 640 by 400, high resolution with 3,016 colors. No one could figure out how that came about. 8 reusable sprites, 80-column color text with 40 columns on a standard TV, custom sound peripheral chip with 4 voices, 9 octaves, complex waveforms, AM and FM, disk drive support, and it would run PC-DOS, MS-DOS, or CPM86, and it was going to cost $300 once it hit mass market. Its target was the Apple IIc again.
How are they going to run MS-DOS on a 68,000?
Not
Did
sure.
they tell you? Okay.
This was the word from Amiga that got back to us.
Oh, okay. So this is like marketing.
Marketing, yes. Well, this was, you know, we hadn't actually made a deal. We were just just finding out. So let's see. When we briefed Marshall on this, I was in this meeting. He wanted to be first with a 32-bit machine. We said, well, 32-bit system's not possible because of lead times. It requires a new software base. So he said, well, what if you got rid of the custom display processor? I don't know.
Well, obviously.
Obviously. Okay, next on the 21st was a meeting with Jay Miner. This was the first actual physical contact with the Amiga folks.
Now, Jay, though, is actually like an engineer and not a marketing person, right? Or was he somewhere in between?
No, Jay's a chip designer.
Yeah, exactly.
So we were at the point of, let's find out what this really is.
So you might actually get some straight answers. Wow.
Right,
okay.
exactly. We went into the meeting calling it the Omega and came out calling it the Amiga. Jay corrected us. Embarrassing. They were working on a home computer, mouse-based. Their company at that point was 20 people. They needed, they needed 20 people. They had about half that, and they could find good uses for about 50. The big issue was going to be the software, which, you know, it always is.
Funniest thing.
Funniest thing. But it looked like a good direction, so we started the process of like figuring out how we could buy the Amiga. And when we got back to Westchester, everything seemed to be quiet, you know, moving along. The rumor mill hadn't started spreading the Amiga yet, but we were studying everything we got from Jay at that point. On the 5th of July, we had a project review meeting. C128 was C64CR, Z8000, and the LCD machine. All of them were on track except for the LCD machine. But there was one minor thing at the end of the meeting. We were starting to recruit in Westchester and Santa Clara, advertisement in the small ad in the San Jose Mercury News, looking for ex-Atari people for some reason, specifically. And we started internally, a couple of us started reviewing the Amiga chips. See, on the 17th, we were reminded by the general managers who talked to Adam and Sig that they demanded a 16-bit machine, but this time they wanted it in the middle of 1985. They moved it up from Christmas. And again, the target was Sinclair QL. Amiga still looked like the best candidate. This is on the 17th. This is our first meeting with Metacomco. Everybody remembers Metacomco, BCPL, Amiga-DOS, right? Okay, this was actually, we met with them on something entirely different. We were actually looking at trying to pitch us an OS for the National 3216 chip. You remember that period?
Oh yeah.
That was supposed to take over the world.
Yes, it was.
National. They also had graphics chips with the.
They made like 5 of them.
There were too many 32-bit-ish chips around then.
So we met with Derek Budge, and he gave us this lowdown on Metacomco and so on. Tripos, they had 18 people. They had a Pascal compiler. They had BCPL, and they were using Lattice C to port their Tripos to the Sinclair QL. And that really made it a win. So we actually liked them. So we actually started a contract with them to do something, but not Amiga. It just, this is how we met them. We continued on the 18th. We talked to Bob Pariseau, and he gave us the lowdown on the software and the status. We kept looking at Amiga hardware, and at this point, we brought the lawyer into it, Nick Lefevre. Amiga patents, Amiga patent infringements, all sorts of things. That got kind of messy. And we talked to Jay with our chip guys to investigate how to get the Amiga chips into MOS's process. You know, they were looking at things like the SPICE model, differences in processes, getting test tapes to MOS, the differences in design rules, metal pitch differences, all that stuff that, you know, necessary for MOS to actually consider making the Amiga chips.
So I imagine they breadboarded it at that point. Had they fabricated the chips for the first time?
No.
Okay.
But there was a breadboard, a functional breadboard, pieces of which still exist.
Mm-hmm.
Okay, we also got, at that point, finally, we got the full Amiga specs. And we were able to actually start costing out the machine. Elroy Schoenfeld was able to start looking at how much it would cost us to actually build this thing. And I started looking around for application software for the machine. who was working for what, because Amiga had actually reached out to software developers, third-party software developers, and there were already people who, you know, were thinking about the Amiga, working on it. Come to think of it, there were chips at this point. I'm sorry.
Oh, yeah.
Yeah, there were chips.
Oh, wow, okay.
Yeah.
Yeah, that was, yeah,
I'm sorry.
mid-'84?
Yeah, mid-'84. There were
Yeah,
definitely
would've been
chips there. I don't.
Oh, okay. Mhm.
Yeah, they were at the, I guess they were at the Zorro backplane,
Yeah.
Zorro motherboard by then?
Yeah.
In the black metal cases.
Right.
Yeah,
right.
yeah, that
They
was,
were
that was
black.
the, yeah, that was the one after the Lorraine.
Right.
Or was it
So
before?
it was
Yeah,
a
I
wooden
didn't- yeah, it was
keyboard
the-
and black metal case.
Yep. Yeah, that, and some real prototype chips with
Right.
different names.
Right, different names, different names. So, let's see, we continued to evaluate the Amiga chips. We started putting more people on it, like Madeline Shaw. And I was given the task of designing, roughing out a C64 success chips. So, let's see, what game should we port? Should we do a cartridge or disk? You know, little questions like that. I was give, you know, 32K ROM.
Minor little decisions.
So, yeah, I was going to go with 32K ROM, graphics library, sprite library, sound library, maybe animation, who knows, text routine, and disk. And I was going to expect the developers to treat it like a 64, you know, hit those registers directly, because that's what they want. They want. At the 25th, we've got our first full Amiga memory map, and I realized that that was stupid. We're not going to be able to hit the registers directly. On the 27th, we bought Metacomco a Sage computer because we wanted them to start thinking 68,000 at that point. Okay, 29th, it was time for the trip out to Amiga. Martin Shabilsky and Madeline Shaw were the people who went out there to actually meet with the engineers except for the first time, really, because we were going ahead with this.
Where were they physically?
Well, Martin and Madeline were in Westchester, and the Amiga people were in Los Gatos.
Okay.
Yeah.
Yeah. So let's see. We prepped Martin with questions for the trip, like how do they do color area fill? Are there enough cycles to change the sprite width? Why is the mouse light? You know, little things. Oh, and the big one. The horizontal beam counter resolution register was only 9 bits. So how did they go to 640? Yeah. Little things like that. And can the chipset be used with something other than a 68K? Because we still hadn't decided that we were going to go 68K. Okay, on the 30th, that was the meeting with the team, had an interesting thing. We reviewed the software. Carl Sassenrath, he was the OS kernel guy. At that time, the exec was 6K, and his target was 4K in the final product. They had a really strange idea. The intermediate product, the thing they had now, was going to shrink for the final version. Never in the history of software has this happened. But that, okay.
Well, it happens when someone holds a gun to your head.
Maybe. So exec.
This was the kernel of the operating system, the task scheduler, that kind of thing?
Yes, it did the ROM calls through its library concept, handled all lists were doubly linked, timer lists, message-based operating system, task switch within 110 microseconds, all reentrant code, and basically kept everything on lists, memory, interrupts, exceptions, ports, everything. No type checking at all. So, you know, it was just basically performance.
This is all 68,000 assembly at the time, too.
All 68,000 assembly. Yep. We looked at the graphics library with Dale Luck. That was 16K bytes, and Dale was not going to shrink it at all. That was his, 16K was where he wanted it to be. It was going to stay that way. It had display operations, raster operations, line draw, blit. Layers was not done then, but it was basically viewports, copper lists, all the features that you know from the final Amiga. Dale had a very strong idea of what it should do, and it was doing it. RJ, everybody remembers RJ? Okay, he was, at that point, he was Mr. Animation, not Intuition. So he did the animation library. It was 12K bytes, 99% in Whitesmith C. That was the C of choice back then for the Amiga development. Virtual sprites using the copper list, a maximum of 50. And if all the virtual sprites were used up, it would automatically use Bob's, the blitter objects. Kodiak, Bob Burns, he showed off the text library. It was 8K at the time, including 3K of fonts. The final was going to shrink to 4K, and then the fonts were separate. All assembler, no C. The fonts at that point were named Helva, Carla, Dale, Olga 2, and Rosa. So, all different. Sam Dicker, a Williams guy, he was music. His Whitesmith C music library was 5K of code, sound generation, and here's where I have the ball demo, for example, took 512K bytes total of sound. The instrument was 256 bytes with 16 bytes for the envelope. Let's see. Yeah. So basically, we came away with seeing that the Amiga operating system at that time was 128K bytes of ROM, including 20K for the debugger. But they were going to shrink it to 42K for the final thing.
Well, it's easy as long as you leave out 2 out of every 3 bits, right?
Right, and that was going to include 6K of device drivers for the disk drive, practice device, and serial device, which weren't in the 128K. So let's see. We had a bunch of questions. On the 31st, Adam and Sig went to Santa Clara and basically said, "Yep, we're buying them," and serious negotiations started. Let's see. On the August 3rd, we were talking with them. 40 third-party vendors, 60 software packages coming on release. They were already working on the more advanced chipset for next year. And we were going through the things like the options, rights, sale of rights to other companies, operating expenses, stock options, and so on. Let's see. On the 8th, engineering staff meeting, 32-bit computer was committed for mid-1985. The Amiga was now up to $400 to $500, but the cost would be lowered after the introduction. And we started working on or talking to companies about the hard disk, which was going to be $150 to $180 OEM costs, and it would be available in 18 months. On the 9th, the negotiations continued, but the option had to be extended, but both sides were negotiating in good faith, and rumors were starting to appear. On the 15th, did the Amiga announcement. So, there were rules. Only the spokesman talks about the Amiga. No one else can make any comment whatsoever. No one can say anything about lead times. And they were saying it was a 32-bit computer with advanced graphics and multitasking for the home and low-end business machine market. Chester and Santa Clara would work well together. And that was basically it.
Wow.
So I work for a company called Ragent, and Dave does too. And I promised my boss that I would say this. We're looking for hardware guys and software guys, especially software people who know Linux and device drivers. And if you know the Mac 802.11 stack, Wi-Fi, we'd love to talk to you.
I have some students. Wow, amazing stuff. So I understand that sort of parallel to all of this was they first were trying to introduce it and display it and so forth before they were actually before it was part of Commodore. Is that true? And
They were showing it around.
They were
yeah,
showing it
yeah,
around.
Yeah.
Yeah.
Then
So-
developers had actual machines.
Yeah.
I was doing software outreach, developer support for the +4. So like I'd visit Infocom, and they'd have a computer in a sealed room that I was not allowed to go into, but they were raving about, and it's like, I tried to get them interested in this 6502 thing with, +4 graphics, and they were saying,
Not so much.
not
Yeah,
we've got something much more exciting that we can't show you.
Yes, of course, yes. Well, so I suspect that may have been the Boeing demo or some version of that has quite a story at CES 1984, where it was created at the last minute. But this was pretty remarkable for the time. A large ball bouncing on the screen.
In stereo.
In stereo, in
Yes.
stereo. The bounces were stereo. That was the impressive thing. And so my understanding is this is what they were running on. This was Lorraine was the prototype?
Lorraine was, there were a couple different prototypes. Lorraine was one of the prototype boards. The Zorro was another one.
Okay.
Yeah, that was, basically in the early days. The first one I saw inside of was actually at CES 85, where Bill Hurd and I, in fact, went back to the Amiga suite and got to take one apart because, of course, you want to see what's inside. We both cracked up laughing because they had a little tower board. If you ever develop things, a tower is the board that you stick inside the chip socket because you need to add some stuff to that chip.
Okay.
They had a tower sitting under I guess it was the Daphne chip at that point, and every one of our C128s at that point had a tower that was done over Christmas and New Year's under the 856380 column chip to phase lock it to the system because the internal chip didn't bother to phase lock.
Okay.
And
So these are fabricated coach wires.
Yeah,
right?
yes,
Okay,
yeah.
okay.
It's a little circuit board that was that's made at the last minute. So we just started cracking up laughing. We looked inside, and I'd met with them later to discuss like parts that we actually use on our 128 and other systems. So when they went to the final motherboard for the 1000, they were kind of building in parallel with what we had been doing, using some of the same parts. Because for some reason back then, if you used the same parts, it was actually an advantage rather than these days when, we can only get so many of that part. You better use a different part for that one.
Apparently, it's traditional for the board layout guy to put a chip upside down. And that's what a lot of the towers corrected.
Yes.
Yeah,
They pins here, not there.
Oh, right.
Our very first 68030 prototype had the 68030 on the other. It was done upside down. Well, no, actually, that was the thing I learned from that. It was supposed to be put on correctly. It was a mistake that was put on backwards, and I'm like, oh, this is easier to probe.
Yeah, okay. Yeah, that's good. Yeah.
So I guess they weren't all mistakes after that.
Yeah, no, I had a friend who did that with a PGA chip and manually rewired it. It was pretty.
Yeah, the 68030s at that point were PGAs.
Yeah, okay.
Yeah, not that was before they had the PLCCs.
Yeah. So it made it. In 1985, it actually came out, the Amiga 1000. Let's see what the score is. So let's see. You said they were originally targeting 128K. They went up to 256K.
No, it was 128K for the what they had then, but they were going to reduce it to.
Right. Okay.
Yeah.
Well, that was.
You're talking about the RAM. Sorry, RAM. Yeah, 128K
RAM,
expandable.
they were planning 128K expandable. This was actually 256K expandable.
Yeah. Okay.
Yeah.
There was a little door in the front that let you put in the other 256K.
Yeah. But pretty breathtaking stuff actually for 1985. 496 colors on the screen.
Yep. 12-bit color.
They did overcome that 3016.
Yeah. They must have fixed it. Yeah. And 640 by 400. 400 is an amazing number because you can't do that on a single NTSC frame. You've got to do interlaced.
Yeah.
And so that was a huge thing. It would do 6-bit planes most, 8 sprites per scan line. You know, the 8-bit audio channels that would go up to 24 kilohertz. That's pretty heady stuff for that speed. And you know, an actual hardware blitter, there were not too many things that could move graphics around like that at that point.
In fact, we I think some of the third parties were doing benchmarking on and to do their own blitter routines, trying to be faster than the blitter over the years. And you had to get to a pretty good 68,020 before you could go faster than the blitter, and that's because the 68,020 has a hardware barrel shifter.
Okay, yeah.
And Jay Miner actually objected when anyone called it a blitter, because it could do math operations as it blittered. It was more than just a copy engine.
Yeah.
So he wanted to call it a blimmer, I think.
Blimmer, okay.
Yeah, but that never caught on.
It could do mathematics, because it was 3 operands, and almost everybody else's blitter was just 2 operands at the time.
Oh, okay. Yeah, so I have a, where did it go? It went around somewhere. Yeah, so this was the, it actually ended up being called blitter, at least in the Amiga program.
That was kind of the name that had already been agreed upon in the industry.
Jay was the only person who wanted to, it to be the blimmer.
Okay, right.
And I wanted to call Bob's blobs, but that didn't catch on either.
That's really a shame.
I know, blitter objects, right?
It makes good sense, yeah. Oh, right, so it would do arbitrary 3 operand, any Boolean operation, any Boolean function of 3 bits. Yeah, it's pretty neat stuff.
You could actually do life with it.
That's fun. I'm sure somebody did that at one point.
Oh, yeah.
Yeah.
Just running with the blitter. And of course, in fact, the floppy was encoded and decoded with a blitter.
Oh. Makes good sense. Yeah, it doesn't surprise me. This was basically unheard of in 1985 to have custom chips responsible for so much, able to do so much at the time, right? So this was the earlier Lorraine prototype. And, well, let's see. We have Agnes, Daphne, and Portia, I guess half of whom disappeared?
Well, Denise, Daphne became Denise, and Portia became Paula.
Okay, yeah. So some people got dumped, so they had to change the names of the chips.
Yeah, basically.
But yeah, amazing thing. So, so here's Agnes with the. This one here, he managed to get the bimmer in.
There you go. Yeah.
Well, and this also had this unusual copper coprocessor.
Yeah.
So what's the story on that? I have some guesses about where that may have come from.
Well, the copper is basically it was a video synced coprocessor, and it could put out register address information and load or save registers. So the interesting thing about the Amiga bus is that there's you can see it in there. There's the register address. Register address can access registers, but it also sort of sends commands to chips. In that controls every DMA channel that's run out there every DMA resources, things that happen via DMA channels are all assigned to register addresses. And so, like video fetch, well, each bit plane had its own RGA address. Floppy, sound, all of that had RGA addresses. So the copper basically has things like wait for a beam position, do some copper stuff. So it could go and reload all your color registers, or it could move sprites around, or it could do all that. Anything.
It could load the different. It could change the sprite pointers on the 64. Changing the sprite pointers was actually problematic for software because we get locked out on some scan lines. You could never predict that. But with the copper list, we know we could get that through. So like doing split screen on the 64, that was a tricky because like Logo, for example, wanted a split screen. But there were certain places I couldn't split the screen because the processor was locked out at that time.
Yeah,
So we get this flickering.
Yeah. Ours was here earlier talking about that, so you could have, annoy him, but why did you steal this bus during these cycles? But yeah, but this was quite a bit different in that it was sort of designed up front to be able to do stuff synchronously with the beam.
Yeah.
How that was doing. So I think the Atari 400 and 800 had something almost like this, but not quite as fancy. And so Jay Miner had designed those chips as well, if I remember.
Yeah,
Okay.
and that they had their player missile graphics, which were,
Bit different, yeah.
but a similar idea to a Sprite.
Okay. Yeah, makes good sense. So let's see. Oh, and another thing that I sort of couldn't believe when I was going through was 25 channels of DMA.
Yeah,
going on?
well, the thing is that it's, you put out, basically when you put out a register bus address, every chip knows what that means, including there can be a DRAM read, a DRAM write, certain chips get involved, other chips ignore it. So that made DMAs very simple because you're basically, Agnes is controlling everything. It puts out an address, it puts an address on the RGA bus, and everything responds the way it's supposed to. It's all baked in. You can't change it. Well, I mean, a few of them are flexible, but like for instance, the thing we used to let the CPU in there went away when we were grabbing too much stuff because, of course, the chips had priority to their own bus. But yeah, it was a real elegant system. It was maintained going well into the future. There's stuff that we were working on near the end that never made it out the door that was still, even though it's completely revamped chips, we're still doing things kind of the same way.
Okay. Well, so that's an interesting question. So there were many models of the Amiga that came out, compared to like the Commodore 64 or something like that.
Right. Yeah.
So how much of a hassle was backwards compatibility? It seemed like there were a lot of registers and a lot of things did sort of go in and attack them fairly directly.
Well, we had the advantage or disadvantage of not having a whole lot of changes for a bunch of years to start with because of decisions that were made at management level that we had no control over. I think there were some software weirdnesses that you had to deal with. There's some tricks with. I know they had to also work around application software like games kind of grabbing resources, but not completely shutting the operating system down.
So yeah, having a real operating system was actually a big advantage. People weren't actually poking the chips directly. They were using the graphics library. They were, using, they were using raw input to get, input. So they weren't using all of it, but most things weren't poking the chips directly. However, every OS version upgrade, we had to go through an extensive compatibility testing phase. And some companies like Electronic Arts were really annoying, mostly because of memory usage. They would figure out how much stack a particular routine was taking and make sure that that was exactly how much stack they allocated. So, and if we added put an extra register on the stack at that point, for that routine, their program stopped working.
Yeah, okay.
Yeah, and we did we weren't completely obsessed when we went on to extending the chipsets for compatibility because of that, because nobody was poking registers. It was actually okay if a few programs failed.
Yeah.
It wasn't okay if...
we were shooting for 90%.
Yeah.
Unlike the 128 where they demanded 100%, we were willing to give up 90%. Give up 10%.
Yeah, so when we went to the Pandora chips, the copper lists weren't directly compatible. I think in every mode at least. There were a lot more registers available because you had all 256 color registers in the LUT available through the copper list, which had not been there before. There was when we went to, even before that, we went to Amiga 3000. For hardware, we had compatibility issues as well we had to look into. Part of that was internal in that the bridge card had to work or I got hit over the head with a stick. So there were a few things about the bus that had been designed as an expansion bus that hadn't really been formalized, that then became formalized because of the behavior of certain things. We ran into some third-party boards that were fairly, like there was this thing called Amiga Live that was a live video digitizer that didn't work in the 3000 on the 32-bit bus when we first got it. It was a 16-bit card supposed to run in compatibility mode. They were breaking some rules. I actually got them, because it's kind of nice when you're Commodore, you can say, send me your PAL equations and I'll tell you what you did wrong. I also told them how to fix it without changing, just by changing the PAL. They didn't have to run any new wires because they were just not qualifying something with address strobe or whatever, and it saw some noise on the bus that was for 32-bit people only that it was responding to. But the thing is, I mean, we also had problems with with applications that were not 32-bit clean. Once we started wanting to add 32-bit memory, some of the support people had written tools that let you find that out ahead of time. If you could test on a machine with an MMU, you could use the MMU to find your bugs. One was called Enforcer, and it was it was kind of a developer tool, but before you knew it, all of the magazines knew about Enforcer, had their own copy, and would write bad reviews if you got Enforcer hits. I don't know how that happened.
And we had Memmung.
Memmung.
Because all memory was allocated through exec, you couldn't just grab memory. We could actually do stuff on the allocation and free to check for whether or not you've violated the limits.
Actual operating system discipline in the mid-80s.
Well, it was the idea was to discipline it on a machine that could discipline it, that would then allow you to have those bug fixes on every machine, because the older machines obviously couldn't.
Sure.
And the operating system really never been written to support, at the time, to support MMUs. But
so you didn't have an MMU in the 68,000.
Right. Yeah.
When did you
the first MMU was in the A2620 add-on card for the 2000. So when I took over the 2000, there had been the original 2000 was based on the 1000 plus. There's a schematic diagram in a book called Schematics and Expansion Specifications that was made back when it was the board. So that's where the Zorro bus got its name. Is because there was an add-on card that just had Zorro on there, which meant it was for the Zorro motherboard, but because they hadn't changed they wouldn't know if they were going to change the expansion bus. In fact, I think back then it was an expansion chimney.
Yeah, the cards were enormous.
Yeah,
and it was going to go in. I think the next generation machine was called the Ranger.
Yeah.
Right.
Well, that was their next gen. Yeah, their idea of the next generation was going to do. They were going to have some tweaks for a high-res bitmap mode.
But it was also going to have a cage built in with those enormous cards.
Yeah. So anyway, where was I going with this? What?
MMUs.
It turns out that the two guys who started the Amiga 500, who came up with Fat Agnes, was Bob Welland and George Robbins, and they had been the guys doing what Andy mentioned before, the Z8000 machine, which was Z8000 machine was, think of basically a kind of like a Sun 2. They were going to have a megapixel bitmap display with GUI.
Running Coherent.
Mark
Williams Coherent.
Which was, a Unix clone. And it ran one of the guys, Rico Tudor, had written his own super fast windowing system, which was basically just it wasn't like you think of on an Amiga or a Macintosh or something. It was really just to have multiple terminals, but it was a windowing system, and it was wicked fast. So they still wanted a machine that would run Unix of some sort. So Bob Welland's dastardly plan was to build a 68020 add-on card, and in the 2000, when I was building the 2000, it's like, well, I have this extra slot here that I don't need anymore because I could fit a megabyte on the main board, and that was really just the edge of the 1000, that connector, pretty much. So I decided that, well, it ought to have some additional protocols in there, since I was integrating the bus controller, all the PALs and stuff into a single bus controller called Buster. I said, well, I'm going to have a new protocol that lets you just plug in a chip, and that chip can request to be master of the whole system, and you don't have to take your 68,000 out or anything. And so we had, built-in plan for an expansion card that gave you better CPU. Because of course, we were using the same CPU in 1986, 1987 that Amiga had used in 1985. So the first one had the Motorola 68851 MMU on it, as well as the 881 math chip, and 2 megabytes of real 32-bit memory on it. And that became the Amiga 2000/20.
Yeah, this is awful. This is something else I need to add to my collection.
Yeah, Amiga 2000/20 was it. Now that was running 14.3 megahertz clock, which came from the quadrature clocks that we had. We had a signal called CDAC, which was 7 megahertz delayed by 90 degrees. So I could make a 14 megahertz clock with an XOR gate. And actually, that kind of got past the FCC guys, because they always they pay a lot more attention if there's an oscillator on the board. But that was the first generation. Then we made a second one with the 68030. One day, one of the managers, Gerard Bucas, or maybe it was Jeff Porter, one of them came to me and said, oh, we're getting the prototype 68030 chip in next week. That's all they said. A week later, I had a card to plug it in, which I redesigned from scratch. Basically spent the entire week without sleep, because I didn't want it to just work on I didn't want to run at 14.3 anymore. I wanted to run at 25 megahertz, possibly 33. So I had to figure out how to do it asynchronously. So you could go out to the 68,000 bus at normal speeds, but run faster. Because the 030 had a built-in MMU. We didn't have to have space. So there was enough room down there for 4 megabytes of DRAM. And this was the one that had the processor on the wrong side of the board, because Terry Fisher is the layout guy who was doing basically all my boards back then. Hadn't quite noticed the bottom view, because again, this was something that we were going to do in about a week, because I knew this chip was coming in. And but Commodore was like that. Like, I could just build this thing, tell Porter or Bucas that, like, oh, I have this thing I just did. Oh, we'd like to. Can we make it? Can we get it? Can we on it?
Did a 68030 board ever make it to market?
Yeah, that became the Amiga 3000/30.
And that's the first one we got Amiga Unix running on.
That actually had enough memory to really run Amiga Unix. I actually ran Amiga Unix. Well, it was called Amix. It wasn't Amiga Unix. The first one was Amix, because that was before you were allowed to use Unix in your Unix name.
Okay.
And Amix ran in 2 megabytes, but like if you loaded GNU Emacs, it would thrash. You would nothing but hard disk activity. So it really wasn't practical you could virtual memory, but it wasn't practical. 4 megabytes was actually enough to run it pretty well.
You could actually run a UI and run. I think it was Gosling's Emacs at the time.
No, it was definitely. I'm not sure. I use Gosling's Emacs too, ever since Carnegie Mellon, but that's because that's where he wrote it. But maybe it was Gosling's Emacs. It was Emacs anyway. Yeah. It was big.
Kind of the same thing. Yeah. Let's see. Oh, I had a few more technical things. So one thing that's interesting. So Amiga has this just amazing graphics system compared to anything else at the time. One of the things that was somewhat unusual is it used bit planes, where you always had 1 bit per pixel, but if you wanted multiple colors, you would stack them effectively. And that's quite a bit different from virtually every other, where you would do 2 bits in a row or 4 bits in a row or something like that. What was the thought behind that? Do you know how that came about?
No, that decision was made.
My take on it was just made the hardware easier, because you had a DMA channel for each plane, and there wasn't any need to coordinate. I wasn't changing DMA structure or anything to fetch it differently
Okay, yeah. Oh,
You
that
know,
makes
so they
sense,
line
right.
up, and that was, and I had actually been reading about National Semiconductor. We mentioned the the 30 and 16 chip or whatever before. Well, they also had a graphics processor, which you had a main processor and you had individual satellite processors. Each one managed a bit plane. And you could stack as many of those as you wanted to make as deep a display as you wanted. And of course, you could make, you know, you didn't take any more, you had to have separate memory for each one, but it didn't, you know, you had a lot of redundancy there where you could just, you know, you wanted a 32-bit display, 24-bit display, you put 24 of those in there. Of course, you know, it was nothing we could ever afford to use, but it was cool to read about. You know, I'd been reading about all that stuff because, you know, like where are we going in the future? But yeah, so that was my take on it, was that it was kind of an economy of design. When we got to the never released advanced Amiga architecture, we had bit planes, we had chunky pixels, we had a thing called hybrid pixels, which look a little bit like MPEG DCT cells, in that they sort of compress color in weird ways. So it was usable for animation back in the day before you actually had real animation process.
On the Amiga, it was a real pain to port Doom because of the bit plane architecture.
Oh, sure.
So the AGA, the advanced, would have made it a lot easier.
Okay. No, that makes sense, because everybody else was using chunky pixels.
Yeah,
everybody else was using chunky.
But you could have 10-bit planar, 8-bit chunky.
Okay.
Can't think of any other particular numbers, but it was that was not something that we'd completely forgotten about. It was just, you know, it was a matter of, you know, the age. So when we went to the Pandora or AA, it was called AA because we started AAA, Advanced Amiga Architecture, in 1988. We started AA in like 1990. But it was sort of like, people thought of it as AA Junior, but it was as AAA Junior, but it really wasn't. It was really, you know, a new version of the existing chipset with new parts that, so the Alice chip was basically Agnes with some other stuff in it. You needed to make some more register paths and others, but it was, that chip was I think, the largest NMOS chip Commodore ever made, and they were very worried about breaking things because it was so large. Lisa was brand new chip done in CMOS. Commodore actually had a CMOS process there. We had a 1.5 micron CMOS process. It wasn't really what you wanted for Lisa, so we were also making them at HP in their 1 micron process. But this was really before contract chip fabbing was much of a thing. I mean, you could get it done, but it wasn't a big business for anybody. So you kind of had to ask nicely and not make mistakes like forgetting to order the parts 6 months or a year in advance or whenever you needed them, which of course Commodore did, trying to roll these machines out. But I had the first AA machine up and running in January of '91. But there was a chip problem. We couldn't get a display. So early in February, we got a new chip in. I forget which. Even though Lisa was the display chip, I think it might have been an Alice problem. But anyway, we got the new chip in. It booted, kickstart. It had some issues because, of course, couldn't use any of the new registers. But it worked. It ran, you know, and it was a year and a half before they got it out the door because of management flip-flops and stuff. Yeah. But it was but because of the limitations on, particularly on the Alice design, they couldn't go and add chunky pixels at that point. They couldn't add a bunch of other stuff just because it was beyond the scope. Now we pushed really hard to get a CMOS version of the address processing chip. Yeah, and a CMOS Alice done. There was talk of doing a AA plus, and that was mostly driven by George Robbins, because AAA was never going to be something you could put in an A500 type machine. It was just going to be too expensive.
Okay.
So they were, at least, unless we had gone to another level of integration, because 4 or 6 custom chips that are bigger than any of the custom chips today, Amiga chips, was going to be an issue.
Makes good sense. Oh, I wanted to show this this pretty picture. So I think we're actually looking at what you could see on one of the early Amigas, and so this is using the hold and modify.
Oh yeah, TAM mode, yeah.
Yeah. So what was were you involved in that, or was that another thing that sort of?
I mean, I've heard stories about it.
Yeah, that came with the original chips.
Yeah, it was
And
originally part of the chips. And
I think it was an accident. I mean.
well, I had heard that that they were originally talking about doing YUV color instead of RGB color.
Oh, sure. Mm-hmm.
So hold modify makes a whole lot more sense if you've got a if your internal color processing is YUV instead of RGB.
Mm-hmm.
Which of course, if you're building a game machine, but they weren't really building a game machine, but they had early on it was good. They were selling it as a game machine. Right. They wanted to build a personal computer.
It ultimately succeeded as a game machine. But yeah.
Well, it was very popular for it was computer gaming. It's not the same. Computer gaming. Yeah. Actually, the one that really was a game machine, the CD32, was that one of those victims of not having enough parts.
Oh.
Funny, I'd be dealing with that all of these years later, which it's been a bad year for parts in the last 2 years as well.
Quite.
For completely other reasons.
Yeah, I was struck by the interesting mix of things, almost all devoted toward graphics, but then of course there was the whole audio system, which was amazing at the time as well. Let's see. So one of the things that was amazing is it had the ability to do, they called it dual play fields, right? It was never referred to as a frame buffer. It was always a play field or something.
Yeah. Yeah.
We really only use that for the sliding screens in the operating system.
Okay. Yeah.
Where you could slide. I mean.
Right. Okay.
The pre-intuition user interface actually made use of that to do more than one thing at a time. Once intuition kicked in and started using layers, that really got ignored.
You'd have to be programming the system pretty close to the metal to be able to use that, I guess, because the operating system didn't like it.
The operating system used it fine, but it was
didn't like
the user interface just didn't do much with it except to have multiple sliding screens.
Okay, makes sense. And it has also a curious mixture. I'm trying to think of other systems that would have this, where it both has the blit facility, which is the block transfer, so you'd be able to copy one thing to another, and true hardware sprites.
Yeah.
And so again, I'm curious if you know the genesis of this or what the effect of all of that, of having both facilities available seems quite unusual.
I think I mentioned that earlier. There's a limit to the number of virtual sprites that you can get by playing copperless games to change the pointer. And but games wanted more moving objects than that, and this splitter was just sitting there. So RJ in his first animation library would do both. He'd do virtual sprites until he ran out, and then he'd switch to bobs rather.
Oh wow! Okay, and it's seamless that you could actually program with it and sort of not know that it was.
Right.
Wow. Okay.
It would be hidden from the the programmer.
Another reason for using the operating system.
Yeah. No, that is.
But that animation library didn't really survive. Instead, RJ would switch to Intuition and Graphicraft and TextCraft.
Okay. Yeah. That makes sense. Well, yeah,
That didn't make sense.
Okay.
No, that makes sense. Okay. That would have been great to have that.
Well, I'm impressed actually. The fact that you were able to maintain operating system interfaces to things as opposed to people going in and getting at the registers directly. Somehow that meant that you had enough performance, right? Most of the time the going in and playing with things directly or whatever it was because it was too slow or ineffective or something like that. But somehow it seemed to work, which is pretty remarkable.
Well, I mean, one thing when you have the blitter that can move things around a whole lot faster than the CPU, and it's not that intuitive to set it up yourself. You're calling the library that sets it up. Not a big deal,
much more
right?
natural.
Yeah, it's not. It doesn't take a lot of time. It's not like you're gonna, it's not like you're trying to write your customized display code just a little bit faster than the, than the guy who did it in your graphics library. You're calling on a hardware resource that's a little tricky to use otherwise. Same thing with sprites. It's not, people could set up their own sprites and write their own copper lists and stuff.
Well, that makes good sense. Okay, so not only, actually there's two things. One is make sure the performance is high enough, but then also raise the complexity to the point where people want to use the software interface. That's brilliant, actually. I like that. I think that's the modern solution as well. Oh, and don't tell anybody about what the hardware's actually doing. That's the other one.
Well, yeah, that's
a key point.
Yeah. Well, and part of that is because like in some cases you get the chip that you built, not the chip that you specified. So if you didn't write the spec in the first place, you've got nothing to apologize for.
Okay.
And we had a few of those, even in hardware. So, for instance, there's a bug in the Alice chip on the Pandora AA chip systems, where if you implement it the way it's supposed to be implemented, the blitter can actually turn on at weird times when there's display or or something. There was a collision, and I found it and worked around it in system logic, and then told the chip guys about it, and they're like, "So you fixed it?" I'm like, "Yeah." Like, so we're not gonna, because there was no other reason to rev the chip at that point.
Perfect. Yeah. No, you flipped the bug to feature.
Yeah.
Well, there was nothing to do with, nothing useful about it. It was just that I had a pal that had to sit there and snoop the chip bus anyway. So, okay, while you're doing that, basically because the ability to let the CPU talk on the chip bus was kind of left up to the system designer.
Sure. Okay.
So while I was doing that, I could do I could basically throw them a bone and make sure that I think I ended up latching the blitter busy signal or something like that through a double cycle, and that solved the problem.
Very impressive.
And of course, all these people, it's funny, all these people like who are now recreating Amigas get to see these these little dirty secrets we never told anybody.
Sure, yeah. Well, but at the same time, that probably makes their life a little bit easier if all they have to do is make the operating system work. But
yeah. Well, I don't think they're recoding huge vasts of the huge bits, unless they're writing their own retargetable graphics library or something. Especially since that work was never quite finished.
Not quite.
Would have been a little easier.
Interesting. Let's see. So we're doing okay on time, but I was thinking at this point, if we have questions from the audience, maybe this would be the best. This would be a time to switch over for it. Do we have an extra microphone? Yeah.
I can speak without it.
It's more for the recording, I think.
Oh. Thank you. This is a specification question, and I know this probably is more focused for Andy. By the time System Software 2 was coming out, which is also coincident with the 3000, very powerful, made the cover of Byte magazine, everyone knows that. Was there ever consideration for a network file system extension? I ask because I know that the 2065 card was available for the Unix style 2500s and above, but yet it never made it into the 3000 or the like. And is that something that even made it into the discussions for the specification, and there just weren't resources to assign to it? That was my assumption.
Yeah.
It would have been would have been much helpful to the system at that time.
We did want to support an NFS library, but that just never happened. Resources, time, and lack of management interest, I think, is the thing. I had a guy who was actually working on that, but never made it into a product. Sorry. No, I understand. There are limitations.
Your timeline had covered like May '84 to September in the purchase of Amiga. I'm right here. And so Tramiel had acquired Atari in July of that year? Did you guys have any
So,
knowledge of the relationship or what was going on with Tramiel and Atari? And
no, and he acquired, well, yeah, the Amiga, it was really weird. I'm looking over the timeline, and Amiga canceled the contract with Tramiel and returned the money on August 13th, which was, and Commodore announced the acquisition of Amiga the next day. So I don't understand how that quite worked so well, but that's how it went down. So clearly that was the, getting out of the contract was, you know, had to start happening after May and before August 13th.
No other questions? Okay, Jeff.
So I know you said that there were a bunch of systems in development when Amiga, but what was the immediate, was there any immediate effect on those projects when Commodore decides to buy Amiga, the projects you had going on? What was the immediate effect on that?
Well, they were starved for money at that point. It was taking up a fair amount of Commodore's money. So like the LCD project, which would have been a great machine, couldn't get its 5K to do a soft tool case. And that was kind of the end of the LCD project.
Yeah, and the whole Z8000 project was shut down. The Commodore 900 is what they were calling it at the time. That was the, yeah, that was going to be your low-cost Sun 2 workstation. I'm not sure what they were. I'm not sure. It was very cool. All of us nerds liked it. I don't know what they were going to do with it in terms of putting it on the market. Because as alien as the Amiga was to Commodore's normal salespeople, this would have been even more so.
Well, it's too bad, too, because Z8000 processor-based computers just went and took over the world at that point.
Sure, they had so few transistors.
Yeah, it was very nice, yeah.
Well, you know, they went to the Z80,000, and, you know, who knows?
Be up to Z8 million at this point? Yeah. Okay.
It could be, yeah.
Thank you. This is another system specifications type question. At the time that the 2000 was coming out or being developed and the hard drive interface or controller being made available, this is more, I guess, a question for Dave.
Yeah.
What happened such that auto boot didn't come out when the 2000 came out and the card had to be re-offered another year later? That seems, well, it seems sort of obvious from the outside, and I remember that my PC-centric colleagues at the time couldn't understand how a large boxed computer system would still need a floppy to start.
I guess there are some software issues with the auto boot. In 1.2, I guess it was fixed in 1.3. That's my recollection. I don't remember exactly what the issues were. It was there was a whole system for this for discovering ROM tags in expansion devices that told you that told the device various things, and eventually it worked fine. But that's my understanding of it, is that a lot of the stuff was kind of happening all at once. So I was working on the Amiga 2000. Jeff Boyer was working on the 2090, the first hard disk controller. The software had already been written, and it took some actual hardware to test it. That's again one of those problems of writing the software before the hardware is available. But again, I don't know exactly what the problems were.
On a related note, so one of the things I find a little unusual is a lot of them had enormous ROMs with a full operating system in it, or nearly so. And it sounds you were making choices like that as well. I'm curious if they were thinking in terms of, oh well, no, this is not how it's going to go forward, or how were those decisions made at the time?
Kickstart was supposed to be a ROM.
Okay, okay.
It was not done in time. So last minute, or it was changed to a disk-loaded RAM system because the OS just wasn't done in time. Otherwise, it would have been a ROM.
Yeah, back,
okay.
yeah. In those days, you burnt the ROM, you actually had masks ROMs that were
yeah.
made mass production, you couldn't change it.
Yeah.
And I guess later on, they could actually kind of patch ROM routines, but I'm not sure.
Oh, no, we
back
could do,
then.
we
You
could do
back
it.
then?
That was
Yeah,
part
but-
of the original
yeah,
thing,
okay.
but it was just
Too
so
much,
far off.
yeah, too far away from what you were really gonna need. You know, obviously.
They wanted to ship the middle. If they'd stuck with the Christmas '85, I think they could have had ROMs, but not in the middle of '85.
Okay.
Yeah, and of course, after we got ROMs, everybody wanted the Kickstart back. So that's I ended up writing that for for the MMU machines later on.
Okay.
Yeah, some other computer had used all the available slots at MLS in '85.
So I know most people remember the Amiga as like a gaming computer, and maybe that's how it started. I worked for a company that really did use the Amiga mostly for video. We were a VAR in a sense, and I was building video toasters like gangbusters, like for a while. And even before that, you had like Sculpt 3D, and you had a lot of 3D stuff. Did that shift in the market change the shift in engineering at Commodore? Because for a lot of people, the Amiga was a gaming machine, but for a lot of people, the Amiga was a cheap SGI. It was their way. I mean, they stuck a Genlock on it. They were doing titling. Did that market shift change engineering internally?
Well, from a software point of view, somewhat. We'd like to do whatever New Tech wanted. Because they were doing great things. And there were, within Commodore, we did see that, desktop video was something the Amiga was perfect for, but it may have been a little too early for, like, the customer base. Desktop video was, specialty places. Not everyone did their own YouTube videos because YouTube didn't exist. So if there had been more consumer interest, desktop video might have been a big thing back then.
Because around 90, I think Harry Copperman took over, and you saw the Amiga AUX, and then you saw the Lowell board, and you saw machines that we couldn't understand why Commodore was even building. And so it was kind of like, to us, the future was desktop video, and we didn't understand why we were seeing stuff. The network boards we understood. We didn't understand why we were seeing machines that weren't video related. So I guess we were very, very focused on video, and we didn't know what was going on internal to Commodore.
Yeah, the ULOL board was kind of a weird thing in that that had been just a smaller sponsoring. And, occasionally they'd come in and show me what they were doing, and I tell them, you did that wrong, just to bus interface it, not their part of it, not their TI graphics chip, but and then it seemed like it was going to go along with Amiga Unix as something you could, but the Amiga Unix was just, that was being pushed for other markets. It doesn't hurt to have your, to find new places to sell your equipment. In the U.S. never quite figured out what they wanted to be. In Europe, it was all gaming. That's all they cared about. Here, it was mostly the video, the desktop video market. And so it was kind of, it was split a little bit just based in product lines, like A500, A1200 were for gaming, and A2000, 3000, 4000 were for video stuff. And I know we got. We even had the 4000T with 2 video slots in it. The video slot was just something that George Robbins and I came up with when we were deciding what neat stuff we could do with this 2000 that we had inherited. He was mostly staying with the 500, but I was taking all the 500 stuff, putting it in there and thinking, what else can we do? And the slot, they had an internal slot, which kind of like their CPU slot was the same as the external slot. It was really just to allow you to put an internal gen lock. And I said, well, that's kind of silly because we have like we have the whole, why don't we run that over? And then George said, we should run a parallel port there too. And if I had to do it over again, I'd see if I could get permission to put in another CIA chip or something, so it had, or some other way to control it, but at least we had some way you could make it do stuff. And that was really with the idea that this will make it better for doing video stuff, because I have a place to put the things that video people need that I can't build into the machine, other than the regular slots. But it wasn't, I mean, there wasn't, I didn't see a whole lot of strategy coming from the top on any of this stuff. We discussed it at the engineering level, but it wasn't like we had a big powwow of all the heads of marketing and sales and management saying, this is our future direction, we should do this and that. Though we were surprisingly in the chip group, we were surprisingly pushing high. Like the AAA chips, video guys would have loved that. They were too expensive for gaming machines, at least if they had come out in, say, 2000 when they should have, or 1990 when they should have, or 1992 when they should have, or even 1994 when they should have, except Commodore never spent enough money on any of that stuff, so it never got out the door. But, that's, what are you going to do? I mean, from the engineering perspective, we were pushing hard in that direction. Even with the 32-bit expansion bus, I was trying to make it better for people who wanted to add stuff on that, Commodore couldn't manage everything. One other mistake we were making, I think, with some of it was Commodore kept doing things that other companies could do pretty well, and we really should have spent more of our time doing things that only Commodore could do.
On the new Superbuster chip.
That kind of got stalled for a number of reasons, COVID and parts availability. But I'll have to see if we'll pick that up again. That's a buster replacement in an FPGA, which may be available off the shelf at some point in the future. The FPGA, that is. There's an amazing crunch on some of these parts. I have a part in one of my systems now that let's just put this in perspective. You can get this part from a distributor, or actually from a broker. From Texas Instruments, they cost about $20. It's just a little power module. Last summer, you could get one for about $950 from the broker. Now, I think it's gone up to about $1,200, $1,500. No, it's $2,200. That's right. The last price I heard was $2,200. Needless to say, I'm not using that part anymore. I made a little module that does the same thing, and I'm not even sure we're spending $20 on it.
That's probably a 3-year lead time on your part, so.
Not yet. But that, yes, and that's, if you look up those parts, a lot of these parts you'll have lead times going into early till mid 2023 on parts like regular everyday parts, not even something that's like super sophisticated or whatever. So I spent most of last year and this year redesigning stuff to be able to let us keep building what we've been building. So I mean, this is an actual thing with parts, and I haven't actually talked to Jens about this lately, but not the kind of thing you want to launch in the middle of we can't really build it issue. And I had some other things took me away from it too. That's not the entire reason, but it's the best reason.
Yeah, I think right at the moment, retro computing, vintage computing is nearly perfect because it's the only affordable computing around.
You can afford it, and maybe you can find parts in a basement somewhere.
Yeah, something like that. Yeah.
I got this is in line maybe with the Buster. If you do recreate it, I'm sure a bunch of Amiga fans are wondering if there are any plans from anyone that you know in your circles to maybe do CIA chips or a couple other needed chips that seem to be disappearing and might never be around ever again.
It's a shame. Commodore had actually done the entire 8520 in I don't know if it was in M language or VHDL or whatever, but it was they did a whole design for that to build the piece that went into the CD32. The integrated part, so they had a big, $500 FPGA sitting in a socket running that in the lab, but who knows what happened to those design files. But yeah, so it can be done. I don't know how interesting making an 8520 would be to the average VHDL person, but hey, if you want to learn, not everybody can be Jerry and design a entire C64 as your first FPGA project, but the thing is, you get the basics down, you plug it in, doesn't work, you figure out why, make some changes, doesn't work again, figure out why. It's not like you actually have to make the silicon and spend your your $250,000 or whatever to find out you did it wrong. So it's, in that particular instance, hardware has become a lot like software. So, that somebody ought to, in fact, I haven't even looked up on open cores lately. There might be something pretty close to that you could even pick up and customize, but you got to know what you're doing, obviously. And, that hasn't been something terribly interesting, I guess, or it probably would have happened already. But, you'd sort of want the entire Amiga to be in VHDL or Verilog or whatever at this point, just because parts aren't becoming more available, and anybody, if you look and you see that, oh yeah, this one's they've done the entire Amiga chipset in a pretty compatible design. Smaller parts ought to be something that could be split out or put into little towers, or it guess it depends. Do we need to have it on a board that plugs in? Because that introduces a lot of complexities today, because nobody's building 5-volt FPGAs anymore. So, if you just want to plug it into a socket, you have to deal with the simple part is getting the 8520 to work at that point, maybe. That's actually one of the problems doing Buster or anything else too, is that if you want to interface with an existing system, it makes it a more complicated design than if you just wanted to build that functionality for something new.
Any of the other boards like you did Rock Lobster? I remember the 500 was.
Oh, they all have names on them. I mean, the A2000 motherboard was called the Boss.
Yeah, I wonder why.
It was a Springsteen reference. It wasn't the.
Dave was from Jersey.
Was from Jersey. I moved out in 2016. I live at either end of Delaware now.
So as long as there's a gap, I am serious about taking people's cards or resumes or whatever for software Linux device driver hackers. Good company to work for, and I could really use people.
Sounds great. Yep. As long as you're willing to hire people who just graduated, I think I may be able to deliver a few.
Okay. As long as.
Burnout hardware engineers. I'm good for 8 bits.
Yeah. Well, let's see. We're nearly out of time here. I'll ask. I'll try to ask an interesting question, though. All the time you remember, working and developing these chips and making them work and so forth, is there one thing that really stands out in your mind as being, oh, this was just wonderful, this was fantastic? I'm sure there's a bunch of negative stuff as well, but once or twice there must have been a success, right?
Yeah. Oh, I mean, for me, it's just the first time I get, the first time the machine comes up and it's alive, and a couple times I was the only one, it's the middle of the night, and I'm like, I like for the AA chips, okay, we had the dead ones, and we got some new ones in, working, trying to work around the splitter bug so the operating system would run. And then it's like, okay, it's up and running, but it's not running anything new. So I sat down and wrote myself a copper list just to build a graduated color, 256 colors across the screen. Just, and then it's like, wow, yes, it's different. It's not the same stuff. And that was just that. I guess that was the first AGA AA Pandora program written. It didn't. I don't know where it went. Nobody keeps this stuff. There was another one when Bill would remember this one when we were trying to get we put the 80 column chip in the C128 and trying to get that up and running. And I also wrote something similar to get that one going, or just some stuff on it, programming the registers. And I found it didn't always work. And then I found if you bang the register several times, it would generally work. Enough to get something up, enough to get a display up on the problem, and that's what ended up giving us that tower that went to CES. That it was not properly synchronized to the because it's got its own bit clock that comes off of it comes off of its own oscillator, and the hardware in there it wasn't synchronizing properly to the 6502 bus. And so, or 8502 bus, excuse me. It's actually it was actually an 8502 at that point, and if you were persistent, and we started joking about this because Kim Eckert, the designer, is from Texas, and previous thing from Texas was Magic Voice, which we all called Tragic Voice, and apparently in that one, there's also registers you have to hit twice to go. So that was anytime you had to bang it more than once, it was called the Texas register. You got to hit it once to wake it up.
When in doubt, write twice.
But just when you bring something to life. Now, I didn't write the first code that went on the AAA systems because it turns out there was a LUT scramble there, and to get anything to look right on the screen, you had to run it through this filter that changed all the colors around. So some of the chip guys had come up with that, and they had written a whole little system that would allow them to load things up on the display through. I guess it's all written in AREX.
Interesting. Do you have similar experiences? I mean,
Yeah, similar. When I guess in the Commodore days, the software people, application guys like me, were, I guess, the customers of the chip. So at the beginning of a chip design cycle, we get to meet with the chip designers, and we tell them what we wanted, and they would say, no, that would take too much space, or that's a terrible idea, or sometimes they'd say, yeah, we could do that. So they then go away for 6 months doing whatever it is that they did, and then they come back after, give it to a person like Dave to put it into a system, and then we get it back. And it was always like a Christmas surprise, finding out what it actually did when we got that. So it's like, well, we asked for this, and this is different.
Okay.
But sometimes it was a really nice surprise, and sometimes it was like,
that's not useful.
Not useful at all.
Christmas is a good thing. You ask of this of Santa, and he brings you something a little bit different. But
yeah.
It used to happen a lot.
Sometimes, so it was always fun getting new peripherals. Like in, I guess, 82, Commodore did from Texas actually, a voice control joystick. You could,
up,
down, left,
okay.
but it was demoed for the execs, and it just didn't work. So it turns out that after they gave it to us and discussed, we were playing with it. Turns out you had to use a Texas accent.
I was going to say it had to be a regional.
You had to say left. Everything was 2 syllables.
Okay. Okay, right. Yeah. I can't do it.
Those are the fun things at Commodore. Bringing up an OS for the first time or new hardware, that kind of stuff is always fun.
Okay. That does sound like a lot of fun.
Yeah, working. I guess death marches. Those are fun always. Yeah.
I just enjoyed hitting myself with a brick because it really feels good when you stop. Very good. Speaking of stopping, I think we are officially out of time
Okay.
here.
Okay.
So please, let's thank our yes.
Yes, I am Mike. How are you?
Good. How do you want me to introduce you?
You can just introduce me as Mike McGann.
Hi, this is Mike McGann, who's going to talk to you about writing an emulator.
That works. So we get to display the work. Oh, those are left over. I have a water. I'm having some video issues here, though. It doesn't want to work for some reason. Yeah, or something. Maybe we need to do a backup laptop or something. So. I do have a PDF online. If I can access that, then we're good to go. Okay.
Let's see. It looks like it's working.
Yes, it is.
Oh, nice. That's really thick.
It is, yeah. Do you have a wireless mic?
I can get one, yeah.
Okay.
One for wireless?
Yeah, I like to stand up and move around.
How do we test it? Oh, I can hear myself. It's working?
Thank you. Thank you.
Check, check, check. 1, 2. Everybody hear me?
Let me know when you're ready.
Okay, we got 2 minutes. What's up, Eric? Ready?
Is it on?
So I adjusted the camera.
Okay.
You can go up to the edge of this.
Okay.
To the edge of the table.
Sounds good. Thank you.
All right, you ready?
Let's do this.
All right. Good afternoon, everyone. Vintage Computer Festival East 2022. Woo! Got a lot of great speakers. Fridays are technical talks, and this is going to be very technical.
Yes, it is.
And you guys are going to really enjoy it. He's going to be talking about writing an emulator. He's had experience writing emulators for the Commodore 64, my favorite. And he had given a presentation at MagFest 2020. So this is Mike McGann. We'll give a big hand.
Hey, good afternoon, everyone. I am actually so glad to be here today. This is my first time at VCF. Never been before. I actually planned on coming out here in 2020, but there was a small little problem with 2020. Happened to be the same weekend as my wedding anniversary. So I decided to try to negotiate with that, and I don't like going out for Valentine's Day. So I said, hey, if I go out for Valentine's Day, can I come to the VCF in April instead? It was a tough negotiation. I was able to make the deal. So we went out and had a great time on Valentine's Day. Then the pandemic hit, and I spent most of April watching reruns of Stargate SG-1 instead. So, but I'm here today. It's 2022. Our anniversary is now on a Monday, so no worries there. So I'm sure that many of you in this audience are familiar with this computer. This is the Commodore 128. This is the computer I spent a lot of time learning how to program when I was a kid. Now, I apologize if I just called you old out there because I said I was a kid when I had this. But this is the Vintage Computer Festival, and like it or not, none of us are getting any younger. I actually bought this exact one from a friend, Eric Chomko, who is here today. Everybody give a shout out to Eric Chomko. He'll probably try to sell you something this weekend. So, he loves to collect old computer equipment. His wife actually keeps trying to get me to buy stuff from him anytime I come to visit. So I took him up on the offer one time and bought this. I have since acquired a Commodore 128D. I got this from my wife's father, Larry Sawyer. This was sitting around collecting dust, so I figured I'd provide a nice home for it. This is how I have it set up at home right now. This desk is usually not this clean. It tends to be a magnet for clutter. So, but it's been really fun playing with the Commodore computers again, and it sort of got me thinking, you know, how much would it take to write an emulator for the 64? Now, I don't want to do anything completely comprehensive or anything like that. I don't have time for that. But how about enough just to get up to where you can actually type in a basic program, everybody's favorite, Hello World, and of course, go to 10, because you have to say go to 10. So that's what we're going to talk about today, is basically how to get from scratch up to getting to Hello World. Quick disclaimer, I am not an expert on emulation. I just happen to have written an emulator. I'm also not an expert on the Commodore stuff. I just happen to own one. So everything I go over today, I hope is correct, but there's always a chance something's going to be wrong. And of course, we're going to concentrate on getting things to work, not necessarily to do it in the best or most efficient way. So the agenda for today, we're going to spend the first 15 minutes talking about memory. Then we're going to spend the next 15 doing an actual CPU implementation. We're actually doing a lot of code in that section there. The next 15 minutes is going to be from there to get to Hello World, and then we'll finish with a Q&A session at the end. So let's first talk about memory. On a CPU like this, we have an 8-line data bus. We also have a 16-line address bus. And with those 16 lines, you can access up to 2 to the 16 different values in the address space, which is 65,536, also known as 64K. So when you're going to write an emulator for memory, you may be tempted just to have one huge array that is 64K in length. So 64K array of 8-bit values. Now the problem with this, it's a little bit too simplistic. It doesn't actually really model the way that the CPU actually interacts with the buses. Okay? So while most of the time the CPU uses the buses to talk to memory, whether that be RAM chips or ROM chips, it can actually use it to talk and communicate with other chips or devices on the machine as well, whether it be the sound chip, whether it be the video chip. And it can actually talk on the bus to be able to manipulate the lines on the back of the computer for the user port. So what you could actually do is take one of those lines on the user port, hook it up to a relay, hook up that relay to your desk lamp, and then tweak a value in memory to turn your lamp on and off. That's pretty great. Now, I would recommend doing that because it's really easy to fry your computer if you do something wrong this way. And they don't make Commodores anymore. So if you want to have that kind of fun, buy an Arduino. They're only $6 if you screw them up. You have to buy a new one. At least it was before the chip shortage. I'm not sure how much they cost now. It might be $60 now. I'm not sure. So we're talking about the Commodore 64. It actually came with 64K of RAM. As we're talking about before, we only have 64K of addressable space. So where does everything else go? Such as like the ROM chips. So of course, a common technique used in the day is that we map these ROM chips into the address space as needed. So here's an example here on the Commodore 64. We actually have the basic chip mapped in at A1000. We have the character generator ROM mapped in at D1000. And then we actually have the kernel mapped in at E1000. And the great thing about this is that, let's say you're writing something that's in pure machine language and you don't need the basic ROM in, you can just sort of map that out and you get access to more RAM for your program. So on the Commodore 64, there's actually 5 latches that control the memory configuration. 2 of these are controlled depending on what's plugged into the expansion port. The other 3 can be manipulated by the programmer at runtime. So that gives you a full 32 different combinations here. Some of these are redundant, but if you actually follow all these here, you'll actually get a correct implementation of memory. We actually had to do a switch out of laptops real quick, so I had some speaker notes. I think this is on c64wiki.com. So it is somewhere on the web. So you have to actually just follow this table, and you're actually pretty good to go when it comes to setting up your memory. Another thing, so what we sort of talked about before is that having a huge array to represent memory is just not good enough. What we really want is actually have an array of mappings to actual memory locations. Okay? So that way what we can do is change at runtime what each memory location points to. Okay? So this is an example here what we had before. We're in the low space of memory, we actually have RAM here. And then up in the 8000s, what we're doing here is we want to map 8000 to point to the memory address 0 in the actual ROM itself. And A1 goes to 1, 8002 goes to 2. Okay? So we want to be able to dynamically change the mapping at runtime. Another thing we have to worry about is, so what happens if you actually write to a memory location where ROM is mapped in? Now, I didn't know. I thought it's read-only memory, so if you try to write to it, nothing's going to happen. Well, actually, what really happens is that if you try to write to it, it actually writes to the RAM underneath that. Okay? So we actually have to worry about actually having asymmetric access as well. So for any given memory address, what you read from could be totally different than what you write to. Okay? And for the Commodore, this is probably the only place you're going to have to run into that. But I actually did some other work as well with like a Pac-Man emulator. And that there's a lot more of this going on. So it's important to realize that this is something that can actually happen. And I only discovered this while I was actually looking at the Commodore 128 startup sequence. What I was finding was some part of the code was actually copying memory from itself to itself. So it'd be like load 4000, store 4000, load 4001, store 4001. I was like, why is it doing that? That makes no sense. Well, then I learned about this. I was like, oh. So I suspect what it was doing was basically copying the data from ROM into the RAM so that when the ROM gets spanked out, it's still available in the RAM as well at the same address space. Okay, so we've talked about all the different kind of things we might have to deal with. So let's go ahead and actually start working on our actual memory structure. Now I'm going to be writing these code examples in Go because I actually wrote my emulator in Go. Has anybody used Go? Do you like it?
Yeah.
Okay. A little bit of a pause, so maybe not, maybe not. So hopefully, if you have some programming experience, this should actually be pretty readable. It's kind of a C-style kind of language. If you're not a programmer, hopefully my narrative will be so exciting, you'll want to stay anyway. So the first thing we want to do is actually just provide 2 functions that will be the interface to our memory. We're going to have one for reading from memory. We just provide an address and returns an 8-bit value. We're going to have one for writing. We're going to give it an address and give it an 8-bit value. And we're going to do this because as long as we keep these 2 functions the same, our underlying implementation can change. So we already talked about that we don't actually want to have one huge array of 8-bit values. Instead, we want some kind of mapping. So a good way to do this is actually to have 2 separate arrays, one for reading and one for writing. And instead of actually having 8-bit values, we'll actually have functions that actually do the reading and the writing. And then we can sort of change these as needed at runtime. And if you do it as a function, it gives you the most flexibility to do whatever you want. So that way, if somebody writes to a memory location, you can actually do the remapping of memory if you want. You can call any kind of function you want. It doesn't matter. So I actually went through 3 different implementations of memory before I landed on this one. The first one, I did things page-based, because that made sense for a Commodore, but didn't for the Pac-Man. I did one where everything was just pointers instead. But then I realized actually this actually provided the most flexibility. So I'll save you the trouble now. This is probably worth doing it this way. Okay, so once you have that, then it's just easy enough to provide some functions that sort of assist in doing these mappings. So say we actually do have a chunk of memory in an array of 8-bit values. We can provide 2 functions, one for mapping RAM, one for mapping ROM, When we call map RAM, we're actually going to do the writers and the readers at the same time. When we call map ROM, we'll actually only update the readers. Now, if we want to do a single value, and this is actually useful for basically certain registers on other chips, where we want to map in one value to a specific memory location, we can provide a map read-write, map read-only, map write-only, and then provided a pointer to an 8-bit value. And then when we want full control, we can provide a map reader and a map writer and actually give it those functions that it really wants. So we'll go ahead and actually do the implementation for one of these. We're going to go ahead and do the map ROM function. This function is going to take 2 arguments. One is going to be the base address of where we're going to map this into. The other one is going to actually be the data array that we want to map in. Now, let's say this data array is 4K of values, okay? You may think we actually have to instantiate 4K worth of functions in this kind of mapping, but we actually only have to write one, okay? And we're going to use basically a closure to do this. So we're going to write one function here. It's going to take an address, return the value, and it's as simple as basically referencing into this array here and taking the address minus the base, okay? That's all we have to do. We only have to write one function. Now, to sort of go into more detail what's happening here, here's our original mapping that we had before. We basically have a ROM mapped in at 8,000. So what we want to happen is that if you do something like 8002, you actually reference index 2 into this array. So let's say we take map ROM, pass in 8,000 as the argument. Now with this function here, if you happen to pass in 8002 to read from that address, what will actually happen here is will be 8002 minus 8,000, which will give you the correct value of 2. Okay? That's how you do your mapping. And then we now just need to copy this into the address space this way, just by looping over it. Okay, so we're going back to original example here. We're actually going to try to do the original bank implementation. We actually have basic the other ROMs mapped in. So we'll first do our mapping here by calling map RAM. We'll provide a RAM variable that has the 64K chunk of memory and say map at 0,000. So it's going to do the read and write mappings for both of those. Now we call map ROM to put the basic on top. So we pass in an array with all the basic information at 8,000. They'll actually update all the readers for that location, but actually won't adjust the writers. So that way, actually try to write that location, it'll actually hit the RAM underneath. And then we do the same thing for the charge in ROM and also the kernel. And that's basically how you sort of do your mappings. And anytime you want to readjust memory, you just recall the mappings and you're good to go. Okay, so now that we actually have talked about memory and went through a quick implementation of that, we're now going to talk about the heart of every computer, which is the CPU. This is a photo from inside my 128. I probably should have cleaned it up a little bit before taking this picture. It looks pretty bad there. But the 120 is actually the 8502, it's a variant of that. So we're going to be talking about that. Of course, if you're a Commodore fan, the 6502 is your second favorite chip, because you know the first one's the SID chip, right? So if you want to be able to understand the machine you're going to emulate, you need to be able to speak in the language of the machine. And I learned how to speak 6502 by reading this book, Machine Language for the Commodore 64, 128, and Other Commodore Computers by Jim Butterfield. I'll tell you, this was actually a really good book. I highly recommend it. If you want to learn 6502, this is the book you should get. I actually still have this book. So it has survived till today. So now, if you don't have this book, there's good news. There's actually a PDF of this available up on the Internet Archive for download. The Internet Archive is a great resource. And they actually have a lot of back issues of Compute's Gazette as well. So if you're interested in those, I know what you'll be doing later tonight. Okay, so here's an example of an instruction that we would like to try to emulate. Okay, so this is the instruction to store the contents of the X register to memory location 381. In memory, it looks like this. So each instruction starts off with an 8-bit opcode. With the 6502, it's always 8-bit. The opcode for this is actually 8E. Then each instruction can be anywhere from 1 to 2 to 3 bytes in length. This one's actually 3 bytes in length. And what follows the opcode here is actually the address, which is 8103. It's actually backwards in memory because this is a little endian architecture. That's the way that works. If it feels the correct way, it'd actually be the big endian. But actually, the cool machines do it the little endian way. So, and the example I picked, the example is actually on the front cover of this book. As you can see, the 0 character there is actually saying the instruction, and then the 1 character is saying how it looks in memory. Okay, now how cute is that? So, whoever came up with that, that's great. So now we'll start working on our CPU implementation. We're going to start with the structure to begin with. The first thing the CPU needs is its view into memory. So we're going to give a pointer to our memory object we created earlier. We didn't have to work on our registers. The first thing we're going to need is the program counter. This is a 16-bit register that will tell the CPU the memory address of the next instruction located in memory. We then have our A, X, and Y registers. These are 8-bit registers. A is the accumulator, where all the fun math happens. X and Y are used for indexing. You can also use all 3 for anything you want as well. We also have a stack pointer. We also have the status register. Now, the status register contains various flags. These flags contain the results of the previous operation, or they can be set and cleared to control the operation of the CPU itself. So as we write our implementation, we're going to be working a lot with the status register, but we'll actually be working with the individual flags. So we actually want to be working with the individual bits on a regular basis. Okay? So there's a couple ways you can actually go around doing this. You can actually just have, oh, these are actually the flags. So I don't have my notes ready. I'm sorry. But these are actually the flags that we're talking about here. I'm not going to go into detail about these flags. But the one way you can do is actually have some constants here to basically represent your flags and do all your standard bit twiddling tricks to turn the flags on and off as needed. What you could also do is just provide some convenience functions. For example, let's provide a function called C that return the results of the C flag as a Boolean, as necessary. Or you could flip it around. Instead of storing the status register in the struct, you can actually store the individual flags as Booleans. And then what we could do is actually have a status register function that will return all of them or together in the times you actually need to work with the full status register. So there's a couple different ways you can do this. I picked the first way. For the remainder of today, we're going to do this way because it's a little bit easier to read the code on the screen. Okay, our basic run loop is actually quite simple. It's going to start off simple. It's going to get more complicated as we go along. But at the beginning, it actually does start out pretty simple. The main job of the CPU is to fetch the next instruction from memory and then to execute it. So we'll put our example instruction back on the screen here. The first thing we have to do is write our fetch function. In this case, it's going to get the next 8-bit value in memory according to what the program counter contains. One thing to note about the 8502 is that the program counter is actually 1 byte behind where the next instruction is. So when it's time to actually fetch the next value, you actually have to increment the program counter first. Then I'll put it in the correct location. And then you want to return the contents of memory found at where the program counter is. Now this is how it works on the 6502. Note with something like the Z80, it's the other way around. You actually want to get the value first and then increment the program counter. So something simple like that can be different depending on which processor you're working with. Okay, now we're ready to write our first instruction. So we're going to start off with a logical AND. The great thing about writing an emulator is that the programming language of choice that you're using most likely has a lot of these operations already built in. So if we actually want to do a logical AND between two values, V1 and V2, and then store the result of that in a variable called R, this is how we write it. Now, with the 6502, you can't actually basically have two operands that are arbitrary. The first one always actually has to be the accumulator. And then the final result also has to go back into the accumulator. So our code now looks like this: CPU.A equals CPU.A and V2. Now, where do we get V2 from? So we're first going to talk about the immediate form of AND. And what this means is that the value of v2 is actually going to be the value that's found in memory immediately following the opcode. So for this instruction and immediate 42, in memory it looks like this. It's 29 for the opcode, and then 42 for the value. So to get the value of v2 is really easy. We just call the fetch function that we just wrote. Now we actually have to set the status flags according to the last operation. With and, there's two that we were concerned with. One is the z flag. This is the 0 flag. It gets set if the result of the previous operation was a 0. And then we have to work with the n flag, which is the negative flag, or also called the sign flag. This is set if the result of the last operation had its 7th bit set. This is how we write it. So this is the full implementation for immediate and. It's only 4 lines of code. But there's more than one and. There's actually 8 different ands. Okay? And these basically only differ by how we actually get that value of v2. And these are called the addressing modes. So these are the actual 8 addressing modes supported by the and instruction. So we already talked about immediate. Then we have the ones we're actually going to read the value from memory instead. So in the second one here, that's actually going to read the contents of memory location 12, and that's going to be the value of v2. Okay, I'm calling it absolute 8 here. This will also be called 0 page in the documentation. We'll actually have ones where it's a 16-bit value for the address. This way you can actually, these instructions can be shorter if you can actually stuff them lower in memory. We got values indexed by x, indexed by y. We also have some indirects as well. So let's go. So this is actually the table I use while implementing my version. So you go to 6502.org. This lists every instruction on the 6502 in a nice tabular format, has all the addressing modes supported by each instruction, and then it tells you which flags are affected by it. But do you recall this is written by John Pickens and later updated by Bruce Clark and Ed Spittles, if I'm correct. So this is a very handy reference to get. So let's go back to our original implementation. Let's go ahead and write the instruction for when we want to get the value from memory location 42 instead. Well, that basically only changes by changing how we get v2. So now when we call our fetch, that fetch is actually going to be the address. And then we actually call a read to get the value from memory. That's what v2 is. So for all these, that's all we need to change. So we don't actually have to do 8 separate implementations of and. We actually only need to do one. And then what we'll do instead is actually we'll pass in a variable called load. That's actually a function. And then that function, when we call it, will actually return the 8-bit value that we need. So this way, the implementation of and doesn't have to worry about where it gets this value from. Okay? It could be absolute, it could be indirect, it could be indexed, it doesn't matter. Then what we can do is actually implement all of our addressing modes by passing in different functions for load. Let's go ahead and do that. So for load immediate, this is how the function would look. It simply returns an 8-bit value. We just call fetch. That's all it is. Now say we want to read from memory using an 8-bit address. We already did this already. Same kind of thing. We call fetch. That's what we use to read from memory. So now let's do absolute 8 indexed by x. Basically the same thing here. The only difference is after we fetch, we're actually going to increment that value by the contents of the x register and use that as the address to read from memory. So we write one of these functions for each of our addressing modes. We're doing a lot of loads here, but we actually want some store equivalences too. And then you're ready to start building your opcode table. So we're going to have an opcode table here. Basically going to have all of our opcodes that are supported by the processor, and then the functions for each one that we should execute when we see those opcodes. So we're going to do our first one here. This is our immediate and. It has opcode 29. So when that gets seen in memory, we're going to call this function here. It actually calls our and implementation, but with the load immediate addressing mode function. So now we'll do the next one, opcode 25. Same thing. We call our same and implementation again, and this time we'll pass in the load absolute 8 addressing mode function. And we just basically do this over and over and over again for all the different addressing modes, and we're good to go. Now we just have to implement all the other instructions. So for the 6502, there's a total of 151 opcodes. As you can see before, we don't actually have to write 151 functions, but we do have to write 37 of those. Some will be harder than the one we wrote, but some actually will be easier. Actually, 11 of them are so trivial, you can write them in a single line of code. Now, my full implementation was 599 lines of code. So if you think writing a 6502 CPU emulation is a huge undertaking, it really isn't. Okay? Now, I did write 2,800 lines of test code. Now, part of that is I didn't write them efficiently. I did a lot of cut and pasting. Don't tell anybody that. The other thing also is that you really, really want to do as much upfront testing as you can now, because any bugs you find now are easier to solve than later on when you're running the kernel through your emulator, and then something doesn't work there. That's going to be a lot more difficult to find out. So do the best you can up front. Do as much testing as possible. Okay, now we're ready to write our CPU function called next. And what next will do is basically just execute the next instruction. Okay, we've already done this already. So we're going to call fetch. That returns the opcode. We're then going to look up that opcode in our table, and that's going to return the instruction function that we want to execute. Then we call the instruction, and we're good to go. It also returns a value called OK, which is a Boolean, letting us know if that opcode was found in the table or not. And if it wasn't found, well, then it's in legal instruction. There's nothing we're going to do at this point. Now, on a real CPU, if you give it an legal instruction, it's going to try to do something. But we're not concerned about that right now. Okay? If we're trying to run something that's using illegal instructions, we're probably in over our head at this point. So a better option here would actually be to log this out, put some kind of warning, so that when you're actually testing this kind of stuff, if you have a condition you're not expecting, at least you're notified of it. So I highly recommend that. Now we're ready to go back and modify our run loop. And it actually is now time to create our machine structure. This is what we're going to use to collect all of our various components of the machine we're emulating. So far we actually have memory. Actually also have our CPU. Now we're going to write our run loop, which is pretty simple. Basically, it's going to call CPU next and do that in an infinite loop. So that's how we get started. Once you've done all the instructions, it's now time to do some minimal tooling. At a minimum, we need a memory inspector. We want to be able to view the contents of memory at runtime to make sure the computer is doing what we expect. And of course, at times, it's not going to do something that we expect. And in that case, we may want to trace the execution of the CPU to sort of get a clue of what's going on. In order to write that, we're going to need to have a disassembler. And as bonus points, you can take all these tools and bundle them up into a runtime monitor. You don't necessarily have to do that. I find writing this tooling to be fun. So I spent way too much time on the monitor. I shouldn't have, but you know, it's a fun project, right? Okay, so now, after we've done that, we're basically ready to sort of power on this emulator to see if it does anything yet. There's only a couple more details we have to take care of. We actually do need to get some ROMs and load this into memory. We're doing the Commodore 64, and we talked about earlier, there's actually 3 ROMs we're concerned about. The best way to get these ROMs is literally just go download the Vice emulator, install it, go look through the file system so you find the ROMs, and then copy them over into your emulator. We then have to handle the CPU reset. When the computer is first turned on, the reset line is asserted, and at that point, there's the reset vector located at FFFC that contains the address of where the program should start on a restart. Now, we don't have video up yet, but what we can do at this point is actually just look at video memory. And that's located at 400. So what we're going to basically do is look through there and see if we actually get the classic Commodore startup banner. So let's turn it on and see what happens. And if you do it the first time, you're going to get this. Okay? This is a whole lot of nothing. Well, actually, it's a little bit of something, because actually these are all 20s, and 20 is the space character. If it was actually a whole lot of nothing, it actually would have been a whole bunch of zeros. So, you know, at this point, you know, probably It did try to initialize, it cleared the screen, but it didn't make it any further than that. So why did this happen? I don't know. So this is where you actually go through and actually say, okay, let's try to trace the execution and see what happened. So when we do that, we start looking, and you can see that the CPU is caught in this infinite loop here. So what it's trying to do is actually read from memory location D012, and it's branching back on itself until that value is 0. So for some reason, this is not 0, and it's waiting for that to happen, and it's never going to happen. Why is this memory value important? I don't know. I am not a Commodore expert. But you know who is an expert is Sheldon Lehman. He wrote this book called Mapping the Commodore 64. And in this book, it actually details every single memory address and tells you what it's used for. I don't have a copy of this book, but once again, you can get a PDF of this off the Internet Archive. So if we download the PDF and open up to the page that talks about D012, what it'll tell you is that this is actually a register that contains which line on the video screen is currently being scanned. So what I suspect is happening here is that it's actually waiting for the video chip to initialize, and it's waiting for that for the scan line to get up to the top for the first time. That's just my suspicion. I'm not sure if that's the case or not. So what do we do here? We haven't actually done anything with video yet. We don't necessarily care about this. So basically what you do here is you basically just give it what it wants. So at the beginning of our for loop, we're always going to write 0 out to D012. Okay? Is this correct? Absolutely not. Will this work? I have no clue. But the fun of writing an emulator is trying these things out to see what happens. Okay? Our main concern right now is just trying to make more progress. Right now we're stuck. It's waiting for 0. We'll give it a 0. Now, sometime later, you may actually want to fix this. So it's important to take notes and remember that you actually put this in. You don't want to come back 6 months later and totally forgot that you had done this. So when we do that, let's fire it up again. Now when we look at memory, we actually do get the classic startup Commodore 64 banner. The problem is, with my implementation, when it came up for the first time, it actually said there are 0 basic bytes free. Well, there's definitely more than 0. Why is it saying 0? I don't know. Maybe it's trying to take the total value minus the used, and that's the free. So maybe there's a bug with my subtraction. So I went looking through the subtraction code. I couldn't find anything wrong with it. I suspected maybe a couple other instructions as well. Didn't find anything there. So I did a lot of upfront testing, but it looks like my testing wasn't comprehensive enough because we still have a bug. So what do you do in this case? Well, you go find somebody else who wrote tests. So I found this repository here. This is written by Klaus Dorman. This is actually a test written in 6502 assembly, meant to be run on an actual processor. And the way this test works is that you run it, and eventually the CPU will get trapped at a certain memory location. At one location, it means the test was successful, everything is correct. If it gets trapped elsewhere, that means you have a problem. And where it gets trapped will give you an indication of what the problem is. So I ran this through, and of course, there was a problem with subtraction. So I actually looked through that a little bit more in detail, and I realized that I actually set one of the flags wrong. So I fixed that, and now we get the correct startup banner. Everything's looking great. So now it's time to move on to video. I was actually hoping to spend quite a bit of time talking about video, but with only an hour, there wasn't actually enough time. So for this last bit of stuff we're going to be talking about today, we're going to go through this pretty quick. So I implemented it using SDL2. That's a simple direct media layer library. And for video, what we want to basically do is have a window that pops up with a display. And we want to render a frame 60 times every second. In order to render that frame, there's a couple places we want to get information from, one being the background color, that's stored at D021. We need the border color, that's stored at D020. And then we actually need the text. We've already looked at that before with the monitor. That text is found starting at memory location 400. And then the color RAM is actually stored at D800. So, and the basic strategy here is you actually want to have two images. So the first we want to do is actually generate a tile sheet over here. So we're actually going to look at the character generator ROM that contains all the bitmaps for the characters we want to display on the screen. So we have to do this once. On startup, we just create a tile sheet here of all the possible characters that we have. And then we'll have another image, which will be our render target. So each time that we need to render a frame, just blank it out with a background color. Draw 4 rectangles. That will be the border. Then for each column and row in the text display, you basically just want to find it in here and then copy it over to there. That's all to do video to start, at least for text video. So, and actually a lot of things on the Commodore was text video anyway. You play some of your favorite games, it was text mode. It didn't look like text mode, but it actually really was. So once we do that, we get that up and running, and we actually have a beautiful start screen at this point. But what we don't have yet is a blinking cursor, because we actually haven't dealt with interrupts yet. Okay? So 60 times a second, the CPU is interrupted to perform certain administrative tasks, such as blinking the cursor, and scanning the keyboard and stuff like that. This was a nice animation of a blinking cursor, but not with a PDF. I apologize for that. So 60 times a second, there's a tug on the IRQ line. When that happens, the CPU finishes execution of the current instruction, then it starts the interrupt sequence. It does that by pushing the contents of the program counter and the status register to the stack, then sets the interrupt disable flag so it doesn't get interrupted while doing the interrupt, and then transfers control to the interrupt service routine. Memory location for that is actually stored at FFFE. That's the interrupt request vector. And then that actually runs until it hits an RTI instruction, return from interrupt. And then the sequence goes in backwards. The return execution to the original program. So now we have that. Now it's time to do the keyboard. Now what we can do at this point is that we can actually cheat. Okay? We don't actually have to do a full keyboard implementation. Now we can sort of take advantage of the fact that we know how we can actually do the work for the computer ourselves. So we know that there's actually a ring buffer at memory location 277. That's a 10-byte ring buffer that contains the keys that have been pressed. Indexed into that ring buffer is stored at C6. And what we can do here is we'll actually pull SDL for keyboard events. When we get an event that one of our keys have been pressed, we take the Mac key or the Windows key or like that, convert it to an appropriate Commodore key, then we can just stuff it directly into the buffer itself. Okay? This is cheating, but this is the easy way to start. So when in doubt, you can try the cheat first to see if it works. And if it doesn't, that's great. You can actually just go ahead and do a real implementation. But right now, we can try the cheat to see if that works. The other thing you have to be concerned about is the stop key is handled separately. That's actually stored at memory location 9.1. I basically mapped the run stop key to be basically press Control C. Okay? Once you do that, run that, you get an emulator up and running. Everything's looking great. You can actually finally type in your Hello World program. This basic program is a little bit more complicated. Actually, my basic is so rusty, I actually had to look up how to write this. So, this is basically everything you need to know to write a basic emulator for 64. I'll let you decide if that was a pun, if it was a basic emulator. So once you've done that, you got a working 6502 implementation. You can continue to work on the 64. You can actually do some other Commodore stuff if you want to. You could do a 128. You could do a VIC-20. Why not? Or you could actually do some other things as well. Some of my favorites have 6502s, such as the Atari 2600, Apple IIe, Nintendo Entertainment System. Now, I haven't tried any of these. I don't know how difficult they are. But once you have something up and running, you can actually use that work for something else. Okay, so that's basically it for today on how to write your basic emulator. Now, in the event I've inspired anybody out here to write their own emulator or to give it a try, I do have a couple of tips for you. One thing is, at the very beginning, you need to collect as much documentation up front as possible and make a copy of that documentation. With the internet, if it's there today, it could be gone tomorrow. Example is, when I was doing the Pac-Man emulation, there was this great document, 8 to 10 page document, on how to do a Pac-Man emulator, written by Chris Lamont. It was beautiful. I used it, got it working. I went back later to check it out, it was gone. He got a cease and desist letter from Namco. Apparently that stuff is a little too valuable to have around. So don't rely on it being there tomorrow. If you see something great, take it and save a copy. You also want to do as much research upfront as possible. You don't want to get halfway through the project and realize you're missing a critical component that prevents you from actually finishing your project. Also evaluate the complexity. Some things will be easier than others. A 6502 is only 150 opcodes. It's not that bad. Now a Z80 is more like 1500. So it may not actually be more difficult to do the Z80, but with 1500, it's a lot more you have to get correct. And doing the first 100 opcodes can be kind of fun, but getting towards the end can be quite tedious. Also requires a lot of patience. A lot of things are going to go wrong. It's going to be a lot of puzzle solving. You got to be up for doing that kind of stuff and enjoy doing this puzzle solving. You got to realize that failure is an option. It's really about the journey of writing the emulator, not about getting to the final destination. And that also smaller projects are fun too. So I do have my code that I've written for this up on GitHub, located here. This is an email address you can contact me at if you got questions after this. But in the meantime, we got 15 minutes for Q&A. Does anybody here have a question? Now, I may not have all the answers, but I can do the best. Yes?
Do you have any sense at the moment, because I know because you're writing it in this other language.
Yes.
Swift or Go, I forget.
Go, yeah.
I'm sorry. What is the relationship between the execution of your emulator versus what C64s were like in their, in their own sense? I mean, I would expect you don't have to be cycle accurate. You just need to be instruction capable. So what's it like?
Okay, so cycle accuracy is a lot of work.
Oh no, I didn't.
Yeah. Well, yeah, oh yeah, I know. So I'll tell you how I handled it. So for this, at first you don't worry about that. So you let the CPU run at full speed. Okay, especially when you're running tests. You want to run tests as fast as you can, so you run at full speed. Actually, when you actually start running the real emulator, you don't want it to run full speed because it's going to drain your battery pretty quick. So, and when you actually have to do the video display and stuff like that, that happens every 60 seconds. So your run loop at that point is draw the display, handle your interrupts, and then run the CPU a bunch of times. Okay? I was actually lazy. I didn't even do the calculations correct. I was just kind of like 20,000. So I did like 20,000 instructions per loop. And it worked. It's not necessarily accurate, but it's close enough. So, and of course, you can make it go really fast if you want to. That's part of the fun too. So, you got any other questions here?
Oh, just a comment.
Sure.
You mentioned Archive or Internet Archive.
Yes, it is a great resource.
All of the Commodore materials are curated at bombjack.org.
Okay.
And they've got all of the books, all of the magazines, and they're collected specifically around this topic. Like when you were trying to understand what was happening in the ROM where you were disappearing into nowhere, I thought about Dan Heeb's toolkit kernel, which basically does a byte-by-byte description of what the kernel ROM looks like. So if you're trying to debug where you're stuck in it, you can read into it, and it gives you a narrative description, not just an assembly breakdown.
That's another thing to point out is that it's actually really fun to do this now because there's been so much work done before. There's a lot of documentation. There's a lot out there right now. Your chance of getting stuck is actually not that bad because there's so much documentation you can find. And if not, you can ask on the forum somewhere, and somebody can help you out. And basically, the method of last resort is to go read the MAME source code. So you can do that as well. Or Vice source code, sorry. So I do got one more story, if you're all interested. So when I was doing the Pac-Man emulator, I was having a problem where a certain part of the screen wasn't displaying. I didn't know why, okay? And I was pretty confused by that. Now, the Pac-Man machine doesn't need a full 64K of memory. It really only goes up to like 5,000 or something like that. But when I was running my emulator through, I saw that there was a lot of things being written to high memory for some reason, up in the C-thousands. Like, well, that doesn't make sense. Why be writing up there? There's nothing up there, okay? But I couldn't figure out why these two things on the display weren't working. And this is actually in a track mode. So what was missing was the high score and then the credit display. That's kind of like two odd things to be missing, right? I was perplexed for the longest time, and then actually went and read the main source code. And what actually happened was on actual Pac-Man arcade cabinets on the Z80 chip, they didn't hook up the A15 line on the address bus. So the A15 was completely disconnected. So what was happening is that when they're actually trying to access high memory, with that not being hooked up, it was actually properly going right into video memory. And I suspect it was actually a copyright protection mechanism. So if you actually try to put Pac-Man ROM in an actual working Z80, then it wouldn't look right. And I suspect it was just because if you're an operator and you're going to put this in location and try to make money, people don't want to play if they can't see how many credits you don't have. And if you don't have a high score, well, then what are you going to be shooting for? So those are some of the issues that you run into. So, any other questions? Yes.
Run into an instance where there was a hardware bug that you wanted to implement, and because obviously you're not doing cycle accuracy, so you'd have to do that in a different way.
No, never got to that kind of specifics in there. What was interesting is Pac-Man is notorious for a bug. If you get above like level 255 or something, that completely freaks out. So it's kind of fun to actually do the emulator, put it up, get to level 255, and see it freak out. I was like, well, then I must have done it right, because it actually freaks out in the same way. One thing to note on, when I gave this presentation at MagFest, I gave a less technical one. That was actually more about telling stories than actually doing technical stuff. I was asking if anybody there had brought a Pac-Man machine with them. Out of all places, I think MagFest would have been it, but nobody had one. Apparently there's actually a switch inside the cabinet that when you press it, it actually just advances to the next level. I don't know why that exists, but apparently it does. So apparently, I think you hit it like 255 times and you get to the kill screen. So, yes?
I noticed that you kind of skipped sound emulation.
Yes.
An important part of an emulator would be sound.
Oh, it is,
Right?
But like sound's like a whole topic just in itself. So, you could actually do sound just by itself, right? You could actually just write your own SID chip player and all that kind of stuff without the sound. For the Commodore, I didn't do sound. For Pac-Man, I did, because I wanted to get something working. And it's probably about 96% correct. It sounds like Pac-Man, but it's just a little bit off. Yes?
Kind of a similar question. Did you implement any type of way of loading like cassettes or cartridges or code from the outside that you're not putting in?
Okay, so disk, when you're talking about disk, a disk drive is basically a full machine in itself back then. Actually, it had a 6502 in it too. That's just way too complicated. You could do tapes like that. I decided to take the easy route out, and what I would basically do, in my monitor, I would actually directly load files from my disk and just stuff it straight into memory.
Like paste them in?
Yep. But I would actually have like a load command in the monitor to do it. So one thing to note about that, if you're loading in something that's like a basic program, there's actually two pointers that you're concerned about. One that's the start of arrays for your basic program, and one that's the start of variables. And they actually initially point to the end of where the program is. So if you load in something directly like that, doesn't know about it, you actually have to adjust the pointers to be right after that. If not, when you start running the program, we'll actually start overwriting the program. So I just did it that way. I got enough up and running. I could play some basic stuff like that. I was actually going to give a quick demo today, but that's not going to happen. So. Anything else? Okay, well, I'd like to thank everybody for coming out today. Hope you enjoyed the talk.
Thank you, Mike. Thank you very much.
2, 3, 4.
Yeah, sure.
Okay.
Yeah, on my things.
Okay.
I'm not done a test run of it, so I have no idea.
You what?
I'm not done a test run of it, so I have no idea.
Not professionals. This is pretty loud. This is supposed
People in the hallway, come in. This is an awesome talk. Come listen, learn something.
I'll be that microphone or this one?
No, I'll just use
Good.
We good to go? Rolling? Okay. Hi, everybody. Next talk is Johan Grip talking about reverse engineering Commodore 128. Here you go, Johan.
Yep.
Thank you for coming.
Thank you very much. So yeah, this has been my project for the last 3 years. So the talk is titled Reverse Engineering the Commodore 128, or as I'd like to call it, how to find every single rabbit hole and jump into it head first. So who am I? Well, I'm just a general nerd. Computers, electronics, old cars, mechanics, you name it, I probably tinkered with it. I'm entirely self-taught. I basically have 9 years of grade school, and that's the end of my education. I've been working in enterprise IT now for 30 years. Network engineering, software developer, database admin, you name it. Once again, I've been all over the place. Yeah, it's just how I grew up, tinker with things. Why did I get into all of this stuff? Well, I got my first own computer, this exact machine, on my 10th birthday as a birthday gift. I still have it, miraculously enough. It's been dragged along in boxes and whatever all over the years. It's a bit beaten up, it's not exactly pretty anymore. Of course, when I turn it on, further background and inspirations. So I've been following the Amiga project by John Hertel in Sweden. He in turn inspired a bloke in the UK called Rob Taylor, who made the 60 clone, among other things, and also the Amiga 500++, which is the one on screen there. So I was tinkering around a bit with this, and I realized that as I was repairing the 128, it had corrosion on the board. So I figured if I have corrosion on this board, other people will have the same type of problem, so maybe I should just make a new PCB you can use to repair these old machines. I mean, I want to preserve them for the future. So I set some goals to myself, because I've learned to set goals before you start projects, otherwise they will not end. So my ultimate goal is to just preserve the 128 platform. I love this machine, I always have. I wanted... Yeah, so the other thing I wanted to do is all the 128 boards, at least the wedge machines, have quite a bunch of factory fixes on the board as they come out. There's yeah. So there were little traces cut, resistors soldered on the underside, bodge wires, etc., etc. And I also wanted to try, if possible, to make small quality of life improvements, you know, the simple things that make life easier dealing with these machines. So as my goal was to preserve the platform, I wanted to use the appropriate software as such. It was always, the goal was always to make this whole thing open source. So I wanted to use an open source software to facilitate that, because if you have the open source files, I want everybody to be able to have the software to also utilize those files. I could have used Eagle or Altium or whatever, but then you have always that little threshold you have to get over. The easiest way to do this in some ways is a small German piece of software called Sprint Layout. The reason behind that is it allows you to import a bitmap image and use as a background. So you can just redraw the traces on top of that bitmap. With KiCad, I have to do it slightly differently. You can still do it, but it's possible. The other nice thing with KiCad is, of course, it's a full EDA suite. So I started doing a schematic capture. And as you can probably tell, this was actually the first time I made any substantial schematic, and it was a train wreck. It was functional, but not very useful per se. So over time, I have learned more and gotten better, so it looks a bit neater nowadays. So I kept it, it's a hierarchical layout, and I tried to keep it so that you can actually see the main blocks of the system and the buses, but all of the small control signals, etc., are just global signals. So it's kind of a hybrid approach, but I like it quite a lot. To help me along with this, I have to say the Commodore schematics were incredibly accurate for this machine. Very, very straightforward. So I think the biggest issue I found on the original factory schematics was a missing ring on an inverting buffer on the output. That was literally it. Yeah. Everything else has been absolutely spot on. The bill of materials has some issues. But on the other hand, I always also preferred to work from the PCB and the way the PCB is set up and what components were on the actual PCBs, because that machine worked, right? So anything else can be a bit here or there, but the PCBs at least actually work. So I always tried to do that. I also did not attempt to preserve the layout of the original schematics in KiCad because it didn't really make sense to me. I can do hierarchy, I'm not limited to the amount of sheets that I can use, etc. So it made more sense to me to just start splitting them up a bit. And for certain things, I mean, do I really need to see the reset signal traced all over the place, or do I just use a global label for it? I know what the reset is, I use a global label. That's one of the things I learned from the first train wreck of a schematic. So now that I had the schematic entered, this took a couple of months just to make sure that I got it all in proper and learning the softwares, etc. It was time to do the PCB, and at that point, you start by taking a board and you desolder everything, right? And by desoldering it, I mean you desolder this component, you look at it, you measure it to make sure that it is what it says it's supposed to be. So you make your own BOM from the existing board.
Was that a working system, or did you sacrifice a working system?
I did sacrifice a working system for this, but I basically considered that it was for a good cause and I was going to reuse the chips anyways.
That must have been hairy that moment you decided.
Yeah, yes, to some degree. I mean, it is a nice working machine, but on the other hand, I'm going to rebuild it. So I figured, whatever. On this first one as well, I also sanded down the solder mask to get a clearer, nicer picture, which did help a bit with KiCad, because the problem with the current process of doing this in KiCad means I have to take that scanned image and convert it into a monochrome bitmap. So if I do that with the solder mask and the silk screen in place, I get a bit of a jumbled mess and it can be really hard to parse. I tried that approach at first, but it was really, really hard. I then just grabbed the board and took it with me to work, where they have nice A3 flatbed scanners, and just scanned it away. Which is a very nice way of doing this, because putting it in a flatbed scanner means you get a very consistent and predictable DPI. That makes life a lot easier later on. So when I then convert this into a component in KiCad, I can enter the DPI, and it will be dimensionally accurate, which is very, very nice. So once you do that, you import the scan as a component in KiCad. So the faint green lines is the bottom layer, and the faint blue lines are the top layer.
That's where you change the shape of the hole? Is that the hole on the left there?
Yep, exactly. It was easier to make it just a square with rounded corners. Yeah. So the first thing you do is just place all of the components, and here I learned a lesson a lot later. I should have picked a fixed grid for the components and shimmied them around a bit instead of slavishly following the original PCB, because I ended up having PCB traces that were a bit too close for holes, and I had a lot of micking around to make them nice and even and get clearances as they were supposed to be. And then you just sit down and draw all the traces. Bring patience, lots and lots of patience. Lots of patience. And if you look at the amount of track segments down in the corner, I clicked all of those. Yeah. And I was just about to say exactly that, right? It was a lot of work for me. I did this over a period of about 3 months, evenings, weekends, etc., just to put it in there. And then when I was done, I realized that Bill and the boys did this in a week, and I was just copying. They had to figure out where to put all the things and calculate on all of the impedances and all of that type of stuff. And I'm just, yeah, okay, I understand the RIP comment on the back of the board now, absolutely. No kidding about that. So, yeah, that ended up pretty nicely. It was a lot of work.
Is that accurate? 14,430. Oh, I'm sorry, 464 nets.
464 nets, yes. The track segments are just individual bits of tracks, yeah. So, no, it's probably the net segment is accurate. I have a lot more track segments than you did because I added a few tiny bits. Yeah. So once I had all of that done, I generated some gerbers, figured out how to actually order PCBs, found the only vendor that seems to be able to do a board of this size because it's 16 by 10 inches. So you look at an ATX motherboard and go, oh, that's nice and tiny.
No excuses.
Yeah. Well, I also have to say, it probably couldn't have been smaller because this thing is packed. It's a 2-layer board. Yeah. So I got all of that sorted out. I ordered my first set of prototypes, soldered one up. That took me 2.5 days to solder up the first prototype. That's when I learned the real value of having the component values on the board, which I then added on all the other revisions after this. Yeah, and as a comparison, building one for me today takes just about 6 hours from start to finish, and just hand soldering. So as you can probably tell from the wires, I got the footprint for the AV DIN completely wrong. I forgot other convenient things like, mounting holes. Who needs those? So, but I soldered it all up. I plugged it in, and it worked on the first try. Wow. Except. And that error confused me quite a bit, because it was weird, and it was also flickering a bit. So, and then I realized I was using the international version, so if you look at the character ROM, it has this happy little carrier board. Because the original character ROM is a 2364 mask ROM from Commodore. It does not fully use a standardized JEDEC pinout. So when they sold these internationally, they wanted to put the European characters in the ROMs. They made a small carrier board to adapt the pinouts to make it work. Except they couldn't make it straight through with just the pins. So there's a little cable that goes for address pin 11. I'd forgotten to connect that one. So it was just floating, and the ROM was just giving different data, just randomly. And that ended up with just, for some weird reason, some letters were lowercase. So I guess it just flowed over from the next...
Was on the bus the last.
Yeah, exactly. So I plugged that one in, and it's just been fine ever since. So I was still absolutely in shock that it actually worked on first try. So that was interesting.
Did they have that same carrier board on C64?
I haven't looked, actually.
Yeah, because at no time did somebody say, hey, someday there will be
Yeah.
an international chip or fob ROM. We never even was on the radar.
That's funny. We'll come back to that one, actually.
Okay.
Yeah. So, speaking of some of these fixes, so one of them is R102, which is on the schematic, but it wasn't actually on the board.
That's a series terminating resistor, I assume.
It is a resistor on the 1 megahertz clock, splitting it into two buses. Yeah, I guess it's for impedance control.
It's for absorbing the reflection.
Yeah, exactly. So that one was just stuck on. They cut a trace and they just soldered it on the underside. So, of course, I did a bit of jiggery pokery and I managed to put a place to locate it close to its original location. So that worked out fairly well. That was probably the first fix that I did on the board.
Were you aware of fixes like this? They inserted a series resistor on one of the clocks. Were they using you to keep production, or was I know Kalea did some babysitting of production? Not too much, no. Yeah, I didn't know there was any fixes, and there's a handful of them on this. Those are probably just production engineering fixes. Yeah. At that point, later on, we definitely had real production engineering. I'm not sure about. Oh, okay. Yeah, I was gonna say, because I'm normally pretty good about putting those resistors in there.
Yeah. And then the next fix that I have documented here is one of the jumpers, which is, there's a jumper that will allow you to use larger ROMs, which were then used in the DCR later on. So you could have 2 ROMs instead of 4 for the system ROMs. It's drawn as A14 in the 128 schematic, as A15 in the DCR, and A15 is what it needs to be. Yeah. So I actually did a trial run before I fully understood the reasoning behind this one. I actually did a trial run where I put a jumper for A14 or A15. That board never were stable. Just adding that jumper and those 2 address lines a bit too close, it made the board meta-stable. It worked for an hour and then it would just freeze and then you reset it and it worked for a little while longer. Certain demos tended to just trigger it to freeze instantly. It would just crash exactly here. So,
You just described my nightmare scenario while working on
yeah. Yeah.
It just fails every now and then. That would be the worst thing.
Yeah. So those things are just a nightmare to debug and troubleshoot, obviously. Yeah. So, yeah. So, coming back to the international one, J7 jumper on the board is documented as using either the 128/64 mode signal or the caps lock key for selecting which font to use in the ROM. So, at some point, this was thought about for being internationalization, right? It would have had to be. Yeah. Yeah. However, if you look on the J7 jumper, you will quickly find that it's not very useful.
We didn't use it.
Yeah. So what they ended up doing, as on the left-hand side for the international machines, they cut a trace and soldered in a budge wire, the brown one. So whenever you find a machine with that little carrier board for the EEPROM character ROM, you will also find this budge wire in place. So what I did was I just reran the traces and made this jumper work. So now you can just jumper between caps lock or 128/64 mode for the font ROM. So that was pretty much bringing it back to the intention of the schematic in essence. So, there were a few more fixes. I didn't put them on slides, unfortunately. One of them, which I discussed with Bill earlier, is for the read-write signal coming out of the CPU complex. There was an additional gate added before it went to all the chips in the system, except for one chip, which is the VDC chip, the 80-column video chip. And I thought once again that it might have been something for impedance or whatever, But as I was discussing it with Bill, he mentioned that, yeah, no, we did that intentionally because we wanted the VDC chip to get the read-write signal a bit before everybody else. So they added an extra buffer gate, a driver gate, just to delay the read-write to the rest of the system, probably to make the VDC a bit more stable. I'm not going to say stable, just a bit more. So yeah, that was pretty interesting. I'm sure there were more little things like that I did. I didn't keep a change log when I was working on this either, unfortunately. I should have. Lessons learned, I do now. So at that point, I was pretty much done with this PCB. I'm working on a few small fixes, just more quality of life, breaking out the address bus on headers so that it's easier to do mods for users. Some of the restore signals, the XROM and game signals, you know, the type of things you might want to tap into for doing modifications. I also brought out, there's one pin on the AV DIN that is not used, it's unconnected. I brought that one out on a pin, so if you want to install a second SID, you can just bring this audio signal out there without having to do silly things. And just because I could, I put a jumper to ground the audio in to avoid any noise leaking into the SID chip. Yeah. And just small things like that all over the board. The other thing I did on the latest revision, which I should have put up here as well, is I added guard traces, so just ground traces around the video signals coming out of the VIC chip. So just grounded on both sides, all the way out from underneath the chip. And I was expecting it to have a bit of a help a bit with the jail bar issue, because the 128s are fairly notorious for having severe jail bars. And to my surprise, when I started one of those boards the first time, the jail bars were gone, almost gone. There's really faint traces of them left, which I suspect is not going to be fixable easily because they're probably from inside the chip. Because the 1 megahertz signal is sitting right next to the video outputs.
Yeah, I think that was our assumption at the time. Is
Yeah.
I never tried to troubleshoot that noise. I troubleshoot ground noise, but I assumed it came out of the chip noisy. So I'm impressed you were able to. Now I'm kicking myself going, oh, we could have done that.
Yeah, yeah, no.
We could have put that ground in there.
And really interestingly,
We had an extra day. Yeah.
leading up to the next slide, I've done some other PCB work since. So I managed to locate and find one of these, which is a 128 CR board. That's a cost-reduced version of the 128 wedge machine. Not a lot of people are even aware this exists. I wasn't until I really started digging around in things. There's no official schematics that I've found anywhere. And yeah, exactly. Yeah, the only reference I have ever found, official reference I have ever found to this board's existence is in the original Commodore kernel source code, where revision 6 has a reference that this is to support this board, etc. Yeah. So I reversed engineered that board, and as I kind of expected from the start, it is the DCR board design with the floppy drive portion chopped off and with a new power supply bit stuck onto it. Yeah. So it was a yeah. So I reversed engineer that board once again, desolder all the things, measure everything, build a BOM, do the schematic, etc. And that's now the only existing schematic for that board that I'm aware of. So I did not fully finish reverse engineering the PCB because it's very handy to work on both the schematic and the PCB at the same time, obviously, because the schematic validates the PCB, which validates the schematic. It just goes both ways. You always compare it to the board. If the schematic is off, you can't connect the trace in KiCad. So it's very useful having both of them available. So I didn't finish that board. All the signal traces are done. I just did not finish all the copper fills and all the power connections because I was pretty tired at that point. So I will pick it up and finish that at some point. It's also a bit odd, this board, because it's slightly smaller than a 128 board. It's about an inch shorter on each side. So I don't think it's much of a difference to make any significant cost saving, especially when you consider that if they wanted to, yeah, and if they wanted to make it efficient use of it, they'd have to tool a new case. Yeah. So what they did instead is they just heat inserts into the original case. So they're easy to locate by just flipping the case, and if you see these brass inserts heat pressed into the case, it's going to be one of these. So I also brought along one of the finished articles. So unfortunately, I could not find somewhere that would do this with hard gold on the edge connectors. Oh, I can find plenty of places that will do it for me, but I'd rather buy a house, I think. So JLC PCB will do this with ENIG for a decent amount of money. And I've tested their ENIG plating on the card edge connectors, and it seems to be fairly robust, I have to say. And besides, if it breaks, you just build a new one. So, that's pretty much what I've done for the those parts. I started reversing the 128 DCR just to complete the collection, because that's the last PCB revision that I'm aware of. Unless Dreen in Argentina did something really weird with theirs. But as far as I understand, the Dreen 128 was only sold in a couple of hundreds in total, so I don't have much hope of ever finding one. Yeah, and I'm also planning on doing the 128D drive board, because it is a 1571, but it does not have the same shape as the standard 1571 board. So just for completeness, I want to do that one as well. So that's pretty much what I've done for all of the PCB work. In parallel, I bought a microscope. I was using that one just for surface mount. That's what I bought it for. So, and at some point, of course, you get interested in, you start seeing people looking at silicon inside the chips, etc., and you get kind of half interested, but I really didn't want to start digging into all of those nasty chemicals. So decapping a chip, so just decapsulating it, removing it from the epoxy, the traditional way is using fuming red nitric acid at 60 degrees centigrade. Yeah. Which should be enough to make most people just go, whoa, 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 hang on, no, please. The other option, which is slightly nicer, is you can use rosin. Rosin. Just like you would use rosin flux. You can use the actual resin from conifer trees. Chuck it in a test tube, chuck the packaged chip in there, heat it up on a Bunsen burner, let it simmer for a long time, and it will actually slowly eat away at the epoxy. Yeah. So that's a lot more gentle. Yeah, it's largely inert, but it is a bit etching, so it slowly eats away at the epoxy, and it seems to leave the dye itself alone. So that was all right. I was planning on tinkering with it when I found a YouTube video by a Frenchman called Antoine. I've discussed quite a bit with him since, because we share our hobby with microscopes nowadays. And what he did, he came up with a clever trick of just taking the packaged dye and heating it with a hot air gun, or your hot air station, to about 350 degrees, at which point the epoxy actually becomes brittle. So now you can crack it off just using a pair of pliers, and of course most of these boards have this little ship carrier sitting underneath it like a metal plate. So if you're really nice and careful and gentle, it takes a bit of practice, you can actually pop the die out with no problem. It comes out nice and clean as well, which is really nice. I was really surprised. I watched the video and I went, that looks easy, let's try it.
What happens to the bond wire? Yeah, exactly.
You rip them off.
And they don't tear the pads off?
Sometimes they tear the pad off, but that doesn't bring a lot of the rest of the ship.
It's not like a PC board where...
No, it just rips a hole in the pad and that's it. So it works pretty all right. Often they actually get stuck, they rip somewhere else. And my solution to that has been you chuck the whole die into the ultrasound and they just fall off.
I have never talked to a person that used the sentence, yeah, we just ripped the bond wires off.
So if you're interested in that one, the YouTube video is actually called Ships à l'Antoine. Yeah, so that one is actually pretty nice, interesting to watch because it is pretty fun actually to crack these things open. And yeah, I did have a jar of busted Moss ships, so I didn't sacrifice anything working for it. So what I did was I took the PLA apart. So I just cracked one open. The image on the left is the first image I ever took of a silicon chip, so the actual die inside. The one on the right is my first interpretation. I pinned out where the legs went by figuring out where the power connections are. They're fairly simple to locate. And then I started quickly seeing the difference between an input pin and an output pin, because the output pins have power drivers. Yeah. So by just looking at those things, I could figure out what the individual pins were on the package, and now I'm starting to get a bit interested. Yeah. So I bought a microscope. So at this point, I'm going up to slightly bigger boys. This is a metallurgical microscope from Amscope. When you get into some proper magnification, of course, you will not cover the whole die with just a single photograph. So you need to motorize it. Motorized microscopes are expensive. So I found a new rabbit hole of building CNC hardware. So I built my own, I motorized this one all on my own. The one on the picture here has motorized XY and also tip and tilt. Because the way I work is I glue the silicon dies to a microscope slide. And of course, you never get them full level because the backside is a bit gritty and etc. So I use the, it's just a small tip and tilt table from optics labs. They use them for leveling lasers and those type of things. And it works just fine to just level it out so that I can move in X and Y without losing focus too much. It's a bit of a trick to get it balanced, but you figure it out. And to keep it nice and simple, I had an Amscope camera that I bought with the microscope. It's nice, it's adapted to the optics, but it does not run in Linux at all. And in fact, it doesn't really have any proper drivers per se. You have to use their application. I didn't like it. So I ended up using the Raspberry Pi high quality camera that you can buy now for decent enough money. It comes with a C-mount, and the microscope actually had a C-mount. So that was pretty nice and convenient. I just slapped it on there and it worked pretty fine. It's not parfocal with the eyepieces, so you have one focus setting for the camera and another focus setting for when you want to watch it through the eyepieces, but that's what it is. Then I built a small control board on the side, just using normal stepper motor drivers and an ESP32. So that worked out pretty nice. So I get some better pictures. So a PLA is of course divided. You have an AND matrix on the inputs, and you have an OR matrix for the outputs. And then you have product terms connecting the two. So on this image, you have on the AND matrix, you have really hard to find information about how these were manufactured and what the different things do, because most of the modern stuff that you can find on the internet is CMOS, which caught on for some reason, and this stuff is all NMOS, so they don't work the same way. NMOS, in this case, is RTL. And if you do FPGAs, you instantly think register transfer logic, but in this case, it's resistor transistor. So eventually, I ended up buying a book, this book, which might be familiar to some people. This is Large-Scale Introduction to VLSI System by Conway and Mead. And this is a very nice university textbook from the late 70s. I think this is the second printing from 1980, which describes how NMOS was designed and manufactured. It has all the bits on how to lay out NMOS logic. I didn't need much of that. I just wanted to understand how the chips were made. I'm still not going to learn how all the mathematics that go into making a working NMOS chip. I just need to understand enough so that I can pick them apart. So that's how I learned all of these glass layers inside. And of course, how do you get rid of glass? There's pretty much only one chemical that will do it, and it's not a nice one. It is hydrofluoric acid, yes. Or as many chemists calls it, the piss of Satan. There is a nice video on that as well, Decapping Ship, the simple and easy way, where they talk about a lot of this, including all of the chemicals and how to do it, etc., etc. Because a lot of people also want to decap ships and have them still work afterwards. I never had that constraint, so I didn't really bother looking into all that much. So what I did was, of course, I can't just go off and buy hydrofluoric acid. I live in Europe. They won't sell it to me. So, industrial cleaners, yes. Porcelain etchers used by dentists. I tried to buy some, they wouldn't sell it to me. That's 9% hydrofluoric. Eventually, I realized that a lot of hobby people etch glass. How do they etch glass? It has to be hydrofluoric acid. So I realized that Armor Etch glass stainer is 3% hydrofluoric acid, which worked perfect for me because I don't really want a higher concentration. 3% allows me to have a slow and controlled process, so I can remove certain layers if I want to. If I remove all the glass, you end up with what I have on the right picture, everything removed. What you have left there is basically the diffused substrate of the silicon itself. All the metal, all the polysilicon, all the glass, everything is gone. But that was pretty much what I needed for this. I've later learned how to control the process so I can just take off the passivation layer, because it also works as a lens when you take pictures. It's a glass layer, so you get diffusion and light diffraction and yeah, all of that nasty that you don't really want when you take pictures. So by doing this, if you look at the right-hand picture, you can see that certain things look different. And that's when I realized that the PLA chip in the 128 was basically programmed in the diffusion layer. So they put different things in. If you put these things in the diffusion layer, you get a transistor, otherwise you do not.
Yeah, we call them diffusion slugs.
Yeah.
We programmed it with preonic contacts and diffusion slugs.
Yeah. And it becomes even more obvious when you look at the other matrix, the OR matrix, where it is blindingly obvious how these things were programmed. So this one was really easy to decode. So once I had the AND matrix and the OR matrix, of course, you then sit down and have fun for a while to figure all of this out by just looking at the images. Yeah. Yeah. I put this into a spreadsheet just to keep track of things, but I've made a few mistakes along the path. You can find all of this on my GitHub, including the captured images in Krita, which I used to do all of this work. and also the spreadsheet. So if anybody else feels up to validate it, feel free. So now I had the and the or matrix and all the product terms and everything else figured out. Of course, now comes the trick. If we go back to the original image, I have this mystery box at the bottom. I have the AND matrix, I have the OR matrix. What's all that stuff at the bottom there? It's connected to all the outputs. So if I want to understand this chip, those things do, right? It's a repeated block of logic. Each block looks a bit like this. So the first image on the left is the full shot with all the layers intact. Now I have a depletion mode transistor. So, and that's usually connected to VCC on these things. It's a small pull-up resistor made out of a MOSFET. It's a very poor pull-up, but it does enough to do the job. Whereas these thin red lines are actual resistors, transistors, so MOSFETs. And I stared at this for quite some time, and then I just sat down with pen and paper and started breaking it out a bit more. And then I loaded it into KiCad and did this. So now you have a logic diagram, and you can actually look at things a bit more. And the things with the fat red line, the fat line, that's a depletion mode transistor. And you can see pretty much all of them have the gate connected to the source. I hope I got the direction right there. I'm still a bit confused about source and drain, because when you go down to the silicon, they're all the same. Yeah, yeah, exactly. So that's actually working like a pull-up resistor. Its NMOS is always going to be a pull-up resistor. In PMOS, it will always be a pull-down resistor. And the other ones are pretty much just normal gates. So if you look down in the corner, where's my mouse pointer? There you go. This one is fairly telling, for example. That's an inverter. So you have a pull-up on the output, and the input goes to the gate, which pulls it down. It's an inverter. So by looking at all of this, and with some help from my trusted book, I could figure out what all of this did and break it down into something that's a bit more recognizable. Now you have the actual logic gates that went into building that thing. And looking at the logic gate configuration, it's a D-latch. So at that point, I basically figured out that, well, certain things are latched on the outputs. In the DRAM write enable has a latch, and the other one is for the, I can't remember straight out of my head, but it's one of the bus arbitration lines. AAC, yeah, AAC. Also has a latch on it, on the output. So there has been some attempts to reverse engineer the PLA before, like they did with the C64, because the C64 PLA is fully combinatorial. If you present this set of inputs, you will get this set of outputs. And they have struggled to do the same on the 128, not only because it's a much larger PLA, but also because they got confusing results. You did a run, you tried it again, and you get a slightly different result. And that's because of these latches. So it's really hard to reverse engineer a latched design from fiddling with the inputs. So after I figured this out, and I had the matrices decoded, you can write Verilog. Great, now we just have to learn Verilog. I picked Verilog over VHDL, which is more popular in Europe. Yeah. Simply because the open source tool chains, there are some now for FPGAs, Yosis, etc., are really good at Verilog and not very good at VHDL. So I just picked Verilog because, hey, I like open source, right? So you can find all of this code at that URL. That's my GitHub. And some debugging later, I actually had a 128 running using this PLA chip. I still had some issues that have since been resolved, but yes, there are machines now running. I think Evie from Backbit is actually selling a PLA replacement for the 128, which is based on this reverse engineering effort. So it works. I have some chips I use myself to test around with. This is a bit exaggerated. What I was doing here is I connected all the inputs and all the outputs because I wanted to compare on both chips. So at this point, I'm actually running the original PLA and my PLA in parallel. All the inputs are connected to both separate because I wanted to determine the difference in propagation delays between the two chips. I have since learned that the 128 is surprisingly tolerant to a PLA being a lot faster than the original one. So the original one has a propagation delay of about 35.
They require minimum delays
Yeah.
in the C64, especially for the CAS timing, especially for CAS.
Correct.
And we hated minimum delays.
Yeah. Well, you did a good job because the original chip has a 35 nanosecond propagation delay, input to output. And I think you had a budget of 40, if I remember correctly. Yeah. And the XC95XL that I'm using has about 6 nanoseconds, and the system works just fine, which is really impressive. So since then, I've started working on the MMU chip. I've taken one of those apart and had a quick look around as well. That one is a lot more complicated. I needed a better microscope, so I bought a microscope. Once again, ignore my spelling, please. I built a whole motorization stack. This one is fully motorized. I have X, Y, I have tip tilt, I have Z-axis, because I want to start playing with focus stacking, and I have a manual rotation on it. So that one is a lot more competent. I'm not fully finished building it up yet. But I've also already started getting involved in reverse engineering some other machines, the Mac SE's BBU chip, for example. I have imaged the original BBU, and we also managed to find a Brainstorm Technologies BBU, which is the overclock device for those systems. So we're working on reversing that one as well now. It's pretty interesting. Anybody interested in this type of stuff, just come to my desk and chat away. Yeah. My future plans on this topic is I'm going to try and finish doing the MMU. I don't really need to do a silicon reversing for the MMU. The documentation is really good, so it's good enough for me to re-implement the MMU. Then I'm going to go to the other chip that's unique for the 128. And there, I'm probably not going to reverse engineer the chip per se. I'm going to re-implement it in a fashion that I find a lot more usable. To start with, drive it off the system clock. And a few other things like that, mostly because there's not a lot of people using the VDC in a custom manner. They drive it through the kernel, and at that point, I mean, who cares, really? And a few other things like that, but I really want to try and make it a good representation of what I think that chip should be. Much better than the one that's in there, at least. Maybe have the IRQ line hooked up. And the ultimate goal for me is to be able to build a brand new 128 from completely new parts. But I also don't want to just shove it into a single FPGA, because for me, that's the same as just running it in an emulator, really. As I usually say, I like having a data bus I can just put my finger on. Yeah. So, yeah, that's pretty much it for me. So, if you have any questions right now, I'll take them. Otherwise, I'll be at my desk for the entire weekend and just come over and chat. I will probably try and have a actual working exhibit. I'm actually going to be sat there working on the MMU code and some of the PLA stuff. So, yeah.
Bill, how do you feel watching somebody recreate your work?
I'm way past asking why, because I fully understand what he's doing, right? No, it's amazing, and I had forgotten about those D flip-flops, though I had remembered that we had made a flip-flop through the PLA as a transparent one. But then you said, there was something odd about the PLA, and this whole thing happened in my head where I'm like, oh, we added flip-flops.
Yeah.
So.
No, it's been interesting. I've been chatting with Bill along the process for quite some time, and I think I'm dragging up a lot of horrors from his repressed memories at times.
And could one of you give me some more details, the differences between the 64 PLA and the 128 PLA?
Go ahead.
Oh yeah, no, sure. The C64 PLA was basically a pirate copy of the Signetics S100. I think that's 82S100. Yeah, correct. So the first machines actually used the original 82S100, I think. Later on, that was not cost effective, so what they did was they just re-implemented the exact same thing. They probably took it under a microscope and looked at it.
We had the Polaroid picture stuck to a
Yeah, there you go.
board
Yeah.
up in the R&D lab.
And they just recreated the exact same chip on their own and just made it non-programmable. It's just programmed in a mask somewhere. And as far as I understood, the high failure rate on those chips is due to a process failure. I think there was too much boron in some layer, passivation layer probably. Yeah, which caused it to basically just, you get oxygen leaking into it and just destroying the chip over time. Because what a lot of people understand that heat will kill a machine, right? Warmer is not nice, but most people tend to forget that when it comes to actual chips, the temperature starts at 0 degrees Kelvin, not 0 degrees centigrade.
Room temperature is still temperature.
Room temperature is still about, what, 300 and something Kelvin, right? It's pretty warm. And when you look at it from that perspective, having another 20 or 40 degrees centigrade is not going to make that much of a difference. So a chip sitting on a shelf will still degrade. Yeah. And oxygen is really bad stuff.
I just learned from talking with Albert Charpentier that it was Bob Yanis who originally used the 82S100 on the C64.
All right.
So that's the genesis of that, which I
Yep.
never knew until recently.
Oh, that's cool indeed.
He's the one that went and pulled it and said, yeah, this is what we're going to use.
Yeah.
So, go ahead.
Was that the theft of the Signetics design before maskwork was copyrightable in the United States? Is that how it worked and there wasn't a patent applicable? Or what was the deal with copying a Signetics?
It was borrowing, not theft.
I see. Well, that got repaid, I guess, when Nintendo stole the 6502 and just deleted 4 transistors in order to make the decimal mode not work.
No, I don't remember anybody ever going, oh, we're going to get in trouble for doing this.
Yeah.
It's like, keep going.
Yeah. So, any other questions? Yeah, there you go.
Out of curiosity, what is the deal on the 128 with all the capacitors on the bottom right side? What do they do?
The bottom right side next to the keyboard connector?
Yeah.
Yeah, those are actually feed-through capacitors. So it's in essence ferrite beads or very low impedance inductors with a capacitor in the middle of them connected to ground. So what it works as is basically a low-grade, low-pass filter. They are there not because they are necessary to make the computer work. They are there to make FCC happy. Yeah. Yeah. So because when you, yeah.
When Japan, Tokyo, Japan showed us that,
Yeah.
we fell in love with it.
Yeah, correct. And if you look at the 128 board, it's pretty noisy. There's a lot of TTL stuff on there. They're working at megahertz speed, which is slow today, but you also have to remember they're doing 5-volt swings, right? They move a lot of current up and down. So when you connect a cable to something external, you have now connected an antenna to a large uncontrolled radio appliance. So those filters will basically try and remove a lot of that noise from entering into external connections.
I have a question. Did you ever track down that VCF line on the PLA?
It is there in the PLA, yes. I haven't.
Figure out what it did, but it's still used, I guess.
I haven't looked into the exact details. It does change a few of which product terms are used for the AES.
Yeah,
It's related to the AES somewhat. Yeah.
And the D-flops made it so we didn't need
Yeah.
VCF.
Correct. It's something like that. I'll look into it later. I still need to validate and clean up the Verilog code to make it not, because I wrote it so I have all the product terms and then I combine the product terms. So it's downright ugly Verilog, but it works.
So I think why the D-flops were needed on the gate, I think we performed a gated read-write function.
Yeah.
And what we found was the VIC chip was going, okay, on to the next cycle. Wait a minute, where are you going with the read-write line? I was
Yeah.
writing here.
Yeah.
Okay? And you left, and I was doing the right, or
Yeah.
let it Twitter, even a
Yeah,
1
great.
nanosecond
The,
will kill a read-write. So.
the one thing I have run into with using modern logic in replacing the original PLA is I get really short 1-2 nanosecond spikes on the outputs because the input signals come slightly different times. The original PLA is so slow that it never reacts, but a modern CPLD, it just goes, oh, well, it's combinatorial, we need that spike there.
Yeah, it was a big capacitor,
Yeah,
grid,
yeah.
basically, yeah.
So I haven't seen a bad effect from that yet, but I'm still working on trying to filter those out because I don't like the RF and noise from it. Yeah. Yep.
So you had an example where between chips, a delay of an extra gate was important for stabilizing, maybe glitching a signal. But was trace length or trace capacitance important on this board, or not at the speed it was being used here?
Well, let's see what you say.
Oh, there is impedance issues, all right.
Well, we did no impedance control because we just, it was a
Yeah.
two-layer board.
Yeah.
So to answer your question, things were so slow back then that we generally didn't have a problem with the speed of propagation. It would actually reflect and echo and settle
Yeah.
down, and we waited for it to settle down. So we didn't have to drive it where it was valid within a nanosecond or whatever 6 inches would be to travel.
Except for the bod wire.
Yeah. Which was crosstalk.
It's crosstalk, yeah.
Yeah,
And
yeah.
yeah. So no, it's a very big board, so you get a lot of noise on there, but these chips are very tolerant in general. Yeah.
So you know that wire that's on the 128 on the top? We cut that. We actually did a video show with it. And I was expecting it to be something like it was ringing, and it turned out to just be crosstalk in there. But I thought it was a propagation back and forth, and I thought it rang like a bell. And it was just, it got too close to another signal at a bad point in time.
Yeah.
So it was, yeah.
Yeah, I've not had to implement that on any of the Neo boards. I've always had CPM working without it, and
I wish I had done it in the video output. Now that you've said, hey, it can be improved, I'm like,
yeah.
why didn't we at least try to do impedance control? And I know the answer is there was no time.
Yeah, yeah, exactly. So, yep. Well, I think we're out of time, so thank you all.
How much did you spend on microscopes
You don't want to know. It's. Oof. Yeah, that's also quite a bit. Yeah. Yeah. No, it's. It's from 1985. I picked it up used in Berlin. He refused to ship it, so I got to drive to Berlin. That's 700 kilometers to pick it up, and I understand why, because it's mounted on a Nikon base. So it's a Nikon measure scope base, which is cast iron. The thing weighs 45 kilos, and on top of that is optics, precision optics. I'm not going to put that in the hands of DHL, especially not if it weighs 45 kilos, because the DHL block is going to be real drunk about the weight.
I can bleep it out. You know what? I did check with the YouTube thing. When I just released the video, I can say, when I monetize it, I can say mild profanity. So I can at least say mild profanity in there. So that'll be good. It'll be fine. Yeah, yeah. When you sort of when you're relaxed and just talking with friends or something like that. Yeah, I know the same thing. Because like when I'm like substitute teacher in a school, I can't be cursing, but when I'm with my friends, that's a different story. Yeah.
But when you said, okay, are you coming back? This year there will be like more people and everything. With your commissioners, right? So you're not gonna have like teenagers in the crowd today, are you?
No. So there was some teenagers earlier in the day. They came on a trip and they had to leave at 2:00. So yeah, they were here for a couple hours. It was called Girls Who Code. There are groups in the U.S. And they came. They seemed to enjoy it, but they left already. What's that? Hers? All right, so you have to guide me how to do that with the audio settings. Audio? You want me to tell her, or you wanted me to do it on Zoom? All right, so the input mic, that's what it is? Is there anything you think I can adjust? Stephanie, can you turn your volume up? I mean your mic, your microphone, yes. You're the first. It's not as loud as me, I think he's what he's saying. Is that better? All right, so hold on. He has to go back to the OBS station. This is you're our first virtual speaker so far, so it's sort of like ironing out the kinks here. Yeah, well,
the whole pandemic brought the whole virtual thing front and center.
Yeah. Well, my point is that they haven't tested out the system they have now today, so they're ironing out the kinks. Is it better over there? it into the headphone jacks. Maybe I have to change. Same as system or headphones. That one. All right, the speaker to headphones. All right, it's changed the speaker to headphones. Microphone should leave it as same as system. That's my microphone. So try. Let's. I want to see if it works now.
1, 2, 3. 1, 2, 3.
Oh, now we hear you. All right. Is my settings. All right.
Okay. 1, 2, 3. I used to be da da da. No. Are we ready?
Are we ready to go?
So are we still 3?
We are at 4 now.
Wow. Okay, that's going to be a great presentation.
Yeah. Did the audio just go down a little bit? Okay, he's adjusting it. Let me know when we're good to go.
All right. Meanwhile, do you mind asking the crowd this very I don't think I'm going to talk much about the philosophy behind the new retro computer thing. I would suggest that you come back tomorrow and I'll talk more about it. What I got myself in that kind of weird place where I'm designing something that is not compatible with anything, and it's not meant to be compatible with anything, but it's really a tool to get people back to a place where, when we, back in the days when we did retro computers, we were after these, back in the 80s, we had all these new retro computers, and I think one of the thrill of back in the day, the nostalgia that we have today is one of those aspects was to actually discover the machine. So in a nutshell, that's basically what those new, when I call a new retro, like the Amiga 65 or the ever maybe will come one day, the X16, is really meant to get people back into that state of discovering something new that we don't know. So today, what I'm going to talk about is really the graphic engine that I've been developing over the last 4 years, because it's actually, I started 4 years ago. About the anniversary is the 18th of April 2018, so we're like four years in. And it all started with David Murray and his request for new retro computers. And again, I'm not going to talk about that stuff because, I've talked about it many times before. So today I want to really focus, because it's a technical presentation, on the inner workings of VK2. So the first generation, the first computer I designed, it was VK. It was a 16-bit bus, and I migrated to a 32-bit bus to get more bandwidth. And since then, I've been developing it more. And now I moved from not necessarily completely, but I've been moving away from the 8-bit, old 8-bit CPUs, because it's like there's a lot of people there already. So I decided to go and move towards more the 32-bit. So eventually there will be a VK3 version of this, which will be 2 different buffers and more capacity, more capabilities. But anyway, I'm digressing a little bit, but basically the introduction of what I'm going to present today is really about the inner workings. And I cannot go very deeply into it because it becomes very complex very quickly. But I'll try to explain basically the different blocks within the chip and what it does. And it's an FPGA development and everything. It's a custom thing that I designed, and it's private. It's not open source. The reason, and make sure that everybody works on the same chip. It's basically, the way I see it is that the way I presented it in the past was really, the FPGA for me is meant to be like an ASIC, something that was, set in stone, nobody could change it. And so making it open source where everybody could change it would make it like, it doesn't make any sense to me, or it didn't make any sense to me back in the day. It still doesn't make much sense, although if I was going to quit the world of new retro computers, I would probably release it. But it's really about having consistencies for people to develop on something that is always the same thing. Anyway, so the agenda as well, I guess I have a little bit more room. I hope so. I can go through my agenda today without being pushed out. I'll do a little bit of introduction. I'll go a little bit deeper on my background that I usually skip over really quickly. Assumption of the level of knowledge. Last year, we did something a little bit deeper in Verilog developing, although we didn't do a lot because, 40 minutes is not a lot of time, but it was definitely more hands-on. This year, not as much. And I'll go through the different portion, like I said, about the chip, what it does. I wanted to show you as well, I think I showed it a little bit earlier. This is like a board. This is the A2560U. It's a 68,000 base board. And so you basically have the FPGA, and I'm going to talk soon about the video DAC, which is here, and the memory buffer, that's VRAM that is here. So physically, that's something that we're using and exist. And this is the A2560 Phoenix U, which is the user version, the small version. So there's way more. So I suggest that you go on the website. And then I don't want to waste too much time on this, so I'll move on right away. So I come, I'm a Gen X. I was born in '69. My father brought this 64 in 1982, but it was the first year it was released. We didn't do much with it. That was my introduction to computers in general. Took a couple of years to get into it, and I started having fun with it. I started doing some hacking, game hacking and stuff like this. So I started fiddling with hardware. I also at 13 started doing, using my brother's kit, Radio Shack kit for those who remembers that, plugging. And I got very interested into this, and I started doing a lot of, hacking on my own. I was always been a very on my own person, doing my own thing. When people were going out and having a drink, I was doing electronics. So that was a very big passion from very early on. And I started my career as a technician. I never been to university, so I don't have a bachelor degree, but I'm a little bit like Elon Musk. I learned, and all these big, guys that just were school dropouts, learn on my own, learn on the heap. And that's how basically I went through my career, just learn a lot of stuff on my own, and, struggle, get myself in trouble, and usually go for the harder path. But there's always a reward by doing this. You learn something and you get better. So I started being a technician, but within maybe half a year, I ended up being in the engineering department, and maybe a few months later, I was responsible for my own project development. So I was definitely early on definitely had a lot of skills into product development in general. I tried to develop, started companies, like the first one was 96, doing some acceleration for the geometry processing. And you have to remember, this is the time where, the first rendering chips were coming out, the rendition chip, the NVIDIA chips, which was shipped at the time. There was AMD, not AMD, but ATI. All these guys were there. They were all starting and then fighting with each other. The same thing, relationship with the different retro computers, or back then the home computers. A lot of choices and a lot of possibilities. And then over time, it just got integrated and everybody bought each other. And then NVIDIA came on top and with ATI. So that one failed, but that was basically a DSP trying to drive a rasterizing chip, rasterizer chip. So to complete the whole, processing flow of the 3D engine. And then I moved on. That company went bankrupt. I bought the bankruptcy back, but it was already too late. I failed miserably the second time as well. And then I went in sales, and then I didn't work out. I loved helping people, but I sucked at the politics of it, and there was a lot of it. And then I moved on into working for many companies to develop products, and got more skills, got more experience, and finally in 2004, not finally, not like it was like at that point, I started a company again, but I definitely lasted longer, but I didn't produce as much as I wish I would. It was by the time, because I was and then I moved in LA, because I was really focusing on image processing. I always had this interest into graphics and pixels and stuff. For me, it's always been very exciting. I always say that there's so much potential in the pixel, way more than a packet of Ethernet, right? So the data transfer, because in the electronic industry, there's many different areas where engineers find their places. For me, it was always imagery, 3D graphics, and stuff like this. So, and processing of said pixels. So in 2004, I was focusing on trying to accelerate the image processing for for movie industry, like a black box that could make things process go faster when you do post-processing. But that was a time where, Intel processors were preferred because they were easy. Somebody came with a solution like this and passed, and, everybody they got stuck with a black box that could not be expanded. So the deal was, I came later, and then they didn't want to get involved, and software people were flaky, and, a lot of whoring around and pimps and whores to get your stuff accepted and everything. And since I'm not much of a political type person, I was like, okay, let's forget about this. And then 2008 happened. I moved in LA in 2008. So I was going to design this super parallel solution with mini processor. It was insane. But the parts I was going to use, the name of the company was Embrace. They went belly up like 2 months after I came in because of the crash in 2008, which I was not aware of at all. So then it was kind of hard, and then I got some money back from the R&D from Canada and everything, and then I started making and designing, global shutter cameras, digital cameras, which was very new at the time. And but again, I'm not political, but I'm not a salesperson as much as I would like. I'm kind of too honest, so it's difficult to get me out of my own way. So eventually, I kind of, I got the camera to a state, it was working and everything, and then I sold the design to somebody else. I worked for that person, and then in 2013, he ran out of money as well, and then I came back in 2013 to start working for people, other people again. And eventually, in 2018, after working for different companies, on the side, and David's, stuff was, it would be great if somebody would design something like the retro computer with my, wish list. And eventually I got into it. I was amongst the very few who actually got in there. But I was in the mood for retro, like a lot of people, and I did something. Although I did it with my own money and I did it with my own angle, my own vision of what he wanted. And I started with the 816, and I created the first C256 Phoenix, and then I moved on from there, and I started developing. So ultimately, like I wrote, the moral of the story is that there's really I've learned a ton with all those failures, because it's mostly when I was in LA that I've learned to do FPGA mechanical design, because I was on my own. So I got to hone those skills and learn, and I was always very good about the visionary aspect of developing a product. I had like a clear vision of what I wanted, but now that I was doing everything, then it just gave me a better edge. The other side of that is that ultimately, when you're knowing how to do everything, you don't know how to do everything as deep as if somebody is doing a sole work, right? It's not as good as a pro that does only FPGA, for example. I'm just really good enough to get it, to pull it out and make it work. But otherwise, most people would do what I'm doing way better if we segmented everything I'm doing in product design. So yeah, so basically, don't be scared of failing, just do it, and you learn a lot, and it's great. So today I basically got involved, and after that, the whole story after that is really the fact that I came to work in Vancouver for a digital camera company, and just working and doing this on the side. And when I left the company, or I was let go, in 2020, I was kind of resisting to go further with this, and I was like, okay, but I didn't feel like going back to corporate. The last job was really hard on me. I invested a lot of my energy and love in this, and it didn't turn out great. So after a few months, failed attempt to go work in US in April 2000, last year actually, I came back and said, okay, let's do it full time, and I've been doing it full time since then. And again, if you want to come back tomorrow or see the video tomorrow, I'll talk about the Gen X, which is really the ultimate new retro computers. And yeah, it's so that's what I'm doing now, and it's ultimately the thing I didn't want to do, because after the last time I started the company, I said, when I don't want to do that anymore. And then the universe has a way to bring it back on your lap when you don't want it anymore. Which basically means when you want something too much, it's like, no, you don't do it. You just let it go, and then it comes back, and then it's more organic. It just happens. You just have to go through with the flow. Anyway, moving on. At this point, there's no really prerequisite. If you have any knowledge of 3D graphics or a little bit how a video card works, it's great. I think it's meaningful. That's why I didn't want to go too deep, because there's many sections. Explain as much as I can. It's really how you see it in your head, how the processing is being done. But otherwise, it's not like last year. Like I said, it's like you don't need like a Verilog background or anything. So that is probably good enough. So no special prerequisite this year. Before we go any further, I want to make sure that everybody's on the same page. Something else I said last year was like ways to see things. There's different ways to do things. Since I didn't go to school, I was not like squared and told in a way to think a certain way, because I believe people going to universities usually learn more about how to process information more than what they need to learn. In terms of technical learning, it's more about how to go about learning stuff or to process information. So since I didn't go there, so I'm a little bit all over the place. So this is the representation of how a display is working. So basically, the information you send out to the LCD screen or CRTs is usually, you'll have the VSync signals, you'll have the HSync signal, you'll have some blinking signal to say when on and off the ray gone. If we go back to we go back in time. So this is kind of a common knowledge. I mean, people kind of know that. Technical people know that. So I don't want to spend too much time on that, but just to the way I'm showing it, because if you look on Google, if you look for information about how the timing and display information is being displayed on screen, you're going to see very often that the blanking is on the right side and the V blanking is at the bottom instead of being on top. I don't know why, but I've always pictured the V blanking and the H blanking on the top left as opposed to be on the bottom right. But in the end, it doesn't really matter because the display doesn't care. It's just going to put your data, as long as the VSync and HSync and blinkings are at the right time, relatively to everything else, it's going to work. So I wanted to present it the way I see it, so it's easier to go along. I've put a small link at the bottom here because this is where you can find really resourceful timing information. It's kind of rare and difficult to find sometimes to know exactly at what clock cycles things happen. And this is really nice. The person who came up with this was really right on. So this is how I see so there's definitely a time where there's nothing happen on display, and it's going to be important later for how you manage the timing, the time to fetch the data off and on the VRAM and so on and so forth. And yeah, so I don't think there's anything else to say, but because we'll ultimately come back to it. So before I go within the VQ2 core, there's two parts that are usually important, of course, to display an image. Most people nowadays, if they want to do a VGA, they usually use a R2R DAC with resistors, with a VGA, an analog way of doing things. The VGA, I find the VGA to be it's in terms of color and everything, it's kind of nice when you have a CRT. But when you leave the CRT world and you go into the LCD, I think an HDMI or a DVI is definitely better. Send your data digitally is definitely better. So I try to stick with this. So you need a video DAC, but in reality, it's more a video DAC. In our case, the parts I use is doing both. So there's DACs to have a VGA output, but it's very finicky. It's very difficult to have a very clear image without having overshadow and stuff. It's very, very finicky. So most people don't use it, which is great. So the parts we're using as a TMDS encoder that just transfer the digital data into the same thing that the HDMI use, and the LCD is way more happy with this. So the video DAC we use, because the data I'm outputting from VQ2 is a 24-bit RGB color palette, if you will. It's always full color. But it's multiplexed, so to save some pins. So you have the HSync signals that we referred to it last time, the VSync, the D-able, which is the blanking, and in that specific case, the data has been multiplexed, and in that design, I'm using a DDR way of doing things. So I use, for example, if we're doing a 640 by 480 VGA standard clock, that means that the clock getting into the video DAC is 25.125. But on the rising edge, I'm going to send the first half of the 24 bits, which is 12 bits, and on the falling edge, I will send the other part. So you see a little bit of graphics here to show that. And the next table next to it is really about what data is being. So basically, I think it's getting the blue information, the green, half of the green on the rising edge, and the other side of the green and the red on the falling edge. Then the DAC just takes care of everything else, and you get your video on screen. So this is one part that we need. This is ultimately where all the pixels will come out. On the other end, you have the SRAM interface. I call VMEM or VRAM or whatever. I mean, back in the day, VRAM was more dynamic, a specific dynamic RAM, but today is more like a generic term. In our case, it's generic term. I use SRAM, and the limitation of SRAM is really the fastest SRAM you can get. I mean, that is still reasonably priced, and if it's not synchronous, it's 100 megahertz. And the deal for me has been to widen the bus to get more bandwidth out of it. The reason I'm using SRAM, even if it's back in the day, SRAM was costing a fortune and people were using DRAM, which made more sense. And even today, DRAM is less expensive than SRAM. But the reason I kept using SRAM, and it's not because I didn't try to use DRAM, is that ultimately the SRAM is a random access. I can do pretty much, I give an address, I give a read or write, and I can actually have my stuff within 10 nanoseconds, which is still fairly fast. And the difference between VKey and VKey2 was because I expanded the bus to 16 to 32 bits, so I could fetch more. So that's the way I went about getting more data out of the memory, to get higher resolution, to get more feature like tiles and bitmap, and so I could have more data being moved around. The reason the SD-RAM is a burst type memory, right? So it's really good at bursting things out. If I had only used it for doing bitmap, then SD-RAM is great because you've just burst a whole line in one shot, and it's really, really fast, and you can go faster than 100 megahertz. But when it came to tiles, for example, or sprites, it's just a small chunk of memory that you go and fetch. So when you're dealing with SRAM, you have like 4, 5, 6, 7, 8 clock cycles before you start doing anything to set up the address, to the RAS, the CAS, the CAS latencies. All these things that you're probably very much aware of are part of the whole transfer. So if you have to transfer 32 pixels, which are basically, in our case, a byte, because everything in that system is 1 byte per pixels with lookup tables. So you would have to transfer 32 bytes, which is 8 32-bit wide, word. So that means that you're gonna use 8 word to set up the whole DRAM, and then you're gonna burst for 8. So that means that you divided your bandwidth by 2. So even if you're running 166 megahertz, that means you're still going at 66 megapixels per second, which is just stupid. So there's no way to go around that. So that's why I kind of stuck with the SRAM and decided, okay, if I want to go faster, I just need to put more or a wider. The memory can be less dense, but having a wider bus. And VKey3, that's what I did. I ultimately have 2 of these configuration. The interface is very simple. There's no DRAM controller. There's no refresh controller. That's also part of the deal. And I just made the calculation last year and said, okay, I can put a little bit cheaper DRAM, but then the overhead to get it to work, the time, the whole thing is not worth it. It's just going to cost me a fortune in time and implementation and make it work properly. So I stuck with the SRAM. So ultimately, there's just a 32-bit bus address. There's a 20-bit bus address data, and the control signals, the byte enables, the output enable, which is basically a read strobe and a write strobe. And if I play my card right, I can pull 400 megabytes or 400 megapixels per second in throughput with that controller. So, all right. So this is what it's outside. I'm not putting it. I didn't talk, or didn't make a slide about what's been connected to it, because so far VKey2 has been implemented with a 68000, a 68040, 65816. So you can pretty much put anything in the front end because, well, from what you're going to see here, you're going to understand why. Because the front end of VKey2 is basically a bunch of register level that you can map, and you can kind of remold it to fit the different type of interface. Everything else after that is pretty much the same. So we're going to spend a little bit more time here because I think it's really important to understand the different blocks and what they do. So within Wiki2, there is at the top level, there's the video text engine block, which is really its own thing. So that guy used internal FPGA memory to put all the character information. And there's another block of memory that has the font information. And everything is done internally. So there's no access to the VRAM whatsoever to deal with text mode in black and white, like one color. Ultimately, Wiki3, I'll expand that. I'll try to use some external memory to put some colors and do some stuff, but we're not there yet. So this is, and the output of this is going into the video output mixers that I will talk about a little bit later. But one of the features of the Wiki2 chip is allowing you to do overlay, text overlay. And that's the reason why we can do this, because it's so much different, it's so separated from everything else that it's just everything is synced up. So you just feed the text on top of everything else. And if I was using the VMAM to do video text, then it would not be possible because it would be just another layer. Then there's the mouse controller, which is another block that is separated from everything else because it's simply a small block. It's a sprite, literally, but it's not part of the sprite system. It's overlaid on everything else, which is, it's pretty standard in video chips. And then you start having the different register level, the bitmap register level, which is basically telling in the memory where the bitmap starts, you don't need to do the size anymore. There's different resolution. I'll talk about that later. The tile map system is 4 layers of tile maps, and you have access to different, you have windows of, you define a map within the VMem, and you define your blocks of graphics separately. You can have 8 of them. And then you have register to move stuff around, to move a window within the map. Not going to go deeper with this today, but it's how it works, and I have 4 layers of them. Then I have the master control that just decide what is the resolution and everything. Then the sprite, there's 64 sprites by default in the system, but you can mux them to a lot more. Right now they're 32-bit by 32 pixels by 32 pixels. The tiles is 16 by 16s. And ultimately, the sprites are very simple. You enable the sprite, you put your graphics somewhere in VMem. There's a pointer that says this is where the graphics is. And you just set the priority on what layer it is, and it's going to be displayed. And then part of Wiki2 as well, there's the VDMA controller, which is the video DMA, which is, you could say it's a blitter, but it's not quite the blitter yet because there's a lot of function the blitter has that the VDMA doesn't do yet. The Wiki3 will have way more blitter functions than what Wiki2 does, although I might upgrade Wiki2 later. I made 2 different DMA system in all the new retro computers I designed because I wanted to be able to do VDMA on one side because there's 2 memories, right? There's the system memory, there's the video memory. And so the VDMA can move block around in the video memory without interrupting the processors. And then if at some point you want to transfer your graphic data from system memory or from SD card or whatever, you use the SDMA, you set up the SDMA, you set up the VDMA, and then you get them started. And then they're just going to transfer data in between each other and then transfer it, in the VMem. The only problem with this is that the 816 so far, you have to stop the processor. You cannot share the bus. You cannot do like a shadow transfer while the CPU. It's not like you can do it like a 68,000 with the Amiga because Amiga had so much time in between every access that you could do a lot of things. And that's what the Amiga was so powerful because there's so many clock cycles that are wasted waiting and processing inside the 68,000 that there was the VDMA or the DMA controller was taking advantage of that. The 816, we cannot do that because it fetches a clock. It uses both phases of the clock and fetches something every clock cycle. So there's no room to do anything. The 68 SEC is kind of like that a little bit because the number of clocks needed to process an instruction went from 7 o'clock to 3 o'clock. So there's no room at all either. So there's a trade-off about doing DMA and VDMA at the same time. So that's why I always say transfer your stuff in VDMA, because the buffer of VDMA is pretty big, and just move your stuff around instead of trying to just push your stuff in and then push more and push more and push more. The register level is really where you keep all the information about where things are, what size, how you move stuff around, stuff like this. And then within VK2, there's the block I call VGE, which is the video graphic engine. And within master state, the master state machine, which is basically a state machines that just going to check what line we are. If the bitmap is enabled, is the bitmap block is enabled? Yes, okay, go do your thing, and go from bitmap, tile map, sprite maps, one after the other to go fetch the data. And that data, each bitmap or each state machines of every of these different types of graphics is, because every bitmap is doing a certain thing. The tile map is doing things in a different way to go fetch the data because it's a different type of graphics element. The sprites are the same. All those three things are really different from each other. And then what it does, it starts the state machine of every block one after the other, and then it goes to send some information of the register level. For example, it basically takes the information from the RID, push it into the memory access manager and said, okay, you need to go fetch one line of bitmap right now, go and get it. And when you get it, go put it in one of the line buffer, and we'll come back to that. And it goes from bitmap, tile map, sprites, and VDMA. And ultimately, all this information that was fetched from the memory is put in all of those line buffers, because the way VK2 works is really in layers. And after, when it's been computed, it's been all the data has been grabbed, because everything has been grabbed one line before it's being displayed. So during the previous line, so for example, if you start at line 1, so you're about to start a new frame, so you're at line 1, so the line prior to this, that's, and say, okay, we're at line -1, and go fetch the information from line 1 that is upcoming, and put all this data in line buffers, which basically is a line memory. So you write on one side and you read on the other. But you go through to get that out, and then it goes to the lookup tables, because it's at that point it's just an index. You say, okay, I want pixel is 20, it means that I want the color number 20, and it goes to the lookup table, and then the lookup table spew out some RGB value, and then for that specific pixels on the line, the value you want. And so this is the basic of the layering logic, but then there's the priority level where I'm going to come back to it later. And then ultimately, all that information is synced up with all the vsync and all these things. And it's, again, there's another priority level where, okay, is it a top level? And then there's the overlay level. And then there's the graphic engine level, which includes all those different lines, which is sprite, bitmap, and tiles. So try to memorize important. So this is how the layering system works. So like I mentioned, there's the sprites have many layers because they can be intertwined between the different, the bitmap. There's a bitmap on the top, there's a bitmap on the bottom. In between, there's 4 layers of tiles, and in between all those layers, there's the sprites. You can put all the sprites in any of these layers. And you have 64 sprites, which means that you could put, sprites 1 to 7 on sprite layer 0. And you could put, sprite 20 to 32 on another layer. But you have to keep in mind that, depending on priorities, and if you want to concatenate or put those sprites together to make bigger sprites, then you have to make them one after the other so they don't overshadow themselves. You have to keep in mind also for the collision system, I'm not talking about the collision system, but there's a collision system, which is not great, but it's there. For example, you would put like your protagonist characters on your sprite layer 1 and sprite layer 0, and then you would put an antagonist on another layer for the collision system to work. But I don't want to go this. But like I was mentioning before, all that data that's been fetched from the memory is written in one of those lines, and one of those lines represent a priority level. So for example, if the sprite layer 0 would be in that line buffer 0, the bitmap would be in the next one, and so on and so forth. So what happens is that when we're ready to go and transfer that pixels offset or pixel pointer to the lookup table, there's a counter that goes through, you know, at the beginning of the line buffer, just go through every pixels and look, okay, which one of these, we read all those values at the same time and say, okay, which one, okay, is there a 0 on top? No. Okay, so this is the pixel we're going to show. The next pixels next to it is like, okay, is there a 0? Because 0 represents transparent. So 0, yes, okay, next one, there's 0, yes, okay, moving on, moving on, moving on. If you don't come across a pixel along the way, then you end up having the background set color, which is just an RGB value, and that's what you've been displayed. So if you come across a pixel before, then you're going to display that pixel before. So this is how the priority level works in that system. I could have put like a kind of it could have been done in different ways, because there's like a Z buffer I could have created or something that could have given each element a different variable, but then you expand on the buffer size and the information you need to. That's what 3D graphics were doing, right? To just give a value of Z, and you compare the value of Z with the other pixels, and you can, you know, remove pixels you don't need. But at the end of the day, one of the challenges was during the design was like, ultimately you need to read all the pixels anyway, because at some point you need to compare them all together. So the idea of line buffer was possibly the best way I could go about it. And considering I had the resources in the FPGA, then this is something I could do fairly easily. So this is how the layer works. So after that, this is the state machine in a very simplistic way. The way it works, bitmap in principle is very easy. This is the easiest way to implement. You want to do a graphic system in FPGA, bitmap is the easiest of all, because it's just, you go read the data in the memory and you put it in the buffer somewhere, and when time comes, you just read it out at pixel clock at the right time, and you get your data. It could be 24-bit, could be 8-bit. You could have a lookup table. Obviously, you need to take into account the time it takes to read the data off the lookup table, but without going too much details, it's very simple, it's straightforward. You set an address in VRAM, in our case, and you say, okay, it's buffer at beginning at 0. You say, go read this. So later I'll show you when it happens, but it's ultimately, the master state machine says, hey, the user wants you to go and have a bitmap image. So you're on, you have an enable signals, and then there's a trigger that says, okay, this is your queue, go fetch the data. So I'm going to fetch all that data at 400 megabytes per second, and I put it in the line buffer, and we're done. And that's the thing, we can enable or disable every of those blocks, but this is very simple. And then the state machine knows where on the image it is, so it can offset the place it needs to go. So if I'm on the 30th lines, it's just going to go fetch the right address at the right time and store in the line buffer. That's all it is. So in that case, the state machine is only the logic or the functioning logic behind it. What happens is really the MAM, which is the memory access manager, is being told, okay, this is the bitmap time. I'm going to give you an address in the memory. I'm going to give you how much data you have to go fetch and latch the data in and say, okay, this is where you need to go. Basically, it's a counter that has been set up and a comparator that's been set up, and you say, okay, go fetch the data. And everything after that and done, you go back to the state machine, master state machine, say, okay, we're done. And the state machine, what it does, it just moves on to the next block. So before we go into the next block, the different, in VK2, you have the borders that you can set up. You have the invisible portion of, it's a virtual place, if you will. It's like not in the memory, it's not in anywhere, it's actually in the blankings. But the starting address of the bitmap is 00, and you can have a border, but you can have, usually when you're using the graphic engine, the border is on top of everything. It's like it's a layer for itself. It's like the border is done in the, hold on, sorry. The layer has been created into the video output mixer. It's not created in the graphic engine. So it's really an overlay of a color, that's all. And the engine, the VK2 engine can do now, actually it's one is missing. You can do VGA, normal VGA, and I call it double pixel, which is you just make things bigger. So 320 by 240, 800 by 600, and then twice as, or the division of 2, I guess. There's a new one which is 640 by 400. That's 70 hertz to have the same as the C64 for the one that likes the big pixels. But all those are at 60 frames per second, and so very, very easy. Moving on. Next, we have the tile map. The tile map is really tricky because a tile map is like a font, a set, right? It's a text thing. You have in your memory, your main memory, there's an information. In our case, it's a 16-bit information for every tile. Within that information, there's enough set, or there's a tile number. We say, hey, this tile, from this tile set, we created all the graphics, which is a block of graphical data, like a font set, same thing. But I've put a 16-bit, it's in 16-bit because I wanted to have assigned the lookup table. I wanted to have, you can actually assign multiple graphic sets. So it's not only one set you can point to, you can have 8 of them. So you can have like way more tiles. You have 8 sets of tiles that you can use within one set of one map. And there's the collision system and so on and so forth. So in the state machine, what it needs to do at first is that since the graphic element is 16 by 16, you have to divide your screen by 16 by 16, right? So within, for example, for the first 16 lines of video being displayed, then you have one tile that has been displayed. So when you go fetch the data for the tile, for 16 line, you're going to go fetch the same data. And usually I'm going to go and fetch once. So at first I'm going to go in the tile map, and the tile map will tell me, the first line of the tile map will tell me what tile you want. So this is done first. And then what I do after, I'm going to access the memory a second time, and I'm going to go get the graphic in small chunks of 16 pixels, and all the different tiles, the tile blocks, graphic blocks, to go get the data I need to display, and that information will be put into the line buffer for each layers of tiles. So if you have 4 layers enable, I have to do that 4 times. And then when I'm done, I'm done. This is what I have to do. So in a way, it's a lot of back and forth and go fetch it. So after I'm done with the first 16 lines, then before I get into the 17th lines, I need to go get the new line of the characters or the tile map information, so I can know which graphics to display in the next 16 lines to follow. So definitely a trickier logic to do tiles. So how it's presents itself is like in the memory, you're going to set up a tile map. The map is where your tile information is, and the tile map can be really big, and which saves a lot of time to, instead of pushing data in and on each sides and everything, to make it, if you want to do scrollings and not RPGs but platformers and stuff like this. The way I saw it, the way I implemented it was really, you set up in your VMem the tile map, the sizes, and you put all your information in there. And then you set up, there's another configuration that you say, okay, the window of the screen will be at X and Y position in your tile map. And so you're moving, you just need to move your window. Your graphics don't have to move. You just have to move your windows into the tile map to get your stuff. The only thing it doesn't do is the wrap up when you go back, but you can cheat and put stuff on the side, on the right side for the left side to repeat, and then you move your window back to where it was before, right? So there's tricks you can do. One of the reasons I put so much memory at the time was that back in the day, memory was a big limitation for graphic engines and everything. So they put a lot of tricks in the hardware engine to do a lot of stuff like inverting, vertical inversion, horizontal inversion. I mean, the SNES, all these consoles had a lot of hardware tricks up their sleeve to really reduce down the amount of memory needed. So you would have wraparounds and stuff like that automatically inserted into the engine to do this. It becomes very complex to put that in place. it complexifies the design a lot. So the one way to mitigate that is to put more memory so you don't have to do it. So now memory is kind of cheaper than it used to be, although nowadays the memory has increased dramatically. But let's say that I can get that memory for cheap. It's still a very economical good way to do it, because I don't have to spend months on end, because I'm only one person in the end. These guys were like 20 Japanese engineers working full time for months on ends to design these graphic engines. So I don't have that luxury to spend 3 years to develop just a wraparound logic to make it cool and fancy. So memory, I have plenty of memory, so expand, use the memory, and usually it does the trick. So in a way, the tile system is pretty powerful in a way, because you have this capacity to have like 4 different layers, and you don't have to do much aside of just putting the graphics, moving things around. Still, the graphic engine does a lot of work. The resolutions are the same, obviously one resolution for all those features to be, displayed at the same time. Another aspect of the tile system that is important is that you need to account for a border for the scrolling system, for the smooth scrolling system, because it does a smooth scrolling automatically. So you need to account for an extra line and extra sides on each side. So when you're moving around, you have data to cover those scrolling areas. So for those who plan on using that chip, then you have to keep that in mind. It's one of those things that people don't get right away. So moving on. Finally, the sprites. The sprites are another interesting aspect. They have something very specific to them, because sprites are just little blocks of data that you can display anywhere on the screen, right? So it's not a full width of the screen. Like bitmap, tile maps are always very precisely, exactly. You need to go fetch the data for the whole line altogether. The sprite is not that at all. It's just a small blocks of 32 pixels every line. So the state machine needs to track the first of all, you need to enable it. It needs to be enabled. You need to go through the 64 sprites. You need to identify where on the vertical level they are. So are you basically the same machines go through every sprites and say, hey, are you enabled? Yes, no. Are you presently visible? Are you needed on that line? And yes or no. And if you are, then you need to go fetch that data in the VMem. And then what the state machine does is takes those 32 pixels and put it exactly on the line, the buffer line, where it needs to be in relationship to the rest of the display. So if it's on the 30, like it's the X coordinate of the sprite needs to be 32 pixels off the sides, so you put it in the right space. The sprites are tricky because of the line system. It requires me to erase the line every time. So I need to filling the lines and putting new sprites information, clearing the lines, which is not the case with the others because I fill the lines every time. And then I go through priority. So if I go through sprites and then I have one, let's say I have a sprite that is been displayed at the coordinate x20, but I have another one at at coordinate 25. So I need to go over the other one. So that's why I need to start from the lowest priority to the biggest priority. So I don't have to worry about, oh, this one is more priority. I need to keep the data for this one. And because also the data in the VMem for the sprite is at 32-bit boundaries. When I start putting in the screen, it's a byte boundary. So I need to deal with this. So I have to put the information into a temporary buffer because I read it in words, but I'm going to write it in bytes. So I need to put in a temporary buffer, and then I can put it at odd address, which is another weird things, but yeah. And then I go through all of them, and yeah. And I have to also look a line prior to it. So I need to identify, okay, are you a sprite that's going to be displayed the next line following, and so on and so forth. So same thing, but the sprites are really tricky in that sense with that kind of system. And in the case of the sprites, when you have a sprite, if it's, you start a sprite outside the screen. So the X and Y's are at 0, 0 when you're totally off the screen. That's not, I'm not talking about the border, I'm saying really out of the screen. So to get it to display on screen, you would have 32 by 32 to see it at the corner. The sprite's information also going to expand as well. It's going to double up. All these things when you're in double pixel mode double up. And yeah, so this is sprites in there. To conjure up a sprite on screen, it's, in terms of logic implementation, it's pretty tricky for the system I have implemented. But otherwise, it's pretty simple. It's on and off. You just assign the lookup table, the coordinates, and you say where it is in the memory. That's very simple. And finally, okay, so this is the big chunk before we're done. Where things happen and how things happen, it's really during the video, with the video portion of this thing. So when the video starts, you have a very long blanking period. And this is where, because the access to the VRAM is, you know, is limited. You cannot there's only so much you can do with VRAM for a certain amount of time. So during the V-blanking time is really the time, if you have any VRAM, VDMA to perform, this is where a good portion of it will happen. After that, it's just very leftover time from the line. So like I was mentioning, the way it works is that I put the line a little bit, you know, farther away from the beginning, but it's the same principle, it's the same concept, is when there's a line being displayed, during that time, the information for the next line is being fetched from memory. But before the line is being displayed, it's actually, if you remember, there was a lookup to the final RGB line. This is where the process of transferring and prioritize the pixel is being done at the horizontal blanking period. So before the line starts, well, while or at the beginning of the VH blanking, the processes of going through all the pixels and to see which one is which and which one will be displayed is being done. And then it's been stored into the final RGB line. So we have the information to be displayed. We don't need the VRAM anymore for that active line to be displayed, about to be. Okay, it's been displayed now. So meanwhile, the VMEM is available. There's nothing to do. If you don't have any graphics, then the VRAM doesn't do anything. But let's say, for example, you have a very complex game. You want to have a background with bitmap and stuff and blah, blah, blah. So how it goes is the master state machine will say, okay, bitmap, do we need bitmap? So that section can be there or not, but it's fixed. We know how much time it takes. It's going to take a portion of the bandwidth of the memory. And so, okay, go fetch the information we need for the next frame or next line. And then it goes, okay, we're done. Go get the tile. Tile is semi-fixed because we know how much time it takes to go get 4 layers. So, but it could be a short 1 layer, 2 layers, 3 layers, 4 layers. So we just took a portion of the bandwidth of the memory to go get that. And then there's the sprites, and their sprites is very variable depending on how many sprites. But keep in mind that if you can go fetch 32 sprites, but you can only see 20 of them. It doesn't matter. You take the bandwidth anyway because you had to read all this information. And I wish I would be able to predict which one will be displayed before and after, but again, it complexifies everything. But so that period is very variable. And ultimately what left over is taken by, you can use it to do a little bit of transfer will be happening. But you know, usually it's not much, but throughout the rest of the image, you can, you know, steal a bunch of time to go continue UV transfer. So you have to keep that in mind. So if you're transferring new information for that frame to come, then you might have some shearing in the screen, stuff like this. It's the same thing with the sprites. You have to be careful to make sure the sprite is completely finished before you start moving it around, because then you'll start seeing some shearing or half a sprite displaying if you want to do muxing. But one could actually use that to its advantage to start doing some weird effects. So there's definitely a lot of room. You can change everything about the sprites during the display of the image. So the good side is that you can take advantage of it. The bad side is if you don't do it at the right time, you could have some shearing and half a sprite there and half a sprite there and so on and so forth. And yeah, that's it. So that time is, so if you enable everything, you won't have any leftover stuff, and that's one of the reason it's kind of difficult to put more sprites in, because I don't know how much time do I have. So if I knew that, well, I could do it. If I knew that the tile map is not available, I could increase the number of sprites to 96. If I know that the bitmap is not there, I could increase the number of sprites because I have more bandwidth to give to doing sprites. But then, so yeah, so that's basically it. This is how the time is being shared, and that's the limitation of the controller. So how much bandwidth you have to go fetch that data. And Wiki3 might be different for that because I have two buffers, so I can ultimately go fetch that information on both buffer at the same time, so I can reduce by half, so I can go fetch way more. But we'll see about that. So, where are we? So that's it. So this is, I don't know, this is really like in the mouth. It's like a lot of information. But in a nutshell, this is how the whole concept works. This is how the, yeah, this is really the functionality of how I thought about it. And again, there's many, many ways we can go about designing a controller. I'm not a, seasoned 3D graphic person that did custom chips with 4 ATI, stuff like this. I really just created this from nothing. But at the time, that's what made sense, and it still makes sense today for this type of things I wanted to do. So that's it. I don't know if you have any questions or, yeah.
Stephanie, you can hear me?
Done. Yes.
So there is one person had said something in the YouTube chat. So I'll ask that question first. It was earlier on. It says,
yes.
How does this SRAM and Wiki2 bus speed compare to Mac 2 or Mac 2 FX video performance?
Max 2?
Macintosh. So the Apple Macintosh 2? An Apple Macintosh 2 FX?
I'm not sure. I'm not very familiar with the Mac early on was sharing the memory to do graphics. So, and I think it was doing what the Amiga was doing, was stealing the CPU cycles to do access to it. That be my take. Is it better? I would say yes to a certain degree, and I would say no to another. The problem with that structure or the way it is implemented is that it's very fast. It's very fast to do a lot of graphical elements at the same time. The biggest problem is once you want to read data off the VRAM, which is very, very limited. So when I talked about, for example, the I think the graphic at the end shows it better. So this time, okay, this VRAM time, this VDMA time is really where you can pull data off the video memory. And it's very limited. So because there's two types of transfer, you can go fetch one, because it can be useful to fetch data out of the graphic engine for collision systems. You want to know what pixels is for that bitmap, and you want to compare it to whatever happens. And so it's tricky because either you're going to go, the way it works right now is that you push a request into the wiki and you say, I want to go read the pixels. And then within the state machine, the master state machine, it says there's a portion I forgot to put, but there's a FIFO. And when there's time, it's going to go fetch that pixel, put it in FIFO and say to the system, hey, your pixel you wanted is there, right? Or you can do a transfer of VDMA to SDMA to a block of data that you have in your VRAM. But then if you don't have enough time, you might not have all the blocks you need. So it's tricky to read because everything goes so fast. There's really no time dedicated to that. In the old system, for example, with the C64, you could share the clock in two, and one time is the CPU, the other time is the video memory. So you can, and it's easy, it's because you have that time. The 816, for example, I said it, they use both sides of the clock. So there's no time for me to use that time nothing happens to go and fetch the data. So I think back in the day, the system was still pretty slow, and the CPU was taking still a lot of time to do a lot of things to go and split that time where there was nothing happening. You could steal the bus, go read the data off, and give it to the CPU or to write something from the CPU, so on and so forth. And as far as how they fetch the data off the DRAM, it's probably the same way. So they probably put in the buffer or line buffer, and they just went and displayed because they didn't have all the colors and stuff like this. But I think after exactly it happens, but the video cards brought this idea of separated buffer, so you could do all your things. I mean, I wouldn't see an RTX 80 using the main memory to do all its tricks and stuff. So I would not be able to answer specifically, oh yes, it's so much better, but if I remember, the Mac at that time were not colors, they didn't have all these different graphic features, because if I was just doing bitmaps, I would be way better. But again, hopefully I answer some aspect of the question in a way.
Okay. Someone else is asking for a demo, but I don't think you have really available. They're asking for a demo of the video processing or something like that.
A video, an example. I have people who design games and stuff.
So maybe you can later supply in the Discord some examples of that, like some.
Oh yeah, I can put some links. They can go on the website. The first thing on the main page is different videos of people who design games and stuff. I mean, it's pretty cool. Hold on a minute. I think I have some links here. I'll give it to you on the Discord. But keep going. I'll answer the questions.
The next question is, how big is the LUT?
The LUT is, the lookup table is, it's a lookup table from 8-bit per pixel. So it's a byte to ARGB, so a 32-bit, because the dual port memory in FPGAs are, 2 exponents something. Right now, there's no transparency, so it's RGB 24-bit. So that's why you can, out of 256 combination, have a full RGB palette. The way it is done is that you can choose 8 different palettes. So ultimately, in one screen, you could have 2048 colors. 8 times 256. That's it, right?
Sounds
yeah.
right.
It's 2K, 2K colors. So you could have 2,000 variation of the full color palette. That's it. So
Okay.
2,248 out of 24 million, 16 million colors. And you can pick and choose which one you want.
All right, let me take a question from the live audience, and then I'll just alternate back and forth. Anybody here in person have a question? Oh, here too. So, all right. So when you get the link, that's fine.
I just posted on Discord. So there's this. This is one. This is a great one.
And all right, so I'll read the next one. I read something about a hardware line acceleration. Is this true? And do you intend to add other kinds of graphics accelerations?
Okay, in Wiki 3, I want to do a line acceleration. I want to implement a line acceleration algorithm in there. Hardware, a very simple one, nothing too complex. So yes to that question. That's definitely in the wish list, because that's the thing. I'm on the verge. The release of the A2560K, which is the keyboard version that I've announced last year at VCF, and the Gen X is about to come out too, finally. So this is really the base to implement Wiki 3, which has 2 different buffers. I'm kind of definitely more room to implement these things. So the line algorithm is definitely in the wish list and will be done at some point when I'm, shipping stuff and I have my parts to ship. Other elements, I definitely want to get the collision system to be way better than it is now. It's difficult to say because I try to go and implement stuff that people need at this point. Because there's, you can go on a tangent and try to design everything you want, and then you come to a point where, okay, you know what, I think I need to stop because it's just people don't use it, right? It's just a waste of time to develop stuff that people don't use till they decide, oh, it'd be great if I had that. So maybe more sprites. Something I wanted to do was maybe have different sizes of sprites, maybe more of them. The line algorithm, transparency, support, you know, and collision system that is definitely better. And obviously the VDMA having more, you know, blitter type system type features. So in the short terms, that's what I see. I don't, maybe because I'm also trying to tackle, because the community brought a lot of people. At first I want to attract, by doing this, I wanted to attract a lot of people to do games, but games need like an audience, and I attracted more people towards like GUI and OSs and stuff like this. So these require stuff that are not necessary on the other side. So I'd like to maybe brought more feature to support like a GUI environment type of things. So that's the kind of thing I'd like to do to support those endeavors. So it's really at this point in time, I'm really trying to stuff that might alleviate some of the challenges that people wanting to do a GUI environment and stuff like this would have to go through.
Okay. Next question. Will Vicky 3 be backward compatible with Vicky 2 code?
Yes.
That's good.
Yeah.
That's an easy answer.
No.
That's good.
No, yes, it needs to be.
Yeah.
No, it needs to be. I'll put more registered on the side and not map at different places, but yes, it needs to be. Yes.
All right. Next one. If the line buffer has ARGB, is there alpha blending?
Well, that's what I was saying. The alpha blending is there. The transparency is a bit tricky in that structure, in that way of doing things, but I'd like to put in there. Like I said, early on, there was a lot of desires for a lot of things, but what happens is that there's a lot of desire for a lot of things at some point, but nobody does anything with them. When it's like, oh, if I have that, I might buy a machine, or if I have this, I might do this, and they never do. So it's kind of, I'm not saying it's sad, but for my own desire, for my own edification, yes, I would like to do a transparency, implement transparency in Wiki 3, yes, but I will do out of my own desire. Or I would do it out of, oh, I'm doing this game, I need transparency, absolutely, can you do it? And I would say, okay, you need it, so we'll try to implement it. It's like this fine line between, I'd like to, because it's part of the philosophy, to really get in there, do some work, learn new things, and struggle a little bit, because the mother of creativity is really the struggle, and try to pull it off if you don't have everything, as opposed to give them everything and they don't do anything with it, because that's what's been happening for the last 20, 30 years. We've been having everything, and we've been like, we have tons of memory, we don't care anymore, and there's like gigabyte size software that you're like, what's going on with these people? I was about to swear. What's wrong with these people? They're lazy, so it's a platform to stop being lazy. So yes, I want to enable people by giving them certain feature that would make their game better, but we're not at the point where people are, oh, I have this great game, it's going to be so much better if I add this. So it's kind of a vicious circle of me wanting to get them in, but if I spend months on it to develop a feature that nobody ever used, what's the point, right? I have sound chips that incredible, they're all together on one platform, nobody uses them. So what's the lesson to be learned from that? And people go crazy for the X16 with a beeper. It's like what the? So it's the same thing. So if people ask, I will create it. But but they need to get involved in the machine first. It's not like, oh, if you have this, I'll buy one. No. Get one, get involved, and then we get there. I'll give you what you want. It's more like this.
All right. Any questions from the live audience? Last chance. And it looks like that was it for the live chats. So that wraps up your talk for today, Vicky.
Yes.
Sorry, Stephanie.
Vicky.
Appreciate you doing the talk. So this was live streamed to YouTube, and it's also going to be, we're going to be processing it later after the show and releasing it in as your own separate talk.
Thank you very much for people for coming live, and everybody who's virtual. Thank you for VCF for inviting me again. Thank you, Jeffrey. I know you're working very hard. It's your baby. Thank you for inviting me again. If I can do anything for you, let me know. And I guess I will see you tomorrow.
All right, I'll see you tomorrow. Bye, Stephanie.
Thanks, everybody. Thanks,
right.
Jeffrey. I'll talk
All
to you
right,
soon.
have a good afternoon or night.
Thanks.
Bye.
All right, we're off.